that. Yes,
Can you
and
see
I
my
hear you.
screen?
Very good.
Okay, thank you. First of all, I'd like to thank you organizers for giving me opportunity to give this talk and to present present status and results from the coherent collaboration. It's been already a couple of talks on this conference about SEVENS or coherent neutrino scattering, theoretical and experimental overview. So I will do short introduction about coherent scattering, but then mostly focus on our efforts at the Oak Ridge National Lab and the spallation neutron source, where we have a first detection of this process in our future program. First of all, coherent elastic neutrino nuclear scattering, we call it SEVENS. This is a weak process which was proposed right after discovery of unique neutral currents in 1973. That was proposed by two independent groups, one from United States, from the Fermilab, Daniel Friedman, and the second is from St. Petersburg, Kopelyovich in Frankfurt. And as you can see, basically they submitted two independent articles within a few months from each other. So coherent neutrino scattering, this is when neutrino interact with entire nuclei at low energy and transfer tiny amount of energy or momentum into the nuclear recoil. So this process does exist in the, predicted by the standard model and predicted it pretty accurately actually. And you can see equation here. Turn out that because electroweak angle is 1/4 contribution from the protons, small, which is not marked here by Z, not zero, but small, and mostly it's contribution from the number of neutrons, which, so the process is proportional to the number of neutrons square. So this process has very large cross-section. So as you can see on the plot on the right, this is a comparison of different cross-section. For instance, SEVENS on the cesium iodide, you see orders of magnitude larger than other one. Next, by the strength is neutrino interaction on iron, on the lead with production of neutrons, and below some general processes like inverse beta decay or neutrino electron scattering. As you can see, there is orders of magnitude. So this cross-section is large and supposed to be detected easily, but the problem is we have to deal with the tiny nuclear recoils, which is difficult to do. And when Daniel Friedman published a prediction for this process, he said that this to detection it's an act of hubris. So it's very difficult because of the requirements for the low threshold and high backgrounds and so on. So it took more than 40 years actually to detect it in the first time. So it was significant development both in detector technologies and in neutrino sources. SEVENS has mixture between particle physics and nuclear physics. This F2 Q square, this is a so-called form factor, which reflect fact that neutrino is not always in the coherent scattering interact with entire nuclei. So at the low Q, it can interact with entire. At the high Q, it's interact with a portion of the nuclear. As a result, there is suppression of the cross-section. This is illustrated on the plot on the left when you see calculation for the SEVENS cross-section, which is dominant in the low neutrino energy, say below 100 MeV on the argon. But as neutrino energy going higher, charge current become dominant. So coherent scattering is interesting in the low energy range. And here the plot show the effect of the form factor for neutrinos with a spectrum decay from the muons and pions. And as you can see, there is significant suppression for the large nuclei or heavy nuclei, and it's getting smaller and smaller. So by measuring this process of the different nuclei, basically we can separate contribution from the high energy and from nuclear physics. Nuclear physics is extremely interesting here because basically neutrino is sensitive to the skin of the heavy nuclei. so we can measure density of neutron distribution in the heavy nuclei, and it can become directly linked to the neutron star density. So this is somewhere when we do in the lab can be compared with what we can do looking up in the skies. Seventh as well, floor for dark matter experiments, looking for the WIMPs. This is irreducible background unless experiments will come out with some ideas how to do directionality. But you see all present generation of experiments are pretty close now to this so-called neutrino floor. And knowledge about exact position of this neutrino floor is important for all these experiments as well. Seventh as well is a probe for non-standard neutrino interaction. So here you can see a Lagrangian when you have components with direct coupling neutrino to quarks, and turn out this parameter space is not constructed very well. So the one Charb experiment, as you can see, the constant for this interaction is on the order of unity. And because coherent scattering is sensitive to that, we can significantly restrict a region of parameters here. And this is actually has very big implication for the dune, because non-standard interaction can create degeneracy for oscillation, which can be detected by dune. And degeneracy is between direct mass ordering and inverse mass ordering. So there is a reference on that. As well, seventh, because it's sensitive to the number of protons, not much, but still. So we have sensitivity to electroweak angle. So it's open possibility to measure electroweak angle on the very low Q when the data are limited and the error bars are large. And it was just mentioned on the previous talk, this problem with the G-2 deviation from the standard model. It could be explained by low mass Z, and therefore it will be sensitive to the difference in the electroweak angle from standard model prediction. Seventh has sensitive to the magnetic moment as well, when the cross-section should be enlarged in the very low Q square. However, here sensitivity is not very large. We might probably improve something for muon neutrino magnetic moment, but for electron, it is not. And seventh is important for supernova dynamics. This is how during the initial teleptonization, proton-neutron star created, and then neutrinos are trapped into proton-neutron star through the seventh. So exact knowledge of the seventh is important for supernova simulations. So there are big efforts around the world actually to detect sevenths. As you can see, we have experiments around the globe: Korea, Taiwan, Russia, Europe, France, Germany, in the US and Brazil. There is a new efforts. I just put it like a couple of days ago in Dresden on the reactor, and I do not have logo of experiment yet. So I just took liberty, use the detector number and to put logo like that. So it's not official one. So all these experiments except two, Captain Mills and the coherent, using neutrinos from accelerator, from nuclear power plants. Nuclear power plants has advantage that neutrino flux is enormous basically, but the problem is it's not pulse source. So it's difficult to see effect in the background subtract. And in addition, neutrinos from reactors are on the lower edge at end of the spectrum. So it's more difficult to detect than from accelerator. So what we use in coherent, this is so-called spallation neutron source, which located in the Oak Ridge National Laboratory in Tennessee, US. So you can see this outline of this complex. So we have linear accelerator, which produce pulses with about 600 nanoseconds. And these pulses are piled up on the accumulator ring and then later delivered to the target with a frequency of 60 Hertz. For this source, neutrinos produce as a result of decay at rest pions and the muons. So 99% of neutrinos has energy below 53 MeV. And because of the pulse structure of this accelerator, backgrounds is suppressed by a factor more than 2000. So this is a mechanism of production neutrinos. So proton beam hitting mercury target, which sits inside stainless steel vessel. And as a result of proton interaction with the mercury, there is production of pi minus, which quickly stop into the bulk target and capture. And there is production of pi pluses, which decay into muon neutrino and to muon, and then muon decay into neutrino. So as a result, for each pi plus production, we'll have 3 neutrino flavors, exactly 3. And all of them produce basically the same quantities. But because of the different lifetime of the pi plus and the mu plus, we can separate neutrinos, so-called prompt neutrinos, which is a muon neutrino, and delay neutrinos. So potentially we have sensitivity to the flavor of neutrino in our experiment. And this is a prediction for neutrino energy. You can see this spike. This is from the pi plus decay at rest. And this this is from the muon decay. So what we use for this experiment is a basement in the main target building of the SNS. This is an area which is very well separated from the all neutron scattering experiments, as well from the target. So backgrounds here is tolerable, let me put it this way. Everybody who is doing neutrino physics knows that if you're close to the powerful source of neutrons, this is a trouble. So here we got lucky to have very well protected and good location, which is pretty close to the main target. And as I said, because this decay at rest, all neutrinos are coming isotropically. So we have several detectors which are located in this place, which now called Neutrino Alley. First experiment was done with the cesium iodide detector. Now we have data on the liquid argon detector, and 2 more detector technology is being deployed this year, 1 germanium and sodium iodide. So this is the first result with a 14 kilogram cesium iodide detector. As you can see here, there was a picture of installation. Actually, the preparation was quite long, but installation itself lasts only for 1 day. 2 or 3 people did work on it. Detector was built out of single cesium iodide crystal with the mass of 14 kilograms, which was encapsulated in the pretty sophisticated layers of the different shielding. This is first result. What is shown here, for the first result, we took 16 months of the data and accumulated 1.4 10 to the 23 protons on target. This is a beam number of protons delivered to the target. Or for these quantities, we already can calculate it in grams. So it was 1/4 of the gram of the protons. This is a result compared with the prediction from the standard model. As you can see, initial accuracy is not very good, but that was definite signal with 6.7 sigma deviation from the 0. And on the bottom, you see this is because we measure at the same time signal in the background, we can subtract signal from background. As you can see, when the beam off, nothing here. When the beam on, there is clear excess in the energy plot and as well in the timing plot. And as soon as you see 2.2 microsecond distribution here, this is a lifetime of the muon. This is a clear indication those are neutrinos. And as people said, that was the first working handheld neutrino detector in the world. Presently, we've accumulated more statistics. This experiment done and decommissioned, but we have 2.5 times more statistics on tape, and results are coming within the next few months. Second detector was argon, liquid argon detector. Detector initially was built in Fermilab for 7th efforts, but Fermilab decided not to do it. So detector was moved in the SNS in the 16. We rebuilt it because initial light collection was pretty poor. And we start to operation in July 2017. The first results, as you can see here, run from July 17 to January 19. And this is some details about detector performance, like separation between nuclear recoils, 7th signal from E gamma. This is a resolution detector. This is some calibration. But the bottom line, we again see effect. We see 4 sigma effect for the argon target. So now we have this leverage. We can put second point here. So we start actually to probe this n-squared dependence of the cross-section for the 7s. And again, so that was initial data. Right now we have 3 times more statistics, and next year hopefully we'll produce results with a much better statistics here. So what did we learn from here? We learned 3 things. First, that 7s does exist, this process. However, nobody dubbed it, but it was nice confirmation. Second is we have very bright, powerful neutrino source, which we can use to study 7s. And now we have technology in hand how to measure 7s. But both of these, all 3 questions is basically binary answers, yes, yes, and yes. And there is not much physics yet. And the problem is to do accurate measurement, to test standard model, we need to go to the next step and start to measure 7s with the high prediction. One of the problems that we have at SNS, we don't know neutrino flux very much. Our estimation that we know it with 10%, which is a big limitation for accurate measurements. This is based on the fact that production of the pions is not known very well for the proton-mercury interactions. So our idea is to calibrate SNS by using known reaction of charge current of neutrino interaction on deuterium. A cross-section for this reaction is very well understood and known with the accuracy between 1 and 2%. So our next goal is to deploy about ton-scale heavy water detector and the SNS and to calibrate it once and forever. After that, there will be no limitation basically on the knowledge of the flux will be on the level 1 and 2%. In addition, this detector gives us opportunity to study neutrino interaction on the oxygen. And I didn't mention, but neutrinos from SNS about the same energy spectrum as from supernova. And neutrino interaction on the oxygen for the supernova range never been measured. So that's of interest, like super Capiacanda detector. If they will see supernova signal, they need to know a little bit about this interaction. So this is some ideas what the heavy water detector can do for us. There is some details, but what we'll look on the right one, this is statistical precision in tons of SNS year. So after 1 year of operation, we'll know the flux by 5%, and eventually we'll know down to 2%. SNS, by the way, it's moving forward as well. So today, this is a 1.4 megawatt source with energy of the beam 1 GeV. There is coming energy upgrade. So the power of the accelerator will go up to 2.0 megawatt and the energy will go 1.3. So we'll have much larger neutrino flux by a factor of 50. And in 7 years, there is a plan to build second target station, which will have 1.7 megawatt power with 15 hertz. And neutrino protons will be delivered in the sequence to the first and to the second. So there is very interesting opportunity for neutrino physics when you have 2 basically identical sources and you can put neutrino detector somewhere here and take advantage of the different baselines. So our long-term program of the coherent to improve accuracy from the previous existing measurements for cesium iodide and for argon, and to deploy new detectors, germanium detectors and sodium iodide detectors to continue to map this area and to continue to do separation of contribution from the standard model, from high energy physics and into nuclear physics. So one of the plans is to, right now we have a relatively
Sorry,
small...
Yuri, 20 minutes.
Okay, I'm on time. So we have a relatively small liquid argon detector because we're limited with the space, but there is a plan actually to build 1 ton liquid argon detector, which will give us very good statistics. And addition, it will measure neutrino argon charge current, which is important for the dune. There is one interesting opportunity, is not directed to neutrino physics. SNS proton beam can produce as well dark matter like particles, say from decay of the pions. So there is some numbers here, our predictions, what we can do, but there is a major update is coming next week. We already have some limitation of production for the dark matter, and that's coming next week. I cannot say it yet, details. And in addition to liquid argon detector, we're going to put a sodium iodide detector. We have about 2 tons of sodium iodide detector on hands, and deployment is coming later this year. And in addition, array of germanium detectors with a total mass of 60 kilograms. Again, detectors on place. All hardware basically does exist, and installation is going to happen later this year. So my summary is detection of sevens on cesium iodide and argon targets open new portal to look for physics beyond standard model. This is a first step, limited accuracy, but we have to move forward to increase accuracy. Neutrino alloy SNS is unique laboratory to study properties of sevens and not only. And coherent collaboration is actively building and has a plan to deploy in near future new sets of experiments. As I said, liquid argon, D2O, sodium iodide, germanium, and maybe xenon target as well. And all this activity has implication to the particle physics, test of the non-standard interaction, precise test on the standard model, maybe search for the dark matter, has implication for nuclear physics, study density of the neutron distribution on the heavy nuclei, and as well has astrophysics implication because we will calibrate basically dune and super Kamiokande for detectors for the supernova neutrino signals. And this talk was done on the behalf of Coherent Collaboration, which right now consists of 21 institutions, mostly from US, but there is a big group of people from Russia, Canada, and Korea. Thank you.
So thank you very much for that clear and interesting talk. There's time for a quick question. Alexander, please.
Yeah, well, thank you very much for your very complete, I should say, and very interesting presentation of different successes of sevens. I would like to really to underline once again that sevens serves as a laboratory for fundamental physics. And let me recall that not only neutrino magnetic moments can be probed or constrained by the sevens, but other properties of neutrinos such as neutrino charge ready or even milli-charge can be tested, and there are constraints from sevens. Well, thank you.
Yes, I absolutely agree with you. I just didn't mention it because limited time, but this is very interesting topics, and we are looking on limits of neutrino charge and so on as well. But thank you for your comment, and thank you for your support for this kind of physics.
So Anatoly, if it's a quick question, please go ahead.
Yes, I hope. I'm curious about the following. The argon has different isotopes. So if to compare cross-section of argon 40 and argon 36, we have a ratio of the cross-section 1.5. It seems attractive to compare two detectors with argon 36 and argon 40 at the same beam. So haven't you considered the possibility of this?
Yeah, as you can see here on the plot, when the argon I showed, there is 3 dots. So this corresponding to 3 different isotopes. And what we cannot separate them independently yet. So what we're showing basically contribution from all 3 of them.
Okay, thank you.
And the same as you can see for germanium, there are many isotopes. There are some ideas maybe to try to enrich germanium, like for instance, take detectors from Gerda collaboration when it's enriched in germanium 76 only, but this is under consideration.
But
this will be very interesting to do.
Argon to enrich? Specifically
right now, we do not have resources to enrich argon, but
yeah.
That will be nice as well. I agree.
Okay, thank you very much. And maybe we can move on to the next speaker, Sanjeev Agarwala, about BSM searches in neutrino experiments. Thank you. I can see that, so I don't hear you yet.
Can you hear me now?
Yes. Good. Please go ahead.
Yeah, let me just make it full screen.
Okay.
So is it full screen? I can't hear you.
It's okay. Please go ahead.
And my slides are being changed, right?
No, we're still on the first one.
No?
Still on the first one. Now it's on, now we've moved.
Okay, so there is some issues. So let me just.
Sanjay, could you please try to start the share once again?
Okay.
So shut down it and start again. It
Okay.
should work.
Okay. So how should I do that? Just stop sharing. Yeah. I did that. I don't know whether it is working. Is it fine?
So now we're on the first slide.
Now you are on the second.
Yep, good.
Yeah. Okay. Thanks a lot. So first of all, I would like to thank the organizer, especially Professor Alexander Studkin, for inviting me to give this talk. So he asked me to give a review on landscape of BSM physics at neutrino experiments. So before I begin, I must admit that it has become an industry now. And you can see every week there are papers on this topic. So in next 25 minutes, it will not be possible for me to cover all the work. So I'm not going to do that also. So what I will do basically, I will just try to convince you that neutrino experiments are indeed a very nice and interesting place to look for BSM physics across a wide range of energies and distance scales. And there are some interesting results are also there. So we should definitely try to build more intense experiments and find experiments to look for BSM physics. So let me start with some motivation. So I'm on my first slide. So the question that I would like to ask, that why we are so much interested in BSM physics in neutrino experiments. So after having a thought, I think that the main motivation is that that we have detected neutrinos from so many different sources. And now we know how to detect neutrinos at various energies efficiently. And over the last 10 years, our knowledge on neutrino oscillation parameters have been improved a lot. So in this slide, what we have plotted is basically the global fit studies of 3 different groups. One, the study from the Bari group. Then in the middle, we have the study by the Valencia group. And then we have the study from the new fit collaboration. So what we have done, we have 6 oscillation parameters in 3 neutrino paradigm. And here you can see these dots are representing the best fit. And these are the 1 sigma range in the shaded band. And these straight lines are denoting the 3 sigma ranges. So you can see that all the 3 global fits are pointing towards almost same range and same best fit values. That means we have a very robust 3-flavor neutrino oscillation model in our hand, and it can successfully explain all the data. And you see the relative 1 sigma precision in the boxes. I have mentioned the relative 1 sigma precision. So let me start with CP. So just take a look that now the CP values between 0 to 90 degree, they are already ruled out at more than 3 sigma confidence level. And this is a remarkable achievement. And here you can see for the first time, we are also quoting a relative 1 sigma error on CP phase, and which is around 16 to 20%, and depending on your what mass ordering you assume. By the way, the red lines are for normal mass ordering, and the blue lines are for inverted mass ordering. But you can see for theta 2-3, this is the largest uncertain angle we have in the 3-flavor paradigm, and we have almost 6% error. And for theta 1-3, Diabe has nailed it completely, and we have almost 3% error. For theta 1-2, 4.5%. For solar splitting, we have 2.3%. And for atmospheric splitting, this is really very nice. This is 1.1%. So I would like to motivate you that we are at the right time to ask that whether our oscillation experiments can see also any subleading effects due to some BSM scenario, because your uncertainty on the 3-flavor oscillation parameters are now within under control. And also in the experiments, we have very good handle on our systematic uncertainties. So that's why I think we are all looking for BSM in neutrino experiments. And what about future? So I'm on my second slide. So here I just want to tell you, these are the plots that I took from the Juno collaboration. So here I'm showing you what Juno is going to give us in down the line, say next 5 to 10 years. So you see, as far as theta 1-2 is concerned, this relative error of 3.9% will go to 0.7%. For theta delta M21 square, you see the 2.8% present error will go to 0.6%. As far as the atmospheric splitting are concerned, we will hit a precision around 0.5%. So I must say that we have a bright future as far as neutrino oscillation parameter measurements are concerned, and Juno will improve significantly our knowledge in this direction. And these developments are very crucial because these errors are now so tiny that indeed it can give us an opportunity to probe any subleading BSM effects in next generation long baseline or atmospheric experiments, or it certainly, it is relevant for IceCube upgrade and also IceCube Gen 2, which is going to come around 2030. So let me go to my next slide. So we all know, we are convinced throughout this workshop that non-zero neutrino mass is the first experimental proof for BSM physics. And you can introduce these BSM possibilities in the framework of effective field theory. So in the left, you can see the effective Lagrangian. You have the tree-level contribution. Then you have the dimension 5 parameter operator, which gives you the neutrino mass. And you have also then the dimension 6 operator, which are responsible for non-standard interactions. So these BSM scenarios, they naturally arise when you try to generate neutrino mass and explain the neutrino mixing. For an example, the seesaw model. So these many models of BSM physics, they basically suggest few important things. What we get from these models, they suggest that there can be new fundamental particles, or there can be new fundamental interactions, or there may be new sources of CP invariance violation. There can be lepton number or lepton favor violation. We had a very nice talk by Anna in the beginning of this session. So now the question comes, can we see the signature of these BSM scenarios in neutrino experiments? So what I would suggest, according in my point of view, the best bet, one of the best bet to look for new physics is to probe these new physics at very high energies, at the energies around TeV, PeV, where you basically observe high energy astrophysical neutrinos coming from very large distances, which are of the order of megaparsec to gigaparsec. And we have very good candidates. We have IceCube at the South Pole, Chem3 net in the Mediterranean Sea, and there will be future IceCube Gen 2. So what is important here, that you have a new approach to probe new physics, which are not within the reach of modern colliders. You are really probing this BSM physics at a completely different length or energy scale, which are TeV and PeV. And the cross sections are also very high over there. And these neutrinos are coming through a long distance, so new physics can accumulate. They have time to gather the impact of new physics on the way when they travel from source to the detector. What is the another approach? Another best bet, in my opinion, is to look for this BSM at low MeV-GeV energies, where we have very nice accelerator and atmospheric neutrinos, and they are traveling terrestrial distances, few meter to thousands of kilometers. And we have a very strong candidates in future. One is Dune in USA and T2 Hyper K in Japan. And there are also atmospheric experiments in the pipeline, like in our country, the India-based Neutrino Observatory project. So what I believe, that these experiments are planned to measure oscillation parameters with high precision. And it means that they will be sensitive to any subleading percent level effects due to BSM at low energies. So this is the landscape that I want to convince you, that you have a landscape in neutrino physics to probe BSM across 18 orders of energy and 25 orders in the length scale. So I don't think there will be any other avenue, better avenue than this to probe BSM. So let me move ahead. So when we talk about BSM scenarios, I just tried to mention some candidates, like we have long range interaction, we have the decay, possibility of decay of neutrino, we have a possibility of a sterile neutrino, then we have non-standard interaction, then we have dark matter neutrino interaction. So you can just see in literature, plethora of these possibilities have been explored. I'm not going to talk about all this, but I will just give you flavor on some selected topics. So these are the candidates of BSM. Now let me proceed. Now, when you think about a neutrino experiment, your new physics can come when neutrinos are produced at the source. So these new physics can affect your flux. Here you can see an example. If you have some new physics through these possibilities at the production level, they will alter your neutrino flux. Okay, what next? Then you can have new physics when neutrinos propagates from source to detector. So when some new physics, you can see in this block, these are the candidates, popular candidates, which affect neutrino propagation, then your neutrino flux or neutrino oscillation phenomena or neutrino mixings can be altered, because there is some BSM physics when neutrinos travel from source to detector. Here in the right, you can see a plot where I'm plotting the appearance probability in T2 Hyper K experiment as a function of energy. And I'm showing with various colored lines how the probability will change if there is a light EV scale sterile neutrino. This is just an example, okay? Now, there can be new physics when you detect neutrinos at the detector. Your detection cross-section can also be altered if there are some new physics. And I am showing another example from one of our study for the Borexino experiment. And you see that if there are some new physics is coming or new interactions are there due to some Z prime, it can alter your neutrino electrons elastic scattering cross section, which is used by Borexino. And you can see, it can change the amplitude of the cross section as well as slope. So ultimate, the game is you have to be very careful when you are dealing with a neutrino experiment. Your new physics can pop up at production or propagation or detection. This is the summary of this slide. And this is true for any neutrino experiment you may think of. So this is a nice slide. You can see here that if I talk about very high energy astrophysical neutrinos, then we have 4 key observables to probe this BSM physics. What are they? The first is the effects. This new physics can affect the energy spectrum. The standard expectation is that they will obey a power law. But if you see any deviation, you can say, okay, I am seeing a new physics. Then it can affect your arrival direction. You can see in the green band. So standard expectation is for diffuse fluxes, you assume or you expect that the flux should be isotropic. But if you detect them and if they are not isotropic, then this can be a hint of new physics. Another handle you have, it can affect your flavor composition, which has been studied extensively in literature. And also it can affect your arrival time. So now people are trying to use this 4-dimensional approach to nail down BSM in very high energy neutrinos. And you can see with these threads, we are trying to connect which new physics scenario will affect which observable. So if you take a close look, you can see that there is a connection between the observables and the type of BSM. So this is a very rich physics. And with IceCube upgrade and with IceCube Gen 2, and there are other detectors in Chem3Net, we have a very bright future to nail down these BSM scenarios. Now let me proceed. So in this direction, we did a work a couple of years back where we tried to probe the long-range interaction that may exist when these astrophysical neutrinos are coming to the IceCube detector from this galaxy or outer galaxies, and the electrons that we have in the big repositories in our local and distance universe. So there are some well-motivated abelian models is there, which are the economical extension of basic standard model, and they give rise to some Z prime, and they can be also super light. And if your new mediator is very light, then your force will be long range. So in this paper, using these astrophysical neutrinos, we placed an ultimate bounce on the coupling and the mass of this new Z prime. So you can see in this slide, you have huge amount of cosmological electrons. Then you have electrons in the Milky Way. You have electrons in the sun, in the moon, in the earth, and you can see those numbers. Now, if there is some Yukawa interaction is there between these electrons and these propagating neutrinos, then your oscillation on the way, the oscillation phenomena will be affected because of the presence of these new interactions. Your mixing will be basically altered if there are these new interactions are there. So in this plot, you can see using the flavor ratio of IceCube, we placed a very tight bounce on the mass of the new mediator and the coupling. And I want to just tell you that this coupling, we can even go beyond the gravitational coupling, which is 10 to the power minus 19. You see that, since there are so many electrons we have in the repositories, so we can really probe very small amount of coupling and a very tiny mediator mass. So let me just proceed. This is just an example. There are plethora of studies using astrophysical neutrinos. Now let me just elaborate for a few minutes on non-standard interaction. There have been many talks in this workshop on NSIs. So I told you that NSI can affect your production. They are charge current type. They can affect your detection. They are also charge current type. And they can affect your propagation, but that will be of neutral current of nature. So these are the two nice review articles. If you want details, you can take a look. So here I am quoting the 2 sigma allowed ranges on these NSI couplings, which have been derived in this paper in a detailed fashion using all the available oscillation data plus the data from coherent experiment. And these are, you can see that we have very tight bounds on these epsilon parameters. And these epsilons are nothing but the dimension 6 4 fermion operators. And these are the neutral current NSI bounds, which basically affect the propagation of neutrinos. Okay. So you see these epsilons, basically you have 3 off-diagonal epsilons, flavor violating, and you have 3 flavor conserving non-standard interaction parameters. So when we do phenomenology, we use these effective NSI parameters, which are basically written in this fashion. You can see my cursor. So in the same paper, they also derive the bound on these effective NSI parameters. So these blue lines are showing the bounds using all oscillation data, and the cyan lines are showing the bounds using oscillation plus the coherent data. And you can see that we have very tight constraints on these on these epsilon parameters using oscillation data alone, and coherent data is also helping in some parameter space. Okay, what about the charge current NSIs? They affect the production and detection of neutrinos. So there was a nice review by Yashman Farzan and Mariam Tortola in 2018, and they have summarized all the bounds which are coming from experiments like Diabe, Nomad, Carmen, and some also measurement of kinematic value of GF. So you can see that also in that direction, neutrino experiments are playing a very important role, and they are giving us very tight constraints. So let me proceed. So this is just an idea how NSI can affect the Borexino experiment. So here in Borexino, you use neutrino electron scattering, and you can have the epsilon with electron flavor or tau flavor, and you have both right-handed and left-handed. I am showing what is the bound that you can expect from the present Borexino data if you assume the high metallicity standard solar model and low metallicity standard model, standard solar model. There are 2 models for the standard solar flux, and you can see how these 2 fluxes will give you these bounds. But most interestingly, if you see on the top, there is a nice complementarity between the bounds that you get from Texono, which is a reactor anti-neutrino experiment, and the Borexino, which is a basically electron neutrino experiment. So when you combine electron neutrino and electron anti-neutrino, the role of GL and GR, they interchange. So you have a complementary bound. You can see from this figure, and ultimately you really nailed down the parameter space, which is very small when you combine the data. So another important message I would like to tell you, that we need to really look for all possible avenues at low energies, at medium energies, at high energies, and we need to combine if the same physics affecting those experiments at different energy scales. So let me proceed. So another interesting candidate for BSM is light EV scale.
Sorry, 20 minutes.
Yes. So I don't need to elaborate on this physics because there are many talks in this workshop. So we have a long-standing saga of EV scale anomalies. We have LSND anomaly, mini-boon, reactor, gallium, and in last few years, we are also seeing some anomalies from NEOS, DANCE, and Neutrino 4, and they are all hanging around 2 to 4 sigma confidence level. So the question is there a EV scale sterile neutrino? So there are a lot of, so the main issue when you think about EV scale sterile neutrino is the tension between the appearance and the disappearance data. From LSND mini-boon anomaly, they are telling you that the product of θ14 and θ24, these 2 mixing angles should be finite. And the reactor and the gallium anomaly is telling that θ14 also has to be finite. But we don't see any trace of sterile neutrinos in disappearance, neon disappearance experiments, that means theta 24 has to be 0. So you see, this disappearance and appearance measurements, they contradict each other, and we have a huge tension, and we need to address that in coming years with dedicated experiments. So we have several short baseline reactor experiments in the pipeline. I'm not going to go into the details because it has been discussed in this workshop. And here in slide number 21, you can see the present sensitivity from all these short baseline reactor experiments, and these are the future sensitivities. So this right-hand side plot is telling you that you can probe the new active sterile mixing angle up to the level 10 to the power minus 2 in this future dedicated short baseline reactor experiments if your new sterile neutrino is lying around EV scale. Fermilab short baseline program can also add into that direction. They will have a very good sensitivity for the product of theta 14 and theta 24. They will have a very good sensitivity to theta 24 alone through their disappearance searches. Now, here in this work, we also showed that this EV scale sterile neutrino can also affect your long baseline measurements. And in this work, we showed that if there is a light EV scale sterile neutrino, then Dune will not be able to tell you that whether theta 23 is below 45 or above 45. This is just an example. There are lots of work in literature along this direction. So just
23 minutes, please, yeah. Conclusions.
So last 1 minute. So there also is another interesting candidate, which is the CPT LIV, Lorentz invariance violation. So you can just look at my slides. So I just want to tell you that IceCube atmospheric neutrino data is giving you the most stringent bounds on these LIV parameters. You can take a look in this Nature paper. And there is another interesting model is neutrino decay. There can be a visible or invisible decay. And these are the bounds you can see from these two slides. So let me conclude. In my opinion, all the oscillation experiments should be in principle sensitive to BSM. But to my opinion, high energy astrophysical neutrinos are going to play an important role at very high energies. And at MEV GeV energies, you can rely on long baseline or future atmospheric experiments. And there is no doubt that BSM will become a dominant physics topic in next 5 to 10 years. I apologize if I missed your interesting word, but time is short. So stay tuned and thank you.
So thank you very much for that insightful presentation. Now, I think we are a little bit short of time, so maybe if people have questions or comments, they could discuss with you offline. So thank you very much.
I can take one more question or something if there is any pressing question.
So there are no hands up. So okay. I think I have a comment, but I'll send you an email. So
okay, great.
Thank you. And we can move on to the last talk by Sabya Chatterjee about neutrino NSI. If you stop sharing. Thank you.
So I can't share still. Hello, can you hear me?
I can hear you. Aha.
Okay,
there.
Fine.
Yes. So now maybe you can share.
So can you see my screen?
I see your screen and I see
Great.
A title slide.
So is it okay? Can you check it? Is it moving?
Yes.
Okay, thank you.
Please go ahead.
So first of all, thank you very much, the organizers, for giving me for the kind invitation and for giving me the opportunity to present my work here. So today I'm going to talk about the neutrino non-standard interaction, a possible solution to the nova and T2K tension. So this work actually was done by with Professor Antonio Palazzo. So let me start with some basically few known unknowns in neutrino physics, although we know that for past few decades, the tremendous efforts and invaluable contribution from the neutrino experiments have established the fact that neutrinos are massive, and we have got quite a few success in this regard, but still there are few things which needs to be addressed. For example, if we talk about the standard 3 neutrino framework, we do not know that whether it is the neutrinos is Dirac or Majorana particle, and also the oscillation experiments are sensitive to the magnitude of the mass square differences. So we do not know about the absolute masses M1, M2, and M3s. The sign of the solar mass splitting delta M21 square is actually known quite well, which is positive, that is M2 greater than M1. But the sign of the atmospheric mass splitting, which is unknown, and this is basically known as the hierarchy problem, where M1 less than M2 less than M3, we call it normal ordering, normal hierarchy, and M3 less than M1 less than M2, we call it as a inverted ordering or inverted hierarchy. Also the magnitude of the atmospheric mixing angle θ23 is also unknown. This also gives rise the famous octant ambiguity problem. It might be less than 45 degree, equals to 45 degree, or greater than 45 degree. So less than 45 degree, low as the known as the lower octant, and above 45 degree we call it higher octant. And for 45 degree it is maximal mixing. And also we have some hint about the CP phase as of currently, as I will discuss in this talk, but it is not confirmed very precisely. So it has a huge uncertainty on that CP on delta CP. So, and now on top of that, as I mentioned, that even though the standard 3 neutrino interpretation framework is quite a success in explaining all the data, but still there are few phenomena already exist in the literature for which indicates towards some kind of new physics scenarios. And for example, those new physics scenarios, I just have mentioned few of them here. For example, it might be a sterile neutrino, it might be long range forces, non-neutrality nature of the P-minus matrix, CPT violation, and non-standard neutrino interaction, and many others. So now for the past few decades, one of the most popular new physics scenarios, which is basically the NSI, non-standard interactions of neutrinos, and it has attracted quite a lot of attention from the theoretical point of view, from the experimental point of view, both. And in this work, actually, we are going to explore the impact of NSI in the interpretation of the current T2K and nova tension. So let me begin with some very brief, although this has been already discussed in this conference earlier by others, about the current status of the 3 neutrino parameters, where we can see that we know that the standard 3 neutrino framework, we have 3 mixing angle, 2 mass square splitting, and 1 CP phase. So θ12 is known quite precisely. θ13 is also known very precisely. Delta M21 square also known, it's positive, and also its magnitude is known very well. And delta M31 square, again, it is also known very precisely, but its sign is unknown. And now in this wheel, we can see there are 2 parameters which are mostly unknown. I mean, it has a huge uncertainty, which is one of them is the atmospheric mixing angle θ23, and then another parameter is the delta CP, electronic CP phase. So let me discuss about some very briefly the NSI and its presence in the oscillation framework. So the effective 4 Fermi flavor changing neutral current NSI is actually realized through this well-known Lagrangian, and in here actually epsilon alpha beta, which is basically the sum of 3 combination epsilon alpha beta E, and then epsilon alpha beta U quark, and then down up quark and down quark. So these epsilon alpha beta are the strength of the NSI, and there might be two interaction. One is charge current interaction and another one might be neutral current interaction, but for this purpose we are talking about the oscillation. The NSI, basically neutral current neutral current NSI, because we are concentrating on the propagation of the neutrinos from the source to the detector. So we know that the neutrino flavor eigenstates are related to the mass eigenstate by this equation, by this PMNS matrix U alpha I, and where U is the PMNS matrix, which is basically composed of three mixing angles, theta 1, 2, theta 1, 3, and theta 2, 3, three Euler angles, and one CP phase, delta CP. So now the time evolution Schrodinger equation for the neutrino flavor eigenstate in vacuum is given by this equation 1, where you can see that I define here is U m square U dagger as H vacuum part. Now when neutrinos propagate from the source to the detector, it goes through also the matter if the distance is high, long enough. And while going through the matter, it goes through the interaction, some interaction which is basically charge current interaction and also the neutral current interaction. Now, when there is such kind of interaction, then on top of equation 1, there is the H vacuum part in equation 1, there is extra term added there, extra matrix, which is the meta matrix we call it, and which is basically VCC plus VNC at the diagonal, and VNC and VNC in the 2, 2 and 3, 3 positions. Now, this is given by the equation 2, and then the H vacuum is actually now can be called as H matter, where VCC is the charge current potential for the neutrino and VNC is the neutral current potential for the neutrino. Now for anti-neutrino, just VCC goes to minus VCC and then VNC goes to minus VNC. So now on top of that, if there is some kind of non-standard interaction, then this the equation 2 in the previous slide actually changes to equation 3, where there is another term which we call it VNSI, which is matrix, basically VCC times the strength of the NSI epsilon alpha beta is given by this VNSI term, where epsilon alpha beta, this is basically represent the NSI strength, this epsilon alpha beta, as I mentioned earlier. And this epsilon alpha beta in general, basically the diagonal one entries are real and the off diagonal are complex, and the non-neutrality demands, the hermicity demands epsilon alpha beta equals to epsilon beta alpha star. Now, since we have the equation 3, we know that this is a time evolution equation, so that we can calculate the probability by the scattering, by the square of the scattering matrix element. And if we want to calculate the probability for one flavor nu alpha transforming to the another one nu beta, that can be calculated by S beta alpha to mod square, and where e to the and that is S beta alpha basically e to the power minus H L. L is the length from the source to detector, and there is mod of e to the power minus HL square, where H is basically can be replaced by H NSI from equation 3. So in our analysis, we assume one NSI parameter at a time, and we have mainly considered the impact of the two NSI parameters, epsilon E mu and epsilon E tau respectively. Okay. So in presence of NSI, the nu mu to nu E transition probability can be written approximately by 3 terms, which is P0 plus P1 plus P2. And P0 and P1 are basically the standard term, which is also present in standard 3 neutrino oscillation probability in the absence of NSI. Now, in presence of NSI, there are 2 terms, P2 for now in E mu sector P2, and there is also in the E tau sector, and both are different. Now you can see from the P2 that P2 is the term which actually which consists of the NSI effect, and as we can see that there is epsilon E mu amplitude, and then basically there is also another new phase on top of the leptonic CP phase delta CP, which here we call it phi. Now for NSI EMU sector, we call it phi EMU, and then for ETAU sector, we call it phi ETAU. So since we have considered the impact of the NSI epsilon EMU and epsilon ETAU, and so let me just tell you that as of the current model independent based limit that comes from the ice cube, and very recently they have also they have published this paper very recently, and then we can see from the ice cube limit that epsilon EMU basically is less than 15%, and then epsilon ETAU is basically 17%, and epsilon mu is very tightly constant. It's around less than 2.3%, and we can see that there is not that, I mean, there is no constant on the phi that which they call delta epsilon EMU, because all of them are basically allowed at 90% confidence level. Okay. So since we are considering two experiments here, T2K and NOVA, let me briefly describe about the experimental setup. So T2K is basically Tokai to Kamioka, is an experiment based in Japan, and this is baseline 295 kilometer with detector mass 22.5 kiloton, fiducial mass, water Cherenkov detector it uses with proton energy 30 GeV. And the data they have presented very last year at Neutrino 2020 with the on the basis of 1.97 into 10 to the 21 protons on target in the neutrino mode, and 1.63 times 10 to the 21 protons on target in the anti-neutrino mode. Similarly, for NOVA is a Fermi-Lab to Minnesota 810 kilometer baseline, is a liquid argon detector, and with detector mass 14 kiloton with proton energy 120 GeV. They have also they have presented the data based on the POT in the neutrino mode 1.6 times 10 to the 21, and then in the anti-neutrino mode it is 1.3 times 10 to the 21. Okay. So here I have shown the data set they have mentioned. So they have basically presented, T2K has presented 94 events in the neutrino mode, and then anti-neutrino mode 16 events, and then 14 events again neutrino mode for E-ring and E from pion decay. And in the nu-mu events in the survival channel, basically the 380 nu-mu events and 137 nu-mu bar events they have presented. And in case of NOVA, so they have basically reported the data set 82 events in the neutrino mode and 33 events in the anti-neutrino modes, and also 211 events in nu-mu and 105 nu-mu bar events. So this is what I have shown the result from the collaboration, and let me discuss what is the tension, which is basically the topic of this talk. So we can see from the upper left panel the delta chi-square as a function of delta Cp from the T2K collaboration, and we can see that the blue line is preferred over the yellow's line, which is, so that is the normal ordering is preferred over the inverted ordering. And we can clearly see that the CP phase they prefer is the maximal CP phase, which is maximal CP violation, that is they prefer minus 90 degree. Similarly, if we look at the right panel, we can see again from the NOVA collaboration that the blue line is actually preferred over the red line. That means they also prefer normal ordering on top of, over the inverted ordering. But the main difference between T2K and NOVA here is that the NOVA actually prefers towards the no CP violation. That means they actually prefers towards the pi value, CP phase with pi value. And in the lower panel, we have shown the in the theta 2 3 delta and 3, they have shown theta 2 3 delta and 3 2 square contour. And in that case, the most important point to note here that both of the experiment and the T2K and NOVA, they preferred also the upper octant. So both of them prefer normal ordering as well as the upper octant. So here what we have done, we have basically reanalyzed that data set T2K and NOVA. And we have shown in the plane of theta 2, 3 and delta CP, now the contour at 68% confidence level and 90% confidence level. So we can see from the left one, which is for the normal ordering, that the red one for T2K, red contour, and green one is for the NOVA, and we can clearly see from the star, the best fit points, that the T2K best fit points and the NOVA best fit points quite differ with each other at more than 90% confidence level. And this is exactly what the tension is in between these two experiments. And for inverted ordering, we can see that there is no such kind of discrepancy observed. Okay. So now we have done the combined analysis of both the T2K and NOVA data in the presence of in the standard 3 neutrino framework as well as in the NSI framework. So the upper panel corresponds to the standard 3 neutrino framework. The middle one corresponds to the NSI framework with epsilon E mu, and the below one is the NSI framework with epsilon E2. Now, a few points can be noted from here. So as we see, when you do the combined analysis for T2K and NOVA both, we can see that the normal ordering is not preferred. Here, inverted ordering is preferred over the normal ordering, as you see from the black solid line and the dashed solid line. And also, we can see that the octant, at least in the standard 3 neutrino scenario, can be discriminated from the lower octant and from the upper octant at certain confidence level, though the confidence level is not high. And now, in presence of NSI, the most interesting thing is that when you analyze in the framework of in the NSI framework with epsilon E mu, and we notice that now actually normal ordering is preferred over the inverted ordering, in opposite to the standard 3 neutrino sector, as can be seen from the magenta solid line and also the solid blue line. But another point is that, again, since the new physics is present here, as already have been shown earlier in different works, that because of this new physics scenario, the octant sensitivity goes down, as can be seen. The lower octant and the upper octant, even although it was little higher in standard 3 neutrino sector, but the sensitivity goes down in presence of NSI. Okay. So in this slide, we show the allowed region when we did the combined analysis of T2K and NOVA in presence of NSI. The upper panel shows the epsilon E mu versus delta CP allowed the plane, and for normal ordering and inverted ordering, and lower one corresponds to the epsilon E tau and delta CP. So we can see that the epsilon E mu, the red star, which is the best fit point, basically 0.15. So 15% is allowed for epsilon E mu, and epsilon E tau it is 27%, and for normal ordering, and for inverted ordering it is 0.02 and 0.15. Now, the most interesting point to observe here is that this red box, that the chi-square epsilon E mu normal ordering minus chi-square standard model inverted ordering is -2.63, whereas chi-square E tau normal ordering minus chi-square SM inverted ordering is -1.21. So that means when you did this fit in the NSI framework, we observed that the epsilon NSI with epsilon E mu actually preferred over the NSI with epsilon E tau. Although the confidence level is not that much high, but still epsilon E mu is preferred over the epsilon E tau. So in this slide, we have shown the epsilon E mu versus phi E mu contour plane, contour in the 68% and 90% confidence level for normal ordering and inverted ordering, and lower one corresponds to the epsilon E tau and phi E tau for normal ordering as well as in the inverted ordering. So we can see from this that this dashed line, the red star is the best fit point from the analysis, and the dashed line are from the ice cube limit 90% confidence level, and which is basic. I mean, we can see that this ice cube limit and the current limit given by this T2K NOVA combined analysis both are compatible with each other. So basically, the current T2K Nova data, which gives the NSI bound, actually allowed, and it is compatible with the IceCube dataset also. So now what we did, so here in the upper, we have shown theta 2 3 versus delta CP plane. Already I discussed earlier in the slide. So what we have done, we have taken the best fit point from the NSI framework, and we have taken the value of the epsilon E mu and phi E mu, what we got from that analysis, that those best fit points, and we took that and then we reanalyzed the data set again in the same plane theta 2 3 and delta CP. Now you can see that from the red contour as well as in the green contour, for in the left panel epsilon E mu and right panel epsilon E tau. Now you can see that both the contour actually overlap with each other now. The red contour and the green contour, and the red star and the green star are very close to each other, and that is, we can see that the tension between the T2K Nova, which were earlier at more than 90% confidence level, that actually tension is gone, and it's basically resolved if one consider epsilon NSI with epsilon E mu. Similarly, this is also the case with epsilon E tau. We can see that both pointed towards the same CP phases, which is around 1.5. The maximal CP violation, which is minus 90 degree in the presence of NSI also. So that means the tension which were earlier in the absence of NSI, that is, if one consider NSI with epsilon E mu and epsilon E tau, then this tension can be resolved. Okay. So as I already, just for the sake of completeness, so since let me show what happens for the inverter ordering. For inverter ordering,
22 minutes.
Okay,
Sorry.
just 1 minute. There was no discrepancy already. Similarly, the case also in presence of NSI. So now there might be some strong constant also from the neutral current NSI from the non-observation of charge lepton flavor violations. And but those possible that can be avoided if some consider the model with neutral light mediators, heavy mediators model arising from the radiative neutrino mass model, and also the mediators models with two mediators in the framework of dimension 8 operators. And if someone is interested in these topics, then they might see these references given here. So let me conclude. So we have investigated the impact of the NSI on the current data of T2K Nova. More than 90% confidence level disagreement between T2K and Nova in the measurement of a standard model CP phase, and that can be resolved if one consider the presence of NSI with epsilon E mu or epsilon A tau. And already we have shown that the epsilon E mu is slightly preferred over epsilon E tau. And normal ordering is also preferred over the inverter ordering if one considers the NSI. But we need to wait, of course, for more and more data, future data from T2K Nova and also from the T2HK dune and atmospheric current, and future data is expected to confirm the presence of NSI and will help resolving this ambiguity also. Now the point is that if you have such kind of NSI which is little big, large, and then in that case it has also been seen in the literature that might also impact the measurement of the mass ordering in the experiment like Dune. So in that case, we evidences the importance of the experiment Juno, which can determine the neutrino mass ordering unambiguously irrespective of the presence of NSI. And on top of that, it might be a physics beyond the standard model also. So and I conclude here. Thank you very much for your kind attention.
So thank you very much. Are there any questions? Or maybe people are hungry. I had one doubt about, you were just mentioning the dimension 8 operators with heavy new physics to give NSI. Is that consistent with lepton flavor violation effects at if you include loops?
I guess, although I'm not expert, but I guess so, because in this paper I was looking at, and they clearly actually mentioned in this paper that can be actually avoided, those constraints, if some uses. For example, there are few papers here. I guess they have mentioned in their paper at least. But
Okay,
I'm
yeah.
not sure that much details about the papers.
So, Sasha, if I can comment.
Yeah, yeah.
So you also asked me that question. So if you have to obey the SU2 symmetry, then your question is valid. You have very tight constraints from mu to E gamma and mu to triple E, and they will not allow you to take large NSIs in neutrino experiments. But most of the discussion are in the flavor independent, model independent framework. And if you want to really build a model, there is a possibility you can't do that at dimension 6 level. If you need to go dimension 8 and also maybe dimension 10 to really systematically cancel out everything, the anomalies, and construct a model. Okay, and there is that discussion is there. There was a paper by Babu and some other collaborators. They discussed about this, that you need to go to higher dimension and you can construct a model avoiding these bounds from charge lepton sector. But
So, yeah, okay, maybe we should continue this discussion offline. It will get a bit specialized. I have a paper with Martin Gorban doing the RGEs in SMEFT for those dimension 8 operators, and we think there's a problem from U to E. But
okay.
Let's discuss offline.
Okay.
I would like to thank all the speakers of this session for their very interesting talks, and thank the organizers. And I think that's the end of this session now, unless Alexander maybe has something to say.
Yeah, well, I also just would like to thank all the speakers of this closing neutrino plenary session of the conference, and also to Sasha Davidson for chairing this important event, the last day of the conference. And I would like to invite everybody to join again the conference at 1 p.m. sharp to continue the plenary sessions of the closing day of the 20th Lomonosov conference. Thank you, and see you very soon after a rather long break that happens, I think, for the first time at the conference. I'm sorry for this very difficult 7 working days of the conference. See you very soon. Thank you.
Thank you very much.
Alexander Ivanovich. It's Zakharov speaking. Do you hear me? Okay, it's Alexander.
Да, привет, Саш,
I would
привет.
like to ask first speaker to share screen just to save 1-2 minutes, because 3 minutes to.
Yeah. You're welcome.
Okay,
Yeah.
Giovanni, fine. Full screen. Could you show full screen mode, Giovanni? No, it's not still full screen. It's not full screen. It's visible, but not full screen. Okay, good. And next slide. Okay, now it's not full screen.
I'll try again.
Try again.
So, but we have at least 2 minutes.
Okay, but it's not full screen.
Professor Zakharov. Yeah.
Can you see it now?
No, not full screen, not full screen.
Oh,
it's not full
sorry.
screen. Probably you pressed several times. That is
Le-
maybe a problem. You press this button several times in this case.
This must be a feature of Zoom because I am seeing it full screen.
Okay, but we're not. But it's in principle, of course, it's possible to use this option, but it would be better to use full screen option.
So
Okay,
since we-
great. Next slide. Could you change
okay,
this?
so
Now it's
we-
okay, but next slide, could you?
Sure.
Okay, great.
Good.
Everything is fine.
Okay.
Okay, we have still 1 minute.
Yeah, no problem.
Okay. Okay. Okay, it's time to start. Good afternoon, everyone. Buongiorno tutti, because I recognize that more than 90% of speakers at this session have Italian names. It's very pleasant. And first speaker is Giovanni Lasurde. It's go ahead, 20 minutes for talk and 5 minutes for questions and discussion according to suggestion of organizing committee. Please go ahead.
So thanks a lot for the invitation to this a very prestigious and traditional conference. I'm honored about this. And I will make a quick review of the status of the field of gravitational waves of observation. Well, it's just a few years since we as a gravitational wave community, referring to the LIGO and Virgo detectors, have in some way shaken the world of the physics with two major discoveries, two breakthrough discoveries, which have really started a new era in observation of the universe. First one was in September 15, first ever observation of direct observation of gravitational waves. In that case, it was the coalescence of two black holes of 29 and 36 solar masses. And then 2 years later, the coalescence of two neutron stars accurately localized thanks to the presence of three detectors, which was followed by the identification of the optical counterpart and its follow-up, which led to the first observation of a kilonova with a number of major implications for physics and astrophysics. Now, since then, a lot has happened. This chart, which is showing the events of coalescing binaries as a function of the two masses, the two component masses, is now very well populated by tens of events, mostly binary black holes, but also binary neutron stars, neutron star black holes, and more exotic events. This has been possible thanks to the existence of a network of 3 kilometer scale interferometers, 2 LIGOs in the US and 1 European interferometer in Italy, Virgo, which have performed 3 observing runs so far. The first run between September 2015 and January 2016 was performed just by the 2 LIGOs, since Virgo was still in the upgrading phase. Second run, and it detected the first few events. The second run between November 2016 and August 2017 was in the final weeks. Also Virgo joined, and that was a magic August with the detection of the coalescing neutron star. And then we have the third observing run, called O3, 1 year long, divided in 2 chunks of 6 months, O3A and O3B. Actually, the second chunk was stopped one month earlier than expected due to the COVID pandemic hitting heavily. The important point is also that in the second part of the run, the network became a 4-detector network with the addition of the Japanese detector Kagura. This has been a very, very important run because there has been a change of regime. We have passed this, from a situation of few detection to a routine detection, about 1 per week. This has been possible for 3 main reasons. First, the improved sensitivity of the detectors. Second, the fact that these are the 3 detectors ensures better time coverage and sky coverage. And third, that the network duty cycle was very high. We approached about 50% of time with the triple coincidence, 36% with double coincidence, and only 3% of time with no detector up. So it's a very important achievement, since it testifies that these are now very, very reliable machines. So there has been a very significant improvement of the detection rate, which has allowed population studies for black holes, and also to detect more distant sources with a redshift as high as 0.8 for the moment. Moreover, during this run, we have published 6 exceptional events. I will tell more in the following. So recently we have published the so-called GWT Gravitational Wave Transit Catalog 2, which refers to the first part of the run, so to the first 6 months, with 39 candidates reported there. The total mass, the mass of the final black holes range between 14 and 150 solar masses. So there is a very wide span in the mass range. And we also report significant observation on spins. Spins are important as key signature to discriminate the formation mechanism of the black hole binaries. They can tell if the binary is formed by star formation or by other process like formation of binaries by random encounter in a dense environment. And there are some events with clear indication of a net positive spin. Another significant paper related to this data is the so-called population paper, which starts shaping our understanding of population. We can start using the data to discuss what is the mass distribution of the black hole population. But clearly, we look forward to the next runs, to a regime where we will be soon detecting one event per day. So we will have 100 of accumulated events, and we will start really to make population studies. Another important aspect of this kind of observation is the testing, the so-called testing general relativity. With the GW observation, we really are testing a general relativity in strong field and dynamical regime. So we can access a region of the parameters inaccessible to other observations. And we can pursue several tests searching for violation of general relativities. And unfortunately, even with better sensitivity so far, we don't see evidence of new physics in the gravity area. So general relativity is still passing all tests. We have also a new upper limit on the mass of graviton, which is lower than 1.7 times 10 to the minus 23 electron volt. There has been a specific talk by Gregorio Carullo 2 days ago. So if we look back, we notice that in just 5 years, we have passed from first discovery to population studies. And we can say that it's just the beginning. A few words on the exceptional events that we have published on the O3 data. GW 190412. This was the first observation of a binary black hole with an unequal mass ratio, a mass ratio of about Q 0.3. Then, for 190814, this was the most asymmetric mass ratio ever observed, with masses of the primary components of 2.6 and 23 solar masses, so a mass ratio of 0.1. And another significant aspect of this observation is that the 2.6 solar mass object lies in the so-called lower mass gap, where we don't expect to observe any object. So it is either the lightest black hole or the heaviest neutron star ever observed. Still going on with surprises, we have observed 190425. This is a binary neutron star merger with total mass of 3.4 solar masses, which is significantly larger than any other known binary neutron star system. 190521. This is a really exceptional event because this is the coalescence of two black holes, very heavy black holes, 66 and 85 solar masses, with a final mass of 150 solar masses. So this is the first observation of a so-called intermediate mass black hole with mass heavier than 100 solar masses. And this is the first observation of a black hole in the so-called pair instability upper mass gap. We don't expect to observe black holes as heavy as 80 solar masses because we can't explain their origin through star formation. So we must hypothesize a more exotic way of forming these black holes. And then the last published paper reports about two events, 200105 and 200115, which are basically the first unambiguous detections of a neutron star black holes. Now, a few words about the open data policies that we are pursuing. Since the beginning, every time we publish a paper on a special event, we also release 1 hour of data around the event so that everybody can check the data. And after 18 months, in chunks of 6 months, we release the bulk data of the entire run chunk. So we have recently, we have a few months ago released the data for the O3A, and soon in fall we will release the second part of the run of the A3 run. And we have this portal called the Gravitational Wave Open Science Center, where everybody can download the available data together with the relevant information on tools for analysis. Now, what's going to happen in the near future? As I said, CAGRA has joined the network in O3b, so we are already a 4-detector networks with a perspective to become a 5-detector network with the addition of LIGO India in a few years from now. Moreover, LIGO and Virgo are being further upgraded with special packages called A+ in the case of LIGO and Advanced Virgo Plus in the case of Virgo. And I'm going to tell you more about this. So Advanced Virgo Plus is a phased plan to increase Virgo sensitivity, which has been now funded. In the phase 1, the aim is basically to double the sensitivity. And in phase 2, we will go further in sensitivity improvement. For phase 1, there is a number of upgrades, a large number of upgrades being pursued. The main ones being the implementation of signal recycling, which was missing so far, and the implementation of quantum noise reduction through frequency-dependent squeezing. For the status is that the installation of the main interferometer has been completed in December. The installation of quantum noise reduction hardware has been completed in April, and now we are commissioning the interferometer. The main interferometer is locked, and the filter cavity is aligned and locked, and so we will soon start the noise hunting phase in view of the next one. For phase 2, the main objective is reducing the thermal noise limit, which is the main limit to the sensitivity in the mid-frequency range. This is done basically by enlarging, by using larger mirrors at the end of the 3 kilometers cavities. So we pass from 40 to 100 kilogram mirrors with diameter of 55 centimeters. This is an extremely ambitious piece of technologies which has been realized, and which allows to enlarge the beam spot at the end of the cavity, which then reduces thermal noise. Then to these, we also plan to add the implementation of better coatings, which are the main source of mechanical dissipation. And so in the end, this will give a remarkable improvement in sensitivity. A parallel program exists at LIGO called A+, again, divided into phases, one to be implemented before the next run, and second to be implemented before between O4 and O5, like Virgo. And in fact, the bottom line, what I was saying before, is that we plan the observing and shutdown period together, since we are a network. So at the moment, the next run is expected to start not earlier than August 2022. We will soon issue a new update, hopefully giving a definite date for the start of this run. Whereas the O5 run, then at the end of the run, which will last about a year, there will be another period of upgrade, and then the run called O5. Now, a few words about the long term. I see I still have about 3 minutes. So when Galileo first pointed its handmade, handcrafted telescope to Saturn, a few months after the reported observation on Jupiter, this is what he saw. Then a few years later, by improving his telescope, he almost was able to identify the Saturn rings. It didn't work the last step, but he went very close. And basically, this is where we are today with gravitational wave detectors. In 400 years of telescope technology development, we came to get this image of Saturn through the Hubble Space Telescope, where we are even able to observe polar aurorae, so interaction of cosmic rays with Saturn atmosphere. And this is where we want to go. So basically, we know we have the right instrument. We need to make it better and better without taking 4 centuries to get there. So we have already solid plans for so-called 3rd generation detectors. And we are trying to coordinate the effort, to have a coherent effort for the development of 3rd generation through the Gravitational Waving International Committee, which has set up a subcommittee which has recently issued very important reports to address this coordination effort. You can download them from this site, they're public. The first project I want to mention is the European one, Einstein Telescope, which has it's a project for a triangular underground infrastructure hosting 6 interferometer, which it's a very ambitious project, which has recently passed a very important milestones, the approval in the ESFRI roadmap. ESFRI is the European plan for research infrastructure, European strategy for research infrastructure. So accessing to the ESFRI roadmap is a very important step towards the approval of the project. And then there is Cosmic Explorer in the US. This is the plan for 2L above ground, 2L shaped detectors above ground of 40 and 20 kilometers. And the Cosmic Explorer Horizon study has just been issued and is available at this site. And with these 2 projects, we have a very ambitious plan. So far, we could observe sources at redshift 0.8. We expect that this can be extended to redshift 2 with the upgrades we are implementing. But with the 3G detector, we really aim to do cosmology and look far in the universe as far as redshift of the order of 100. And that's all I wanted to say. So I thank you for your attention, and I'm available for your questions.
Thank you very much for excellent talk. You presented really like factory of discoveries. So I do not see raised hands, but I do not see. But in this case, I will ask. Because I would like to ask a question first. In this case. So you showed a lot of data about masses for binary black holes, etc. But initially, before discoveries of first binary black holes in LIGO and Virgo searches, people do not expect that it will be so heavy sources of gravitational waves. What about consistency? Because I would like to ask a question first. No, wait. Initially, before discovery of first binary black holes. Wait. Maxim, wait. It's first you have to ask. First you have to ask and after that you interrupted me. Sorry. But question is, are these observational data consistent with current understanding of stellar evolution in binary system, or there are some puzzling events?
Well, they are partly consistent and partly not consistent. There have been a lot of surprises. Astrophysicists did not expect to observe masses in the mass gap, especially in the upper mass gap. This is something to be explained that cannot be explained by current stellar evolution model. So there must be other mechanisms which give an explanation for such heavy black holes. There are already models for that. For instance, hierarchical formation of repeating coalescence of black holes, which then accrete to larger masses. But how probable these mechanisms are is still difficult to say. So I think that one very important aspect of this data is that they are giving food for brain to the community of astrophysicists, and we who are eagerly waiting for new data to understand how frequent these exceptional masses are. And so let's wait and see. I'm sure that there will be an extraordinary production of theoretical models in the next months and years to explain this data.
Okay, thank you very much. But also about mass gap. According to my understanding, mass gap was surprise for theorists in astronomy. It was early. It was like observational fact, not the theoretical one, because it's naturally it has to be filled. But now you filled this gap. Yeah. Thank you very much. Next question and last question, Maxim Dvornikov, if you want to ask question.
Yes, I would like to ask you, suppose that two supermassive black holes merge, what shall you observe?
Nothing, because supermassive black holes merging produce gravitational waves in a frequency range that we cannot access with ground-based experiment. So we have to wait for LISA in order to access this kind of sources.
Okay, thank you.
I do not see other questions. Raised hand. Thank you very much.
Thank you, and thanks again for the invitation.
Thank you, thank you, thank you. And next speaker is Dmitry.
Yes, I'm here. I'm here. Just
okay. Please share your screen.
Yes, share screens. Even one.
Okay, great. Full screen, please.
Wait.
You're still not full screen. No.
Sorry. No. Is it?
No, it's better, but still not full screen.
Yeah. Wait a moment. Just where is it? Full screen. This one. Is it better?
Yes, it's fine. It's fine. Now it's fine. Okay, go ahead.
Okay. So many thanks to organizers for inviting me to give this talk. So the standard cosmological model is described by several parameters, and usually it can be illustrated in this with the help of Friedmann equation. Okay, so we introduce in the scale factor A, and A dot over A is a Hubble parameter which describes the expansion rate of the universe. Now it is governed by the Friedmann equation, and there are several parameters entering the Friedmann equation. If we rewrite it in terms of present Hubble parameter, these parameters describe the relative contribution of various entities we have in our universe, various species we have at present. their relative contributions, okay, and actually only one of them, which is omega gamma, the relative contribution of relic photons, which we measured directly, okay, just observing the nice shape of photon spectra, okay. All the rest are obtained by performing some, well, sometimes very sophisticated analysis of astronomical data. However, from this study, we observed several quantities which, for example, we so far cannot reach even in particle physics. For example, we know that the sum of the mass of neutrinos should be smaller than 0.2 electron volt, and this limit is far away from the sensitivity of the present experiments on direct measurement of neutrino mass. We know that there should be, roughly speaking, 3 neutrinos, okay, not much more, okay, and their contribution together with the contribution of photons is negligible if we analyze, if you look at the present universe. The main ingredients here is the baryons, which about 5%, and this quantity is consistent with observation of the baryon content from analysis of abundance of chemical composition, which are formed in the very early universe at the moment of primordial nuclear synthesis. And then about 27% of dark matter, and the rest is a cosmological constant. So we live in the very flat space. Okay, so the Hubble parameter, at present Hubble parameter, can be deduced from analysis of the cosmological data. We observe large-scale structure, galaxies and galaxy clusters, and their origin is the primordial matter perturbations, which is adiabatic, Gaussian, and can be described. It can be described by the amplitude and the spectral index, which actually very close to unity, so it's mostly flat. Okay, we don't observe tensor perturbations, which are really gravitational waves, and there is one more parameter which actually we could calculate it given the knowledge of particle physics and astronomy. However, we failed, and we extracted from the cosmological data. This is the redshift of reionization, where the first stars have been formed. Well, looking at this model, taking the general relativity and particle physics, we can trace back the history of the universe back to the moment where the temperature of the primordial plasma was as high as about 2-3 MeV, and everything more or less is consistent with this nice picture. And this 2 or 3 MeV corresponds to the production of the primordial chemical light elements, and this is the earliest observable we have so far. Okay. Now, so this is the standard so-called standard cosmology. We know the standard cosmology from present down to this primordial nuclear synthesis. Everything is in agreement with various independent observations. Okay. Now, of course, we don't know many things. Okay. And for example, while the cosmologist says the particle physics that we need some new ingredients, we have no idea about the dark energy. We don't see what is the dark matter. We don't understand the baryon asymmetry. Cosmology only says when we should produce this type of new ingredients in the early universe, but not the scale, but not the energy scale of new physics. And in particle physics, we need an energy scale, not the time scale. Okay, so this is the difference between. So it's a clear indication, but not the indication of the energy scale, where we should expect some new physics. Okay, truly speaking, so from this anyway, we conclude that we need the new physics. And if we discuss the baryon asymmetry of the universe, it obviously requires some violation of baryon number, and this implies a new physics. Okay, However, sometimes people say, well, it could be just the initial conditions and that's it. Okay, if you don't like to to dwell on these initial conditions, then it's the baryon asymmetry of the universe is 100% indication that you need new physics, new particle physics. Okay, because it's baryon number. Now, usually people say that the dark matter is also the indication that we need new particle physics. Okay, well, strictly speaking, it's not the case, because all observations we have so far in cosmology and astrophysics, which we interpret as the dark matter, is indications that we have a lack of gravitational potentials at different time scales and different spatial scales. Okay. Well, people try to modify gravity, obviously, but fail so far. And if you just add some stable massive particles in the early universe with a particular amount, then everything will be perfectly explained just with general relativity and this new ingredient. So, moreover, in particle physics, we have many well-motivated extensions of the standard model of particle physics, which predicts the existence of stable particles, stable massive particles, which can be employed to play the role of dark matter. Most probably, the dark matter also indications that we need some new particle physics. Okay. Now, well, there are many problems in this setup. Okay, we don't know the origins of dark matter and matter-antimatter symmetry. We don't know what is the dark energy, whether it's related to particle physics, to gravity, or something else. Well, we observe matter perturbations, which origin we also don't know. It can be related and nicely related to inflation, but it's not 100% guaranteed. We have other things. We have coincidence, okay, in numbers which we observe in this cosmological setup. For example, well, the relative amount of dark matter and baryon asymmetry are more or less the same. But when we discuss the particular, dark matter candidates or realization of baryogenesis or leptogenesis, they're not related, and so this looks like a coincidence. And the same story about the coincidence of matter and dark energy. It's also, usually it's not. They just two different numbers. We have our other, close to each other number, like baryon asymmetry, the relative contribution of the baryons to baryon asymmetry of the universe, okay, which characterized usually by the ratio of the baryons to photons and the square root of matter perturbations, for example. There are some coincidences we have, we observe looking at the parameters of the cosmology, like the temperature of neutron decoupling and the ratio of the neutron and proton mass, which are particle physics quantity, okay? And because they are of the same order, we have such, rich zoo of primordial chemical elements. Well, there are some relations which happens just because of a particular values of the relative contributions of the dark energy and dark matter, like the very close relation between the age of the universe and the inverse Hubble parameter, present Hubble parameter, which usually is a complicated function of the cosmological parameters. Okay, we don't know whether this coincidence indicates some, hints on the origin, for example, of dark matter and dark energy, on the relation between dark matter and baryon asymmetry of the universe production. Maybe it's just a coincidence, maybe they're not. And on top of that, we have the anomalies. Okay, maybe the long-standing anomalies is our fail to predict the lithium abundance at the rate we observe it in astrophysics. Then we have some funny things with multiple statistics in cosmic microwave background radiation. Well, also we know that, and it was a paper by Planck. It's where if you try to extract the cosmological data looking at the low multiples of cosmic microwave background anisotropy and the high multiples, we observe significantly different cosmological parameters. There are some discrepancies in measuring the lensing and the Sinaev-Zeldovich clusters in the same Planck. On top of that, we have problems with measurement of or extraction of the Hubble parameters from the direct so-called astrophysical observations and cosmological observations, early universe measurement and late universe measurements, problems with understanding of the evolution of the perturbations at the late stage, so-called sigma 8, which is the amplitude of the matter perturbations at the scale of 8 megaparsec. And well, all these anomalies it's like in particle physics. It can be due to statistics. It can be due to some systematics, and then astrophysics and cosmology, systematics. A lot of very suspicious things. And historically, even in cosmology, well, we know several cases where some values were changed by several sigmas, just because, well, of some systematic errors which people didn't realize previously. Anyway, but maybe these anomalies give again some hint to the origin or to the coincidence problems. And for example, the problems with late-time measurements of Hubble parameter at sigma 8, maybe it's indications that we start to see some hints that it's not the cosmological constant, but some dark energy with very specific properties. Maybe not, but still these problems we have. I cannot describe all of them, of course, but can run through several of them and try to explain possible relations between them and why they are important. Well, the oldest one is the lithium problem. Okay, we have enormous progress in nuclear physics trying to solve this problem, and we can predict very nicely the abundance of light chemical elements from the standard cosmological models. However, we failed to explain this number. So all the helium and deuterium are very nicely consistent both with observation and with the Planck measurements, but not the lithium. Okay, well, again, from time to time, people make new observations and reanalyze data, saying that, well, deuterium is somewhat deviate from the predictions, or helium-4 deviate from the predictions, but it's just, it's not the anomalies, it's just new data which usually can, scatter around the previous one. However, in case of lithium, we have the problem for decades, okay? And well, maybe it's resolved just by, maybe we'll lack the understanding of star formation. Maybe we have some serious problems with systematics, but maybe there is some new resonance in nuclear physics, like we have the Hoyle resonance, which helps to produce the carbon in the first stars. Okay, so I mean it's kind of anomaly we have, and it may indicate something. However, people try to introduce some new physics to solve this problem and failed. Okay, so it's quite remarkable. Now, well, there are many improvements on both sides when people try to understand these many issues. In some cases, we have the progress, and some cases not. Okay, but actually, we obtained more anomalies for the last years than get new insights. Maybe it's because we are approaching the accuracy at the level of 1% in measuring the cosmological parameters, and faced a lot of anomalies, and maybe it's indications that we underestimate our systematics. Anyway, just to illustrate, it's important. For example, look well, it's a limit on the sum of neutrino mass. Okay, it's parameters. It's what cosmology can say about particle physics. And these results some 12 years ago. It's limit on the sum of neutrino mass at the level of 0.2 electron volt. And the same limit we have at present, in spite of this 12 years. Okay, the similar story with sterile neutrinos. Okay, this is a hot topic at present, and it was hot topic 10 years ago. And at that time, people said, well, maybe at some level we can have some, one more sterile neutrinos. But to explain the anomalies we have in neutrino oscillation experiments, we need at least two, okay, maybe more. They're not consistent with each other. And if you again consider the set of cosmological data, it's also not consistent even with one sterile neutrino. Okay. However, presently we have anomalies, and we can solve these anomalies like measurement in Hubble or measurement in sigma 8. And in this, we just introducing one, more or less standard, well, not standard, well, not normal or typical parameter, which is beyond the standard cosmological model, like mass of neutrinos, like additional sterile neutrino, like maybe axion or something like that, or maybe evolution of the parameters of the equation of state of dark energy. With these simple extensions of the standard cosmological model, we cannot solve these anomalies. Okay, so people started to use a very complicated model with several parameters, and in this way you can also play with several parameters, trying to accommodate, for example, the sterile neutrinos. Okay, and this is just illustration. For example, this is a BBN, and we can introduce 4 sterile neutrinos, but also can introduce the lepton asymmetry. We don't know whether the neutrino sector, relic neutrino sector, is symmetric or asymmetric with respect to lepton asymmetry. And so if we have 2 new parameters, then we can fit to observation of the helium-4. Now, does it help? Sometimes people argue that it can help. This is the measurement of, this is the extraction of the Hubble parameter, and we introduce the lepton asymmetry, and the highest lepton asymmetry corresponds to the blue here, and you see you can have a larger value of the Hubble parameter if you play with the blue line. Here is another illustration. Okay. For example, presently neutrino experiments try to constrain the some anomalous interactions of neutrino in neutrino sector. Here is a model where we have standard neutrinos and some interaction between these neutrinos, a pure penological model with light scalar, okay, Yukawa type of interaction. And here is a contribution. Here is an attempt to have to increase the limit on the sum of neutrino mass to 3 electron volt. Okay, so here is a 3 electron volt, and we discuss here the cosmic microwave background radiation, and here is the residue between this between the data and the prediction of this. Of these models, where we have long range interactions between active neutrinos. Okay, and you see if corresponding parameters of the model becomes large, the ratio of the coupling and mass to the mass of the scalar. So it's a light scalar, okay, mostly. Then this black line is perfectly in agreement with observation, okay, and so you can have 3 electron volt as the mass of active neutrinos if it interacts with this new ingredient, okay. And here is the illustration. If you introduce something more, then you see even if you feed to structures and to the Planck data, you even allow to have well, actually a lower sigma 8. However, lower sigma 8 implies also lower Hubble, and it's quite typical with this simple and this is a simple extension.
Excuse me, Dima, you spoke 20 minutes at the moment.
Okay, so I'm finishing. Okay, so it's just to illustrate that in this case, it's typical to explain some anomaly, but not another one, to make another worse. Okay, and so if you introduce here the information about the structure, baryon acoustic oscillations here, you see that you are back to the CMB predictions. However, you are very, you are not sensitive to the sum of neutrino mass. You can have it from 0.1 to 3 electron volt easily. Okay, and it's just illustrations that you can accommodate many things like this. Since since I'm I'm not able to cover all these things, just let me say that, well, to finish, just let me say, but however, we expect some progress which can give some some quantitative results in some cases. For example, for the dark matter, people discuss here many experiments and measurements, especially related to the WIMPs. Okay, and there are serious limits. It's just 5 years ago we observed present results during this conference, and also the estimates of the future experiments, which they almost reach the neutrino floor. But I mean, for example, for the indirect limits, measurement of the possible products of annihilation of dark matter in the galaxy, we have we already excluded the case where the dark matter, if it's really weakly interacting, okay, case below 10 GeV, and if you consider the new generation experiments, now we have a Cherenkov telescope array, then they promise to exclude the dark matter with mass below 10 TeV, which is very close to the unitarity bound. And I would say that this dark matter is weakly interacting particles should be either observed or excluded with this new generation experiments. Given the lack of time, let me finish here, just saying that, well, similar thing we have for sterile neutrinos, for example. We also have very small region allowed, and with new generation experiments like Erosite and RTXS, we can fully explore the rest of the parameter space. Mind, however, that some of these regions are related to the observations, okay? And for example, this BBN limit implies that we understand BBN perfectly, and we still have the problem with the lithium. So maybe this region is not fixed very well. Anyway, just to finish, let me say that maybe at the age of some new fundamental discovery in cosmology, this anomaly may indicate that we now start to probe the dark energy. The dark matter, in case of its weakly interacting massive particles, should be, I would expect, discovered in the next 10 years. And what is almost guaranteed, the measurement of the sum of neutrino mass with a new generation of experiments working on the observation of large-scale structure and the theoretical progress when people started to apply the particle particle physics instruments like perturbations, perturbation theory, to calculate the structure formation at the the perturbations becomes enters the nonlinear regime. So thank you for your attention.
Okay, thank you very much for excellent talk. We have time for only one very short question and short answer. Please, Ibrahim Mirza.
Yeah, thank you. Would you like to say something on possible source of cosmic neutrino background?
Okay, short answer, please.
You mean cosmic neutrino background, this relic neutrino background, or what is observed now by IceCube, for example?
Relic neutrinos?
Or I mean high energy neutrinos like IceCube observe, or these relic neutrinos which we expect from the neutrino decoupling in the primordial plasma. Which type of neutrinos, which type of cosmic neutrinos?
I apologize. Now timing is very bad. We have -3 minutes. Please continue your conversations privately. I apologize for inconvenience, but there is no time, unfortunately. Next speaker is Giorgio Arcadi.
Hello.
Okay.
Yes. Can I share the screen?
Yes. Go ahead, please. Full screen, please. Okay, it's great. Okay, go ahead.
So, first of all, I would like to thank the organizers for giving me the chance of giving this review talk on leptogenesis. And in a similar fashion on some other colleagues, I would like first of all to pinpoint that given the broadness of the topic, my talk will just cover some selected topics, and this selection will also not be immune from personal bias. So I apologize for this, and more importantly, I apologize if I'm going to miss some to refer to some important works. So, in a nutshell, so here the problem that we are dealing is the following: we are asking how what I'm calling the visible and ordinary matter content of the universe is originated. And most of the community agrees on the fact that the most plausible solution to this puzzle is the existence of a dynamical mechanism which created during the early stages of the evolution of the universe an asymmetry between matter and antimatter, starting from a symmetric situation. And a necessary requirement to achieve this task is the existence of three conditions. That is, the existence of processes capable of violating the baryonic and leptonic number, the existence of sources of a violation of CP, and also the processes responsible for this generation of the symmetry should have occurred outside thermal equilibrium. Among also these three necessary requirements, however, still open a wide range of possibilities to achieve the creation of this asymmetry. And another important message to bear in mind is that the standard model, while still well capable of fulfilling these three necessary conditions, nevertheless is not capable of accounting, say, the correct value as measured by Planck of this matter-antimatter asymmetry. So the solution of the baryogenesis puzzle also enter in the broader context of the searches and the building of theories beyond the standard model. And between the various possibilities, the one that I will cover in my talk is the so-called leptogenesis, which again represent still a large variety of possibility, which have the common feature that the creation of the baryonic asymmetry starts actually with a creation of an asymmetry in the lepton number, which afterwards is converted by the non-perturbative B-L conserving Sphaleron processes. This leptonic asymmetry is then converted by them into a baryonic asymmetry. On general grounds, to compute this baryon asymmetry, one has to solve a system of Boltzmann equation whose detail will actually depend on the specific model in which the leptogenesis mechanism will be embedded. So for this reason, I'm not giving any detail in my talk. I'm just to bear in mind that on general grounds, this system of Boltzmann equation will contain an equation for the source of the baryonic asymmetry, like for example, the out of equilibrium decay of a new exotic particle, and an equation which actually describes the evolution in time of the leptonic or of the leptonic asymmetry, or even better, of an asymmetry in the B-L number. Again, from an historical perspective, one of the reasons of why leptogenesis theories are among the most popular considered options in the context of baryogenesis theories is the fact that one can relate the solution of the baryon asymmetry puzzle to another relevant puzzle, which is the origin of neutrino masses. And while this already being something interesting on its own, this also opened the tempting possibility of testing leptogenesis through the various experimental observables which are looked for in order to test the possible models for the generation of the neutrino masses. Nevertheless, I mean, this relation in practice is not super trivial to establish, because at the moment we have not a clear hint on which will be the possible new physics scale responsible for a viable leptogenesis mechanism. Indeed, as you may see from this slide, we can achieve a viable leptogenesis mechanism within a rather broad range of new physics scale, which range from around the sub-GeV scale up to the grand unification scale, or even above. And as you may see, to different values of this new physics scale, we can associate different main, say, leptogenesis mechanisms. So, as you see from this slide, on the lowest side, we have the so-called leptogenesis from oscillation. I will describe this mechanism in more details in the next slides. Then we going higher in the new physics scale, we reach the so-called resonant leptogenesis, up to arrive at the highest scale when we met the thermal leptogenesis, which also from the historical perspective was the first leptogenesis mechanism proposed in the literature. And as we move in our new physics scale, also we have different experimental probes that we can consider. Of course, in some sense, the lowest energy scales are most probably the more interesting, because in principle we can directly test this new physics scale, for example, through the searches of new particles, which will be accessible at present and the next future experiments, while as the new physics scale increase, we will need, on the contrary, to rely on some more indirect probes of the new physics responsible for the leptogenesis. And as said, since I have to do a selection of topics, what I will do in the remaining of my presentation was to focus on some specific leptogenesis examples, but all of them will have the common feature that the new physics responsible for the leptogenesis is represented by new heavy neutrinos, which are typically called right-handed or sterile neutrinos, and these new neutrinos will be also involved through the seesaw mechanism into the generation of the mass of the standard model neutrinos. So within this context, we can make a first distinction on the possible scenario that we are going to deal with, and this selection will depend on the mass of these new neutrinos. Indeed, if we consider, say, heavy neutrinos, by this I mean with masses above the 100 GeV scale, the leptogenesis, also in different realization, will go through the out of equilibrium decay of these new states. On the contrary, for lower masses of the right-handed neutrinos, the most relevant and most interesting contribution to the leptogenesis will come from oscillation process. So we will be in the context of leptogenesis via oscillation of red-ended neutrinos. And exactly at this intermediate scale, we can have also a sizable contribution from lepton number evaluating decays of the standard model Higgs bosons. Before going ahead, just a relevant thing, take this value of 100 GeV as a sort of tentative value. Do not really interpret it as a sharp cutoff, even because I will show in 1 minute that in reality there is a continuous transition between these two leptogenesis regimes that I've depicted here. So let's start with the first scenario, which is the one which is active at the lowest energy scales that up to now we have considered. And this leptogenesis via oscillation is also called ARS leptogenesis, from the names of the author who have first proposed this mechanism. The general feature of this mechanism is represented in these slides. So you see, these slides represent a sort of a self-sustained circle, because what happens is the following. First of all, we have new red-ended neutrinos, which are thermally produced in the primordial plasma and feature CP violating oscillations. Since these red-ended neutrinos have via Yukawa couplings a connection with the sector of standard model leptons, this CP asymmetry created in the new neutrino sector is converted, is transmitted to the sector of the standard model sector that from now on I will call active sector. Then, and this is one of the most relevant features of this mechanism, this asymmetry, which is passed to the standard model sector, act as a sort of background potential, which further enhance the asymmetry generation in the sector of this new red-ended neutrino. So for this reason, I represented this mechanism, as I told before, as a sort of self-sustained circle. Then, the other relevant point is that part of the asymmetry which is transmitted into the standard model sector is then converted by the sphaneron into a baryon asymmetry, which is the one we are interested on. And one, again, of the most relevant feature of this kind of mechanism is that if we define a unified lepton number which describes both the standard model sector and the new neutrino sector, what we are going to find is that this total lepton number is actually conserved in the ARS leptogenesis, at least in the original formulation. And as said before, I mean, this mechanism is typically active for relatively light neutrinos with masses not exceeding the few tens of GeV. And this, from the observational perspective, this is one of the most interesting scenario, as I'm showing in this slide, because there are many currently running and planned experiments which are really aimed to look for new red-ended neutrinos with the mass not exceeding by far the scale of a few hundred GeV. So an eventual detection, or on the contrary, the lack of a signal, in principle could be used also to test this leptogenesis mechanism, which has the requirement of the existence of these light neutrinos. Indeed, there are many studies performed in the field. Here is the first example. And again, here I'm using this slide also to pinpoint the fact that the minimal realization of this leptogenesis mechanism requires the existence of two new red-ended neutrinos, with the additional requirement that they should be almost mass degenerate. And the reason is that this mass degeneracy works as sort of resonant enhancement of the rate of the oscillations. So here you see some result. Here you see the most important is maybe the plot on the upper left part of this slide, in which you see we can summarize our result, you have seen some plots has been also shown in the previous presentation. You can summarize the result in a bidimensional plane, mass of these new retained neutrinos, and in the y-axis there is a matrix U squared, which measures the mixing or the coupling of these new retained neutrinos with the standard model sector. And here I pinpoint that these sensitivity plots of the various experiments are casted in the same bidimensional plane, so one can think at a certain point to overlap the two kind of plots. But for the moment, I would like just to pinpoint here the region in this bidimensional plane which correspond to a variable leptogenesis within this scenario. And here I'm just showing a first example of this sort of overlap. Although one can realize this IRS leptogenesis in a very simple minimal model in which one just considers just a low energy type 1 seesaw. Probably the most interesting model in which apply this kind of scenario are models characterized by neutrino mass generation mechanism, like the inverse seesaw or the linear seesaw. And the reason is that this kind of model are characterized by feature which is just a tiny amount of violation of the lepton number. And this is again also a feature which can easily accommodated in this neutrino oscillation leptogenesis mechanism. And as you may see, this kind of plot show as points the one giving a variable value of the electronic asymmetry according to this mechanism. And here you see instead as colored dashed lines, as colored solid lines, the expected sensitivity of some experiments looking for new retained neutrinos. And as you may see, the variable model points, most of them at least, lie exactly within the sensitivity range of these experiments. I think I'm around 2 or 3 minutes left. This is correct?
Yes, exactly. Okay. Even four.
Okay, this I can skip. So here I would like just to pinpoint that I said that the minimal realization requires 2 almost mass degenerate neutrinos. Nevertheless, in principle, we can further enlarge the variable region of parameter space, as shown, for example, in this plot, if one consider the case in which 3 new retained neutrinos via the oscillation creates the leptonic asymmetry. I said, first of all, in this scenario, one can enlarge the variable parameter space in this bidimensional plot mass mixing matrix. And most importantly, if one has 3 retained neutrinos, it's possible also to release the requirement of mass degeneracy between these new neutrinos. So I have to rush a little bit. So this is what I would like to say about this oscillation mechanism. Now, if we increase the mass scale of these new retained neutrinos, and this is also discussed in detail in this work by Klarich and collaborators, one can have a continuous transition towards another leptogenesis mechanism, which is the so-called resonant leptogenesis. Here we have, again, a new retained neutrinos, but this time the asymmetry is generated via the out of equilibrium CP violating decay of these new neutrinos. But to have a viable leptogenesis at still not super heavy masses, we still need that these 2 neutrinos should be almost degenerate in mass, because the mass degeneracy again will result into an enhancement of the CP asymmetry. Just a snapshot in this scenario, here resonant leptogenesis is typically considered and particularly interested in the case of TV scale retained neutrinos, and this is particularly interesting because this is a scale in which we can use, for example, LHC to test this kind of models. Here I'm presenting a few slides from this paper here, in which is presented a model of resonant leptogenesis within a left-right symmetric model. And here we have a particularly interesting signature associated to the collider production of the new retained neutrinos. And here the signature is represented by 3 both same sign and opposite sign of the leptons. And in this work, it's been demonstrated that by comparing the amount of same sign and opposite sign dilepton events, it's possible to test the variable region corresponding to the leptogenesis. In my last 2 minutes, I would like just to give you what we can have instead if we consider the conventional thermal leptogenesis, which is a mechanism that works instead when the neutrino masses are deep in the multi-TV regime. Here I would like just to mention a recent interesting work which studied the leptogenesis in the so-called neutrino option, which represents the case in which the Yukawa couplings of the new retained neutrinos, besides also being responsible for the leptogenesis mechanism, are also responsible of the solution of the hierarchy problem and of the breaking of the electroweak symmetry. And as last mentioned, so the case in which we have really the conventional leptogenesis, here I'm just shown in this last slide, a result from a work in which it's possible to realize the conventional thermal leptogenesis by just relying on the phases present in the PMNS matrix. And so in this case, one can test this kind of scenario by just the measurement of the PMN of the eventual PMNS phase at present and next future experiments. I think since I'm already over time, here these are my conclusions that I leave you just to read. And I thank you again for your attention.
Thank you very much. Grazie mille. We have time for 1-2 short questions and short answers, if there are any. I do not see any raised hand. I would like to thank George again for almost perfect timing, plus only 1 minute. It was excellent.
Many thanks to you.
Grazie.
Prego.
And next speaker is Arnella Palamara. Please. George, okay, good.
Okay, sorry.
Okay, it's fine. Okay, full screen, please. Okay, great. Go ahead, please. Arnella, you could start, but probably you did not unmute yourself. I don't know.
Yes, I need to do that.
Start again.
Good afternoon, everyone. And first of all, I would like to thank the organizer for inviting me and giving me the opportunity to tell you about signature for new physics in short baseline liquid argon neutrino experiments. So what I would like to cover is, first of all, a few words about why we are looking for beyond the standard model physics in short baseline liquid argon time projection chamber experiments. And I will focus on 4 liquid argon TPC experiments sitting on 2 neutrino beams at Fermilab, the short baseline neutrino program, which includes actually 3 liquid argon detectors, and the Argonaut experiment taking data some years ago, but still giving very interesting results. So why we can look for new physics in liquid argon TPC short baseline experiment is because the combination of high intensity proton beam, which produce high intensity neutrino beam for precision neutrino measurement, coupled with large mass, in some cases, liquid argon detectors close to the beam target, with all the wonderful characteristics of the liquid argon that I will review in my few slides, in a few slides, open unprecedented opportunity to probe signature for new physics and new scenario in the neutrino sector and beyond. What we can do is the opportunity that we have can be divided basically in 2 categories. The first one are modification to the neutrino oscillation paradigm, so effects of beyond the standard model physics on neutrino oscillation. And the other is to look for new experimental signatures. And there is a very long list here, from dark matter to milli-charged particle to heavy neutrinos, that are producing the target when the proton hit the target to produce the neutrino beam. And then we can look for in neutrino detectors. At Fermilab, we have two neutrino beams. The first one is the NUMI beam, which starts with the main injector accelerator, 120 GeV protons, producing a neutrino beam with an average, with an energy in between 4 and 7 GeV, which is a tunable beam. And the second beam, which is the booster neutrino beam, which start with the booster accelerator, 8 GeV protons, producing, which is the Fermilab low energy beam, produced 700 MeV, average energy neutrinos. On the Fermilab area, there have been, in some cases, 4 different liquid argon TPC experiments. The first one was the Argonaut detector, a very small, only 240 kilogram active mass liquid argon TPC, so a tabletop size experiment, basically, sitting on the NUMI beam, on axis on the NUMI beam for only 5 months and taking data several years ago, but still producing results. The experiment was 100 meters underground, just in front of the Minos near detector, which was used as a spectrometer for many of the analysis of Argonaut, and the detector was 1 kilometer from the target. The second liquid argon TPC experiment installed at Fermilab is the Microboon experiment, which is currently the world's longest running liquid argon TPC experiment, taking data from 2015 to present. The detector is on axis on the booster beam, but also receive data, receive beam from the NUMI in an off-axis position. Other two detectors added to the Microboon detector form the short baseline neutrino program. Those are the Icarus detector as far detector in the short baseline program, and the short baseline near detector, or SBND, as near detector in the program. And the detector are all the three on axis on the booster beam, but also Microboon and Icarus receive off-axis data from NUMI. So the short baseline neutrino program, as I said, is composed by 3 experiments. So here is the target. The near detector is the SBND detector, 120 ton liquid argon mass, 110 meters from the target. Then there is Microboon, 89 tons, 470 meters. And then the large Icarus detector, 476 ton of liquid argon at 600 meters. The program has been designed for sterile neutrino searches, and I will tell you in a moment about that. But the important and key feature is that the 3 detectors share the same beam, the same nuclear target, and the same detector technology. All these designed to reduce the systematic uncertainties to the % level for the oscillation searches. Few words about the status of the Icarus and the SBND detector. I'm not going to say much about Microboon because there was a presentation at this conference about Microboon. So Icarus, the Icarus detector has been commissioning since summer last year and collecting neutrino data from the booster beam and the NUMI beam since March this year. And here you can see 2 events, one muon neutrino events from the booster, one electron neutrino events from the NUMI beam. Now there are improvements in progress, and the goal is to start the physics data collection in October this year. Here you can see very nice picture of the detector. The first one when one of the 2 modules of the detector was installed inside the pit, inside the cryostat, the top of the cryostat with all the electronics and the other facility for the detector functioning, and a beautiful image from the inside of the detector. The near detector is under construction. All the components are at Fermilab, and we are now in the assembly phase of the TPC. The detector actually has 2 TPC volumes. So here you can see the installation of the central cathode, which is already done, and the installation of the wire planes on one side and the other side of the TPC will happen in the next months. But all the components are at Fermilab. All the components for the photon detector are at Fermilab and ready to be installed. From the point of view of the facility, the warm cryostat is already installed in the building, and we are starting the installation of the cold cryostat soon in the detector building. The detector is expected to be ready for cold commissioning by the end of next year. I would like to spend a few minutes just to remind you why we use the liquid argon TPC technology for all those neutrino experiments, both the short baseline and long baseline. I think this image, which has an old image from a bubble chamber detector. We all know how many beautiful results on neutrinos were coming from bubble chamber detector. And on the other side, there is an image of a neutrino events from the Argonaut detector from a liquid argon TPC. We can immediately notice the bubble chamber quality of the liquid argon TPC data with added the important characteristics of being able to measure also the energy, to do calorimetry. And in fact, the liquid argon technology offered the possibility to measure a neutrino interaction in real time with sub-millimeter position resolution, and has excellent sensitivity for energy deposition from sub-MeV, as I will show you in a moment, and those are quite new results, to the GeV energy range that we know a liquid argon detector works very well there. So at work, a liquid argon TPC can give, starting from multiple 2D projection of the events, we can achieve 3D reconstruction of tracks and shower in the detector. At the same time, the total charge is proportional to the energy deposited, so we can have the calorimetric information. And from the energy deposited per unit length along the track, we can do particle identification, so recognize proton from kaon, from muons, and so on. Here there is a collection of events from, again, the Argonaut detector. The reason why, sorry, I'm showing you this is because what I would like as a message, an important message to give, is that the liquid argon TPC, combining this beautiful imaging with the calorimetric information, is able to provide us information on any kind of neutrino topology, starting from very simple topology, like here where we have just a lepton, a muon in this case, emerging from the neutrino interaction, or an electron here, and going toward more complicated topology where hadronic activity is present at the vertex, like one proton here, 2 protons here, a proton and a pion here, plus the muon, or much more complicated topology with a lot of track from neutrino deep inelastic scattering events. The same for nu E. And important, if we focus on these events here on the bottom, is that we can recognize, for example, the presence of showers produced by gammas, like in these events here, where there are 2 pi zeros producing 4 gamma showers, and I will come back to this. But the important message is that liquid argon TPC allows us to characterize the events in terms of particle content and kinematics, and recognize hadronic activity in the neutrino events. I mentioned before about the capability to reconstruct sub-MeV energy deposition. This is a quite relatively recent result that has been achieved again from the Argonaut collaboration, being able to demonstrate the capability to recognize and reconstruct sub-MeV isolated energy deposition, like we can see here, where we have a neutrino events with the muon and the proton, plus those isolated energy depositions that have been reconstructed with an energy threshold of 300 keV. And this capability, I want to mention, is very important, for example, for the detection and reconstruction of supernova events in large detector like DUNE, but also open the capability to study new physics scenarios, as I will show at the end of my presentation. Now let me focus on what is the main goal of the short baseline program, which is the search for sterile neutrinos, and why we are doing that. There are, as we all know, there are experimental hints for beyond the 3 neutrino mixing. I'm not going in any details here because those has been presented in other presentation during these conferences, but you know, we have accelerator anomalies with electron-like event excess from LSND and mini-Boone experiment. Plus we have reactor and gallium anomalies. And all these anomalies could point at BSM physics in the neutrino sector. So the existence of eventually additional sterile neutrino states with large mass square difference, driving neutrino oscillation at small distance. So that we want to see in short baseline neutrino experiment, for example. A key point here that I would like to emphasize is the fact that we know important results on this topic are coming from the mini-Boone experiment, which was sitting on the same booster beam on which the short baseline neutrino program is. The mini-Boone experiment was a Cherenkov experiment, so not capable to distinguish electrons from photons, so electrons from pi0, for example, because and if you look here there is the data which show an excess with respect to Monte Carlo predictions. And if we look here, most of the background is coming actually from photon-like signature. And here is where the liquid argon TPC enter into the game, giving us the possibility to discriminate electron from photons in a clear way. Here there is an electron event, an event with an electron shower, and here an event with 2 gamma showers produced by a pi0. And as I said before, an important characteristics that we use in liquid argon to discriminate is the topology, because a gamma presents a gap from the vertex. And also we analyze the energy deposition per unit length in the 2 cases in the first few centimeters of the shower. And we can recognize electron where the deposition is around 1 minimum ionizing particle from photons that being producing electron positron pairs have a double ionization. And discriminating this is a crucial capability of the liquid argon in order to understand the signal versus background nature of the electron-like excess observed by mini-Boone. This is where the micro-Boone experiment is sitting, is designed to investigate the low energy excess observed by mini-Boone. The physics run from the experiment has been recently completed, and the series of first results on this low energy excess are just around the corner. The experiment decided to look at different final state, so different topologies, similar to the ones that I was showing you before, in order to have a complete picture of what is going on. So stay tuned because results are coming soon. I told you about this, the presence of this, the appearance of an excess of electron-like events. But if we look in the parameter space and we try to combine the measurement from experiment that have seen an appearance together with the measurement from experiment, which at the same time try to look at disappearance of mu neutrino, this also should be there for a sterile hypothesis to be true, we see immediately that there is a big tension between the allowed region by the disappearance and the allowed region by the appearance. So something is going on there, and we want to look into that. So the first way in which the short baseline experiment can look into this is that the SBN program has the unique capability to be able to measure, and this is the only experiment that can do that, measure at the same time appearance, neutrino electron appearance and mu neutrino disappearance at the same time in the same experiments. So, and here in red, you can see the sensitivity of the experiment in the appearance and in the disappearance at 5 and 3 sigma, compared with the global allowed region, which are the green area there, the LSND result here, the other area there. And we see that SBN can cover the parameter space at 5 sigma quite well. And for the mu disappearance, the same. And I want to emphasize that the observation of mu disappearance will be essential for the interpretation of any electron excess as being due to the existence of sterile neutrinos. Actually, the landscape is not limited to that. Several alternative BSM models have been proposed in order to explain the short baseline anomalies. For example, this presence of appearance and not mu disappearance. I'm not going to in any details of the model here. There is just a representation from a good friend of mine, a theorist, Pedro Machado. But this is not at all an exhaustive list. But what I want to emphasize is many of these models predict a complex final state, with different level of hadronic activity. Many of these models predict as final state those trident, which are opposite sign lepton pairs, and which is something that we can measure very well in liquid argon. So, of course, here again, a representation of some of those models. Some of the signatures are somehow clearer, like mu plus, mu minus trident, but other, of course, are more challenging. E plus, E minus in several detectors, photons, electrons, and E plus, E minus are basically indistinguishable, as I said before, like the Cherenkov detector. So in the SPN program, and in particular in the near detector, it's our goal to explore the landscape and test not only the sterile neutrino hypothesis, but other new physics. And all of this we want to do, of course, using the unique capability of the liquid argon technology, which open up all the information that I showed you before. So characterizing the final state in terms of particle content and recognize the presence of hadronic activity, which is critical to distinguish signal from background, for example. I want here to talk briefly about another important characteristic, which is the prism characteristics of the SPND near detector, which is a unique characteristic because the detector is actually slight off axis. By design, the detector has been positioned at 74 centimeters off from the center of the booster beam, and this allows us to sample different multiple of axis with the same detector. Here you can see how the flux evolve moving on the different of axis position when we slice our detector like with something like is designed here. So for mu neutrino, we clearly see the center of the beam, that the beam is not centered in the center of the detector, while an important point is that electron neutrinos are instead more uniform. And these, for example, allow us to work with something like ratio of nu e to nu mu, which change with moving of axis. This allow us, and all those studies are ongoing, to study different interaction model constraint, sterile neutrinos, also oscillation with the near detector only, and dark matter searches.
Sorry, Ornella, you
Yes.
spoke 21 minutes. You spoke 21 minutes. Okay.
Good. Thank you. So let me show here. So as I said, several studies of new scenario physics are ongoing for SBND. And here, for example, there is a collection of some of those studies for going from dark matter to heavy sterile neutrinos to dark neutrinos, producing electron-positron pair in the final state. As I mentioned before, that's a very important component of our program, being able to measure electron-positron pair, because several of these scenarios end up with this type of final state, or studies done, for example, to study dark matter, which produce a very forward-going electron. Here, the prism characteristics is very important, because the dark matter signal will be basically uniform, while the background, which is mainly neutrino elastic events, decrease with the off-axis angle. So this helps us in the study of this type of topology. Now, on this topic, I want to mention that the microboon experiment has recently published 2 searches. One search for heavy neutral leptons going in muon pion, and another search of Higgs scalar portal is actually the first attempt to recognize electron-positron final state from the NUMI off-axis events. Of course, after the SBN program, the DUNE, in particular the NIA detector, will also probe several BSM scenarios, and there is a nice paper here which summarizes the capability of DUNE. I just want to finish presenting two searches done with the tabletop size detector that I mentioned before, the Argonaut detector. Argonaut has been able to make the first search for heavy neutral leptons decaying in a mu plus mu minus in liquid argon TPC, and the paper has been recently accepted, so this is a very new result by PRL. And here you can see the Monte Carlo simulation of one event. We actually focused on HNL produced predominantly by tau decays, and then HNL decaying in mu plus mu minus, as I said. Here there is a Monte Carlo simulation of the events going through Argonaut that you can see compared to the MINOSPHERE detector, this little square there. And in the Argonaut detector, since the mu plus mu minus are very forward boosted, in some cases they could appear like just one track that you see there. But then when the mu plus mu minus enter the MINOS detector, which is magnetized, we can clearly recognize the opposite sign muons. As I said, the analysis has been completed and published. 0 events have been observed in the data compatible with the expected background. And here you can see in the parameter space exclusion region a 90% confidence level, the Argonaut limit, which as you can see represents a significant increase in the parameter exclusion region compared with other previous results. The other result that I would like to show on new physics from the Argonaut experiment is a search for milli charged particles. This actually has been presented already by Zhen Liu a few days ago, but I want in a parallel session. So this is the search for milli charged particles. So with charge much less than the unitary charge, produced by meson decay and detected in the Argonaut detector to the scattering electrons that they produce when they ionize the liquid argon. The low energy threshold that I mentioned before is the key here for this type of analysis. And one candidate event actually has been observed with 2 hits pointing to the target, and which is compatible with the expected background again. So here you can see the Argonaut limit again in the parameter space, and you can see the Argonaut put leading constraint in unexplored parameter region again. So this brings me to the conclusion. Liquid argon TPC neutrino detector and short baseline are fantastic tool to look for new physics in the neutrino sectors and beyond. I showed you some example, but of course we are here to have more hints from our theorist colleagues. And please, if you have any other model that we could try to test, please be in touch. I showed you that the potentiality, I think, of the liquid argon TPC detector in this sector are shown by the fact that the Argonaut is small liquid argon detector exposed to the NUMI beam for a very short time, provided leading constraint on milli-charged particle and heavy neutral leptons. And but in any case, the best is still to come. The three SBN detectors sitting on the booster beam at Fermilab will perform a world-leading search for electron volt scale sterile neutrinos. And beyond the flagship oscillation search, the SBN program has also a broad science goal. I haven't touched at all the important program of measuring neutrino interaction and neutrino cross-section. But beyond that, the SBN program also has the science goal of addressing alternative explanation of the short baseline anomaly and includes other BSM exploration at the same time. Thank you very much.
Thank you very much. Fortunately, we have no time for questions and discussion. I recommend to use chat to ask questions and communication with speaker. Thank you very much again for excellent talk. Thank you. And next speaker is Fabio Montavani.
Yes, do you hear me?
Yes.
Okay, excellent. And do you see my slides also? Okay, you're mute, yes. But I understand that is okay. So first of all, thank you very much for the invitation. I appreciate it. And today I would like to speak about geoneutrino, the state of art and future prospect. Some results that I report in my slide is collected in a review paper that we are going to publish together with these colleagues. Briefly, the outline of my presentation, first of all, we will try to understand the different contribution to the terrestrial heat power and why geoneutrinos are relevant in this for this topic. At the end of 2019, Kamlan and Borexino collaboration published the last release of geoneutrino, and then I will summarize them. And I will show you how to extract mantle geoneutrino signal from multi-site detection, in this case from Japan and Italy. And what are the implications for the Earth heat budget? Finally, we will see the future prospect for the next detectors, NOPLAS and Juno in particular. Well, we can start with a very simple observation that the Earth is hot, and in particular, the Earth has the highest heat power in the terrestrial planets. So it implies some open question about natural radioactivity in the Earth. Let me summarize some of them. What is the radiogenic contribution to the terrestrial heat production? Which thermal condition the Earth initially is formed? And how much uranium and thorium are in the crust and the mantle? Please don't forget that the deepest hole excavated by human being is only 12 kilometers depth, and the radius of the Earth is 6,400. And we don't have any sample from depth higher than 700 kilometers down. So the deep Earth is geochemically inaccessible in this moment. And what is hidden in the Earth core? Maybe a georeactor, potassium-40. There are many hypotheses about that. And finally, is the standard geochemical model, the so-called Balsky Earth, consistent with geoneutrino data? Well, the heat power of the Earth that I indicate with Q is about 40 terawatt, okay? It's equivalent 10 to 4 nuclear power plant. And the conduction is not the only way of Earth cooling, because convective motion are responsible for significant fraction of the surface heat loss. The quantitative assessment of heat transport by hydrothermal circulation remain a difficult task, because as you can see from this map, the highest heat loss is in the middle of the ocean, where you have the underwater volcanoes. And the heat flow observations are sparse in the world, mainly in the continents, and not uniformly distributions, in particular in the ocean. So as you can see from this table, the contribution of the flux from continents are, let me say, well known by different authors, but the contribution from ocean is still debated. And this implies that the Q value, the heat power of the Earth is embrace a big range, okay, between 30 and maybe 50 terawatt. If we speak about the Earth heat budget and we neglect the tidal dissipation and gravitary contraction, which is negligible in this framework, the two main contributions to the total heat are basically two. The secular cooling, so the cooling down caused by the initial hot environment of early formation stages, and the radiogenic heat, which is produced by what is called heat-producing element, okay, uranium, thorium, potassium. As you can see from this scheme, in the core and the mantle, the contribution from the secular cooling is dominant, okay. But of course, the range is big. On the opposite, the contribution from the radiogenic heat and is dominant in the lithosphere and in particular in the lithosphere. The lithosphere contains about 2% of the Earth mass, but it accumulates 40% of the total heat-producing element. It produces 8 terawatts of power. We can measure it, collecting sample and make some evaluation of the distribution of uranium, thorium, potassium in the crust. On the opposite, the radiogenic power from the mantle, the contribution, the secular cooling from the mantle and core are model dependent. And so it's not clear to up to now the ratio between the secular cooling and radiogenic heat. In this framework, the people used to define the Ure ratio, which is basically the ratio between the radiogenic contribution in the mantle respect to the total heat production in the mantle itself. In this framework, geoneutrino can say something, because uranium, thorium, potassium in the Earth release heat together with antineutrinos in a well-fixed ratio. So in principle, if you detect geoneutrinos, which are the antineutrino produced by beta EM decays, including uranium and thorium chain, you can say something about the radiogenic power of the Earth. We can note that in the uranium decay chain are included 8 alpha decay and 6 beta decay, which produce 6 antineutrino. Please note that the endpoint of the maximal energy of these geoneutrinos are about 3.3 MeV, and only a small fraction of geoneutrinos from uranium and thorium can be detected by inverse beta reaction that I report here, okay, less than 10%, order 6%. And you can note also that the antineutrino produced by potassium 40 decay is under the threshold of inverse beta reaction. And we expect a flux of order of 10 to 6 geoneutrino per centimeter square per second on the surface of the Earth. And we used to report the signal in terrestrial neutrino unit, which correspond 1 event per 10 to free proton per year, which correspond basically a 1 kiloton of liquid scintillator. Okay. Now go directly to see the recent result from Camlan and Borexino. Camlan released the last data in the end of 2019. As you know, Camlan is 1 kiloton liquid scintillator detector in Japan. Well, speaking about geoneutrino, the uncertainty reached by this experiment is order of 15%. And so it's pretty good. The ratio between the signal from reactor, which is a kind of noise in the region of geoneutrino detection, and geoneutrinos is order of about 3.4, 3.7. But it's not constant. So they forced them to analyze different time series due to the fact that during immediately after earthquakes, they stopped and they shut down the nuclear power plant. So this ratio is not constant. Well, speak about Borexino, you can see that the background event compared to the Camlan is definitely lower. So the radio purity is higher. And the ratio between reactor events and geoneutrino events is about 0.7. So it's a good place for measuring anti-geoneutrinos, Borexino and Gran Sasso in general. Unfortunately, the total mass of Borexino is lower, 0.3 kiloton liquid scintillator. Here I summarize the timeline of Camlan and Borexino geoneutrino results. And it's nice to, well, the first observation of geoneutrino was in 2005 by Camlan collaboration. And they report the result on Nature. And in the last release, both experiments reach uncertainties or comparable to the uncertainty of the model. So this is very important for understanding the implication, the geological implication of this measurement. Well, if you want to extract mantle geoneutrino signal from multi-site detection, so from Camlan and Borexino, which are in Japan and in Italy, we need to consider, first of all, what we call the far-field lithosphere, basically this thin layer on the top of the Earth, which is included the crust and the continental lithospheric mantle. And since the flux goes with the inverse of the inverse square distance, it's important to evaluate the near field crust contribution, because in a range of about 500–600 kilometers, you receive about 50% of the total signal. And so for this reason, if you want to extract the signal from the mantle, you need to consider the experimental result and subtract the contribution from the far-field crust, so basically this brown layer, and the continental lithospheric mantle. And finally, you need to subtract the contribution from the near-field crust. Of course, the target of this observation is the mantle, because it's the main unknown reservoir in the Earth. Please note that this geological model needs to comply with the following constraint. The far-field crust model needs to be unique for the analysis. And moreover, the near-field crust should be built with geochemical and geophysical information typical of the region around Camlan and Borexino. And the near-field crust must be geometrically complementary, so they need to fit with the rest of the lithosphere. And all neutrino signal contribution should be separate and reported together with the uncertainty. If you follow this logic, we can see that the far field crust and the continental lithospheric mantle signal are fully correlated because they are derived from the same geophysical and geochemical information. On the opposite, the local information, so the near field crust signals for Borexino and Kamla are considered uncorrelated because the peculiarity, the geological peculiarity of the two regions are totally different and independent. Well, using the experimental signal published, the two collaboration without any spectral information, unfortunately, we reconstruct the probability density function of the two experiments, and then we extract the mantle geoneutrino signal from uranium-thorium in TNU for the two experiments. And you see here, okay, here you see the probability density function. So the joint distribution of the signal from the mantle can be inferred from the probability density function with the condition that the signal from the mantle detected from the two regions is the same. And then we extract this signal, which is 9 TNU plus minus 5, roughly speaking. So this is the final result of this analysis. If you want to understand the implication in terms of the fundamental question that I mentioned at the beginning, we need to understand what is called the biospheric Earth models. Well, this model describes the primordial non-metallic Earth condition that follow the planetary accretion and core separation prior to its differentiation into mantle and lithosphere. So basically, in this long list of authors, we summarize about the papers of the last 30 years. You can recognize that there are three classes of bulk silicate Earth model. What is, let me say, make an analogy with is the same of the solar standard model in some sense. Okay, so we have the poor heat producing element models, which estimate about 12 terawatt from uranium, thorium, potassium, and the medium one, which estimate about 20 terawatt from uranium, thorium, potassium, and the rich model, which estimate about 32 terawatt. Okay, globally for the Earth. Since we know the contribution of the radiogenic power from the lithosphere, and this is independent by biospheric Earth because we can, in some sense, measure it collecting samples, as mentioned before. The discrimination capability of combined geoneutrino measurement among the different biospheric models can be studied in the space signal from the mantle versus radiogenic power. Okay, so it's simple because there is a linear correlation between these two quantities, and the slope depends by the distribution of heat producing element, in particular uranium and thorium, in this case in the Earth, because if you consider a homogeneous distribution, for the same amount of uranium and thorium, the signal is higher. And if you put all uranium and thorium on the base, in the core mantle boundary, you obtain the opposite, the low scenario. Okay, these are the two extreme cases which is compatible with the geochemical observation. So if we report the three classes of biospheric Earth here for the radiogenic power from the mantle, we can see the Kamland and Borexino combined analysis in this framework. Okay, so roughly speaking, we can say that this combined result fit with the medium model. And This is the last result of a combined analysis with the lower uncertainty. And here there is a collection of geoneutrino mantle signals. Let me go back to the previous scheme. And so the question is, what can I understand from this result in terms of Earth heat budget? Well, first of all, we can understand the ratio of heat production over heat loss, and also the Ure ratio can be fixed. So basically, here you can see the heat producing element, radiogenic heat power estimated by Kamla and Borexino compared to the previous model. And then you have a constraint also for the secular cooling, since the total amount of heat is fixed. So very quickly, some few words about georeactor after the discovery of natural nuclear reactor in Gabon in Africa. Some authors make the hypothesis to have some georeactor in the deep earth, in different position of the earth, and fitting reactor spectrum and constrain the spectrum number of reactor antineutrino events. Borexino collaboration put an upper limit for different power of georeactors in different position of the earth, and this georeactor are excluded at 95% confidence levels. Briefly, the expected geoneutrino signal from SNOW+. We expect the result maybe in the next year. And please note that the ratio between signal from reactor and geoneutrino is roughly close to 1, due to the fact that close to SNOW+ you have Bruce power station about 500 kilometer distance, and it is the number of events is not negligible. Here I report some expectation, and in particular, this paper report the contribution from local geophysical and geochemical local information. So we can repeat the same exercise that we did with Kamla Borexino also for SNOW+.
Excuse me, Fabio, you spoke 20 minutes at the moment.
Okay, I conclude. This is the summary of expected signal from Juno. And finally, then I skip this and finally take away message, the deep, to deeply understand the experiment geoneutrino result, we need to use a refined geological model. And for the moment, we extract the mantle radiogenic power from the mantle, using a combined analysis from Kamla and Borexino. And the presence of georeactor in the center of the Earth is with a power 2.4 terawatt is excluded 95%. And the most important message is that very soon we will investigate the Earth with Kamla, Borexino, SNOW+, and Juno results. And so this means that the era of multi-site detection of geoneutrino is definitely open. Thank you very much.
Thank you very much. We have time for a few questions, if there are any. Please, Marco, go ahead. Unmute yourself, Marco.
Yes. Ciao, Fabio. I'd like to ask the following. How big is a pity that we don't have a detector in the Hawaii?
Sorry, I missed the question. Could you repeat, please?
The question is, wouldn't be, I mean, we won't have a detector in the Hawaii, right? Yes. In any time soon. How big are we losing? What are we losing? It will be very useful. Am I wrong?
No, it's useful because in this logic, in the Hawaii, you basically minimize the contribution of the far field lithosphere, and also the contribution of the near field crust. So these brown and green terms are negligible because you are far from the continents. And so basically the experimental signal is dominated by the mantle, because at the Y, the mantle is very close to the surface, order of few kilometers, and the continental lithosphere in America and Asia are very far. So basically, the uncertainty that you receive from this term is lower, and so in some sense you have a direct measurement of the signal from the mantle. Okay, so concerning the dimension of the detector, is enough to repeat Cameron dimension, so it's a good experiment in this framework.
Thank you very much. We have still time for one question more, but I do not see hands.
Thank you.
Thank you. Okay, let us thank speaker again. It was very interesting, really. And the last speaker of this session, Federico Nguyen.
Hi, good afternoon, Alexander. Can you hear me?
Yes, yes, I'm hearing you. But
okay, now I switch on the video.
Good. Okay, good.
And then I think I have to share my screen.
Exactly.
Okay,
good. Full screen, probably.
Can you?
It's fine, but it would be better full screen or not.
Is it not full screen now?
It's not full screen, it seems to me.
Because to me it seems full screen.
Okay, it's good. It's good. Go ahead.
Okay. Okay. Let me thank the organizers for inviting me to this conference for presentation, and it's really great that also this year this could be made. And the main subject of this talk is a different application of particle accelerators, different than high energy physics colliders, namely free electron lasers. So after introducing the topics, we pointing out two specific applications, I will describe in detail the XLS compact light project, with main emphasis on two drivers: a technology one, namely short period magnet ondulators, and a user driver, namely the FEL performance and the reach needed to cope with the applications I will mention. And then I will conclude with one particular perspective. So back to some basics and a brief detour to basics. So these are light emitted by electron beams entering in magnetic insertion devices, and depending on the K parameter, namely the magnetic deflection strength parameter, you end up in a Wiggler radiation rather than an undulator radiation. But then, if the electron beam is very high quality, something more happens, namely bunching, that allows the free electron laser dynamics to take place. Here, for example, what happens passing from a disordered system to an ordered system where all single electron waves emit in phase at the same resonating wavelength. And if the bunch length is much smaller than the radiation wavelength, so-called bunching happens, and the free electron laser dynamics take place. And it allows to have a coherent photon source with many applications in physics, chemistry, biology, and medicine. Here, for example, this is the electromagnetic spectrum, whereas by shortening the wavelength.
Oh, sorry, Federico.
Tell me,
we are seeing the first slide.
Oh, this is a pity. So something nasty is
yes,
happening?
now it's second. Fourth, it's okay. Now it's
okay.
Fine. That's fourth slide. But before we saw only first slide.
Okay, let me jump to PowerPoint. That maybe could make. Sorry for that.
No, but fourth slide was visible.
Okay, let me. If
Okay, it's 20. Okay. It's better probably. Go
Okay,
ahead.
It's full screen, correct?
Yes, it's good. Full screen. It's nice.
Okay, thank you. Sorry for the.
No. It's okay.
Okay, so I was telling that. So by shortening the wavelength, namely increasing the photon energy, you are allowed to probe viruses, proteins, and on the vertical axis, I also qualitatively emphasize the thing to probe these kind of targets with the laser-like quality of radiation that in the X-ray domain can be provided in an efficient way only by means of X-ray free electron lasers. And out of many applications you may find in literature, I would like to point out two target applications, namely study of chemical properties through magnetic polarization and coherent diffraction imaging of biological samples. For example, the magnetic properties, the X-ray study of magnetic properties could be enhanced by the X-ray magnetic circular dichroism technique, namely studying the difference between left and right circular polarization FEL. This allows for specific atom, element, and site studies, and there is a growing interest in ultra-fast switchable FEL polarization applications for this in this field. And of extremely interest, in particular nowadays, is the diffraction. The diffraction electron imaging, where coherent photons hit the sample, creating a diffraction pattern. And what is visualized in the detector is the Fourier transform of the electron density. So you need to obtain the 3D images, you need to process several diffraction patterns. And since the sample is destroyed by the FEL photons, you need also many identical samples. But then at the end of the day, you come up with the full 3D reconstruction of the virus by means of X-ray FEL, extremely important at present. So, but what is the XLS compact light design project? The collaboration gathers several laboratories, international laboratories, and university institutions with the aim at promoting the design of the next generation FEL sources. And the main goal is the design of a specific goal is the design of a 5.5 GeV beam energy X-band LINAC. So based on the click technology, for an FEL able to cover both soft and hard X-ray options. It consists of 26 institutions plus 5 associated partners, and clearly it is consists mainly of European institutions, since it belongs to the Horizon 2020 InfraDev European Union funds. And here are the details of the duration. The main goal, as mentioned, is to facilitate the widespread development of X-ray facilities, and with the stress on the affordable and cost-effective aspects of the enterprise. So it somewhat assembles 3 key pillars for accelerator and magnet technologies, namely high brightness photoinjectors, high gradient radio frequency accelerating structures, and the main topics of this talk, novel short period magnetic ondulators. Here is an estimate of the peak brilliance of XLS as a function of the photon energy as compared with the other existing FEL and synchronous radiation facilities. Here you see that it stays well within the most performant FEL facilities, but here the main challenge is the size reduction the thing is, the more compact is the facility, the more affordable and easy to implement will be. It will then ideally fit any university campus. This is the main philosophy of the project study. And here is a sketch of the XLS structure, where the several working packages are superimposed on the sketch of the facility layout, of the baseline facility layout. And let me remind the three key pillars. And please consider that I will focus only on ondulators and light production, but please consider that for each key element, comparison and down selection of several options have been applied in a fashion very similar to what happens in the clearly based on physics performance, feasibility, risks and costs, in a fashion very similar to what happens in high energy physics experiments when deciding their detectors technology. Here, then, what is the target? The target is shown here on the table of FEL parameters from dedicated discussions with the users, and basically they would like to have a repetition rate up to kilohertz in the soft X-ray regime, and possible simultaneous operation of both soft and hard X-ray. In addition to that, peak brilliance of about 10 to the 31 soft X-ray and 10 to the 33 hard X-ray photons per second per millimeter milliradian square per 1 per mil bandwidth. This implies the choice of three working points concerning the beam characteristics, three working points differing in energy, minimum peak current, and energy spread, in order to meet the user's requirements. Here is the layout of the facility, with the main linac having a length of slightly more than 200 meters. And here below is they are sketched the several accelerating stages, where you see that the target beam energy is reached after the proper energy gradients, in order to meet the hard and soft X-ray requests. And then let me focus on the main FEL character, say, the magnetic ondulator. As I mentioned, the FEL process takes place along an ondulator, magnetic ondulator device, where if the electron beam is particularly of high quality, the bunching and so the free electron, the FEL dynamics takes place. The strength parameter fixes the resonant wavelength, depending if you are working with a planar or a helical ondulators, namely if the oscillations are confined within a plane or follow a helix, and will turn out with a different degree of polarization of light accordingly. And briefly, in short, several ondulator configurations have been scrutinized and compared on the basis of technology readiness and FEL performance. For example, here are below on the left a sketch of possible permanent magnets, and here on the right some configuration of superconducting ondulator coils. So either out of vacuum or in vacuum permanent magnets based devices, be them room temperature or cryogenic, as well as low temperature niobium titanium and niobium tin structure, as well as high temperature bound tapes have been scrutinized. And the criteria the main criterion is the peak magnetic field, because at the same you want essentially would like to have the shortest wavelength, and if the shortest wavelength could be reached with the highest magnetic field, you end up with a stronger FEL interactions, namely with the higher output power that can be delivered to the user, and in addition to the pulse energy, so the power argument, you have to consider the higher the FEL interaction, the shorter is the distance needed to reach for the maximum power, and this defines an important figure of merit in FEL dynamics, that is the saturation length. And you may check here on the plot here on the bottom left that the naive expectation of a superior superconducting undulator performance is confirmed by a full FEL 3D simulation with the XLS electron beam parameters. On top of that, several undulator configurations have been compared and scrutinized, meeting the requests of the project, namely that in both cases, in both hard and soft X-ray, a factor 2 wavelength should be achieved, either by varying magnetic gap or the superconducting coil current. So you would like to have at the same shot a bright and compact source, and here is a temperature plot where the third axis, the color plot, exactly emphasizes and picks the best undulator solutions. And let me summarize in short that the best technologies are the high temperature superconducting technology, but they are not yet mature for a facility, for a user facility. Then the choice has been a niobium titanium helical superconducting undulator. Here is a sketch of the module, where you may see the about 1.8 meter long undulator module immersed in the cryo plant vessel, and so the total length is about 2.3 meters. And here are the parameters in terms of undulator period, undulator gap, and maximum magnetic field on axis. Here is a picture of the winding trials ongoing in the UK to work on a shorter, let's say, on a smaller model, where has been bound with copper wire, and they are starting, our UK colleagues are starting to bind with the superconducting wire. And I was mentioning polarization, selectable polarization possibility, and 3 schemes have been envisaged to reach for variable and selectable polarization. For example, to operate the XMCD experiments as an example, and we consider a full undulator line consisting of variable polarization undulator, a cross undulator technique, and then the third scheme, that is one that's been selected, is an undulator, possibly the most performant, followed by an afterburner. The choice at the scheme 3, since it's less expensive than scheme 1, so it clearly you cannot afford the full line with variable polarization undulator by means of cost, and they're more efficient both in terms of polarization and light pulse than scheme 2. So here is the scheme that allows us to reach for selectable variable polarization, namely a helical SCU with fixed circular polarization, followed by a permanent magnet afterburner with variable selectable polarization. And this provides, when compared with SU only or afterburner only, provides a growth shorter, so a shorter distance, a shorter length, so a shorter sides of the undulator line by 40%, slightly longer than the SU only, but SU only has no variable polarization, at the price of delivering 2.5 times lower pulse energy, but still in the ballpark of 200 microjoule, and having polarization switch control as a bonus. Then, as a last important performance test, we wish to prove that the upper FEL photon energy limit of 16 keV is feasible with the full chain of beam transients from the GAN through the last undulator exit, taking also account for the most sources deteriorating the quality of the electron beam due to collective effects, namely coherent synchrotron radiation, bunch space charge, and wave fields. So all these effects have been accounted for in the full transfer line from the cathode to the undulator exit. And we studied the thing in detail, and we saw that the beam exhibits a transfer deformation along the bunch leg due to exactly CSR. This causes FEL degradation, this deformation, this shear, but still, by looking at the solid black line, you see that the peak brilliance stays in the ballpark of about 5 times 10 to the 32 in brilliance units. So this leads me to the conclusion that XLS compact light will offer challenging FEL schemes with a broad range of operating modes by means of affordable and compact technologies, exploiting, for example, the best and most advanced solution in terms of photo injectors and accelerator gradient structures and magnetic ondulators. It will meet the requirements of simultaneous operation hard and soft X-rays, and in particular, a detailed, comprehensive FEL analysis selected niobium titanium superconducting ondulators as the magnet technology, but we also addressed alternatives. And the FEL 3D simulation with selectable polarization in the soft X-ray regime is proven to meet the requirements. Then finally, the full star-to-end simulation embedded with all the effects degrading the beam quality proved that the peak brilliance requested for probing biological samples from viruses to proteins is within reach. So please stay FEL tuned. Very last mention that in a near, in the near term, not so longer term, the compact light technologies possibly will be implemented in the Eupraxia facility, both in terms of X-band accelerating structures, and in particular also in the superconducting ondulators. And the Eupraxia consortium has been elected as a strategic infrastructure in Europe. So thank you very much for your attention.
Thank you very much. Thank you very much for your timing also. We have time for 1-2 questions, if there are any. I do not see hands, raised hands, but as I understood, it will be, let us say, some center in Frascati, near Rome.
Yeah, okay, let's say.
Please, a little bit more about organization.
Yes, sure. So the point is that the XLS compact light is offers somewhat a toolkit of technologies to be deployed, say, wherever. Then, in parallel, the Eupraxia project is going on, and most probably will make use of the key technologies of the XLS compact light. And the Eupraxia consortium project has one pillar in the Frascati. Yes.
Okay, thank you very much. Thank you very much. At the end, I would like to thank all speakers of this session for very nice talks. And I will give a floor for Professor Studenikin. Probably he has to add something.
Yeah, well,
Thank you.
first of all, I would like to thank all the speakers of this plenary session of the closing day of the conference, and also to Alexander Zakharov for his very nice contribution to this session. So we are in time, thanks to his efforts. I would like to mention that during these last plenary sessions of the last day of the conference, we are trying to go deep in our discussions to items that have been already touched in some way in some approaches during the previous days of the conference. And also just in the very last moment, we're trying to discuss items that are new for the Lomonosov conference. And the last talk, it was just an example of this problem. So now there is a break, and in 3:45, as I see on our big screen, we shall start the very last plenary session of the 20th Lomonosov conference. So, and we have some minutes before to relax. Thank you once again, and see you very, very soon. Thank you. Good afternoon. So I think that we have 1 minute. Yeah, more or less. Hi, Marco.
Привет.
Привет. Вы будете по-русски говорить, по-английски или по-итальянски?
Нет, я не говорю русский. No, I don't speak Russian. Just a few words here and there.
The most important not to speak, but to understand, I suppose. Yeah?
Yes.
Yeah. Okay. So I think that we can start. So I just announced that the closing plenary session of the 20th Lomonosov conference is opening, and it is a great pleasure for me to give floor to Professor Dr. Katerina Lipka. Пожалуйста, please.
Thanks, Alexander. I think we can also leave out Professor Doctors because we are all professors. I think. Okay, so welcome to the final session of the Lomonosov conference, and you have just seen the agenda shared by Alexander. So, and we start the session with Marco Giamacchi from ENFN Milano on the low energy antimatter physics. So Marco, if you can share your slides.
Yes, I will. Let me share my screen right now. And I hope you can see it at this moment. Can you?
Right.
Okay, great. So I'm going
to...
Now
it's full screen.
Yes, I'm going to discuss low energy antimatter physics. And the reason for low energy is the study of fundamental laws with antimatter. One can also study fundamental laws at very high energy with antimatter, but I will focus on low energy. So I will discuss at low energy, I will give you a few ideas of on why physics with antimatter, and talk a little bit about antihydrogen, positronium, and the muon atom. So in general, let me present this little picture that I will focus a little bit on. It has to do with gravitation, with matter and antimatter. So when people speak, gravitation is one of the issues for studying antimatter. Because we know very little about gravitation with antimatter. So there are two fundamental laws one can study with antimatter, which is CPT violation and the weak equivalence principles. Now, the CPT symmetric situation would be an apple falling in the Earth gravitational field, compared with an anti-apple falling in an anti-Earth gravitational field, leaving aside the fact that CPT is not a classical symmetry, but is a quantum symmetry, and these are not quantum objects. On the other hand, the situation that sometimes we study is the anti-apple falling in the Earth gravitational field, and this is not a CPT symmetry test, but it's a test of the weak equivalence principle. Antimatter, of course, has a criticality in terms of its very non-existence in the universe. The particle antimatter, particle antiparticle asymmetry is critical and is one of the mysteries of the universe that we would like to learn about. As you know, in the very early stages of the development of the universe, there was well within the very first second, there was an imbalance at the level of 10 to the minus 9, 10 to the minus 10, and that imbalance, when annihilation took place at the end of the electroweak epoch, that generated a little survival, which is all the matter that we see around us. So there are symmetries that relate particles to antiparticles that we want to study. CPT is a theory of particle physics at the quantum field theory level, and it's a flat space-time theory. And the weak equivalence principle of general relativity is at the classical level. But space-time is not flat on one hand, and reality is not classical. So these are the problems that we want to address with these systems. And on the other hand, One could say, because of this, that this kind of equation F equals ma has a dynamical meaning, and here you have the inertial mass, whereas of course here you have the gravitational charge in the Newtonian equation. So according to the weak equivalence principle, you would write this equality, inertial equal to gravitational mass, and the CPT theorem will tell you that mi equal mi bar, which if you follow this chain of equations, if you want to say that compare the flow of a particle and the flow of an antiparticle, so the two gravitational masses in the Earth gravitational field, you don't really know if there's a break in this symmetry. You don't really know in principle whether it was a CPT theorem violation or a weak equivalence principle violation. So this inequality would not necessarily mean that CPT is broken. It could be that CPT or the web are broken at the particle level. And the general framework for discussing these violations is the standard model extension, which takes into account all the beauties of the standard model and renormalization. It's an effective theory, actually, and accommodates for all possible violations, maintaining a gauge invariance and things like that that you could imagine. And of course, it contains a Lorentz invariance violation, because CPT violation cannot take place without Lorentz invariance violation. Speaking of gravity, in many quantum gravity models, one has different picture of gravity, which in the static classical limit can be represented with the addition to the regular graviton thing of a gravivector and a graviscalar component. So, and the sign of the gravivector and the graviscalar component can be different between matter and antimatter. So, this is a motivation for studying, for instance, gravitation with the particles. And from the particle physics point of view, it could be mediated by a tensor spin-2 carrier with the charge being, of course, mass energy. And what you have is the normal tensor like gravity. The graviton could be supplemented with the vector, which could be repulsive. And so it will be a gravivector component, or the scalar, which will be always attractive in any cases, but the vector, you see, will be repulsive or attractive differently in the case of a matter-matter system or a matter-antimatter system. So this is a possible motivation to study antimatter, and the studies of antimatter have a very long tradition. In my case, I will concentrate on slow antiprotons. It's actually a very subtle concept. For instance, if you do an experiment at high energy, and like we did, and we even signed papers about CPT violation, comparing masses of charged particles and things like that back in the 80s when I was a PhD student at Fermilab. And it turned out that the concept of some papers is actually a bit flawed, because what you do is you compare a final state and you use relativistic invariance to reconstruct the particle. If you use a relativistic invariance and you claim not violation of CPT, you are neglecting the correlation between them, which is called the Greenberg theorem. The Greenberg theorem is telling you that if there's CPT violation, you need to have some level of Lorentz invariance violation. So I should be discussing in principle also Lorentz invariance violation, but this is a too broad subject, so I will concentrate on these two items. We have for anti-hydrogen, if one starts with anti-hydrogen, a source of slow antiprotons, which is the CERN antiproton decelerator, followed by the Helena ring. And we have experiments at CERN in the antiproton decelerator hall. There's a bunch of experiments taking place here. We are also preparing one of these experiments. It's a detector system that is typical of CERN, and you have experiments like G-bar. Our experiment here is called Asakusa Alpha, Aegis, Base, and other experiments. It's a typical environment. And this is the only place where you can have slow antiprotons in the world right now. The production of antihydrogen at low energy has already been made. the recipe for formation of antihydrogen is catching antiprotons, catching antiprotons here, produce positrons in a positron accumulator, and putting them together in a potential well, which has this form, because you need to trap particles with different signs. Then you also need a magnetic field around to confine them. So when antihydrogen is formed, it will leave the trap, being a neutral particle, and you will detect them with a detector around the system. So this has been made, and the production of 10 Kelvin, so we measure really low energy, we mean 10 Kelvin antihydrogen or 100 of Kelvin antihydrogen, has been made in 2002. It has been confined, so there's a challenge in confining a neutral anti-atom because you need to confine antiprotons and positrons in a trap, and then the confinement of antihydrogen. In order to confine, you need to have an inhomogeneous magnetic field. It's difficult to confine neutral particles. It's based on the magnetic moment, of course, and this has been made by the Alpha collaboration in 2011, 2012, with this kind of magnetic field, which has a gradient here. It's an octopolar magnetic field with a gradient. So this has been confined for many, many seconds, and many, many anti-atoms have been confined for 1,000 seconds, for instance. So the shape of the potential is like this. And they have been playing with these different states of antihydrogen in a magnetic field. You see here the bright rally plot for the energy states, and they have been able to make flip between these states and free them free the particles with some microwave spin flip here. Of course, the detection of antihydrogen can be made, if you confine antihydrogen, by switching off the magnets, and then antihydrogen will fly. A first antihydrogen beam has been made by the Asaxa experiment. This is the configuration which I will not discuss in detail of the Asaxa experiment, but still again, you have antiproton and you confine antiproton, and here you mix them up with positrons. It's like, I'm Italian, I like spaghetti. It's like adding pasta with sauce. You need to add pasta and sauce, and you have some kind of, I don't know, amatriciana or some kind of spaghetti recipe, and you need to put together all the ingredients, and you put them together here, and they have been forming a beam of antihydrogen because of a special configuration of fields here, and they intend to study the spectroscopy of antihydrogen. We are starting to study spectroscopy of antihydrogen, and this is the main message of my talk, I have to say. So here are the states of the antihydrogen system with all the different effects like hyperfine splitting and fine structure, lamp shift, and so on. And okay, we have had mostly by the Alpha collaboration, the first observation of 1s to s transition for antihydrogen. The first observation of hyperfine transition, this transition here for antihydrogen. The first observation of, this is a 2-photon transition. It's very important, this 2-photon transition, because it's slow, 2-photon. They also have done laser cooling by means of by using, of course, the dipole allowed Lyman alpha 1s 2p transition. This has been quite a bit of achievement, and one can really say that anti-hydrogen, antimatter spectroscopy has started. And the idea, of course, is to use anti-hydrogen to do CPT tests by testing the levels of hydrogen and the energy levels of anti-hydrogen. And I have summarized here a few of the tests that can be made with electrons, muons, protons, and also K0 mesons here. This is in terms of relative accuracy. A sensitivity plot, however, should take into account the absolute energy, and you see here that if you do this, the level reached is the left side of the blue band, and possible extensions for the future are here, painted in orange. Most of these tests have to do with physics being prepared at the AD, essentially, so at the antiproton decelerator, and there are several tests of them that have been done, reaching a pretty good limit, you see here, for instance, because of these experiments, or are planned, like, for instance, the measurement of ground state hyperfine splitting, very sensitive test. The experimental test of the equivalence principle is also very important, because for matter, we have been testing the WEP, weak equivalence principle, now to the 10 to the minus 15 level. But there is no direct measurements of gravity effects on antimatter. Low precision measurement, like 1%, will be the first one. It's never been done. While you see here the progress in accuracy of web tests on matter systems. The very preliminary test has been done by the Alpha collaboration. They have been confining in the octupolar configuration. They have been confining anti-hydrogen, and then they have released the anti-hydrogen. The equation of the anti-hydrogen motion is something like this: magnetic moment, dishomogeneity of the magnetic field, and they have added a term, a gravitational term here. They have added a gravitational term here, and they have measured the effect of the gravitational term. And this was not stringent at all. The ratio between gravitational and inertial mass was measured to be less than 75, which is not, but this was a proof of principle, and they intend to improve. You will see here the up-down symmetry. So you free anti-hydrogen and you see the up-down symmetry. If this is the zero level, and this will be the level that you would see if the violation will be enormous. F equal 100 ratio between these two masses. And of course, we are searching for much smaller kind of violation. Positronium is the other system we are studying, and actually my group is studying positronium. And I like to say that positronium is really the atom. So the most elementary atom should be maybe written like this. And this is complementary to anti-hydrogen in several ways. First of all, anti-hydrogen is not an elementary particle, and not even the anti-proton is. Positronium is made by two fundamental fermions directly appearing in the standard model Lagrangian. So most of the mass of the anti-proton is not constituent mass, like we even teach this at our courses. It's like mass of the quarks plus mass of the color field. So you are really studying the symmetries in a very complementary way. The positronium comes in two states, ortho and parapositronium, according to the different spins. And of course, what we are interested mostly in is the ortho positronium, which has a longer lifetime. It's still short, but that's a longer lifetime that can be used. And there's a long tradition of testing QED with high precision, of course, with positronium, studying the decay rate, lifetime, fine structure. The inertial studies tests are, however, just at the beginning. There are several experiments here. Kuplas is our experiment, but there are also other experiments. And for instance, this is our experiment. In this configuration, what we plan to do, we plan to have positrons and to form a positronium beam. And this is really a holy grail for people searching in this, doing physics in this field. And then we need to, we're gonna form in our experiment an ion, focus the beam, photodetach the ion, and then do interferometry, which is our kind of specialty, because as a side product, we have made our group has made the first single particle interferometry experiment with antimatter ever with the positron, which was presented last time also at the Lomonosov conference. The other system that people are starting to study is the muonium atom. I don't want to call it muonium. It's a muon atom, I'm sorry. I don't want to call it muonium because it's not really correct. Muonium will be mu plus, mu minus, like quarkonium. So the mu atom is something like this, and there's a research program centered at PSI, which I would like to mention, with a very intense mu plus beam. You need to do it with a mu plus beam because you want to get some electrons somewhere. So you need to have the mu plus beam coming from some place from the accelerator and getting an electron, and you have a mu atom beam that they plan to make interferometry with. And the reason of doing interferometry is to have precision for a gravitational fall. In our case, in our experiment, we were able to measure a few micron displacement exactly because of interferometry. So the conclusion is that antimatter versus matter is really a cosmic mystery. And as a benchmark to study CPT, anti-hydrogen spectroscopy is here already. And people are studying in the experiments mostly concentrated at the CERN antiproton decelerator, but also other places. Most of them are concentrated at the antiproton decelerator of CERN. They are doing already spectroscopy. Anti-hydrogen spectroscopy is started. And as a benchmark to study the weak equivalence principle, I can say that anti-hydrogen first measurement, that means a measurement of the gravitational fold, is likely to happen in 2022 by the alpha experiment. Positronium studies are also in development to study the CPT and the web with an antimatter system with mostly leptonic component and muonium. I should have written mu atom to be consistent with myself, but you know, I wrote it in a contradiction with what I believe it should be written, and I wrote it muonium, and this is already in development. So this is a really exciting new field. And there are a variety of experiments being planned for the future. I'd like to thank you for your attention.
Thanks a lot, Marco, for this very, very educative talk. I enjoyed it a lot. In particular, we are working at the LHC, as you know, on testing the CPT with the difference of the top quark and anti-quark masses. And yeah, up to now, I have to say, it was not clear to me that really the Lorentz invariance violation has to be considered. Yeah, that's very interesting. So thanks a lot. I open the floor to the questions. So please raise your hands. So we have a question from Alexei Petrov. Please, Alexei.
Hi, interesting talk. Could you please comment on the muonium program at J-Park in Japan?
Oh, I have to say that I am not really an expert of this program. I know that it exists, and if I understood correctly, it involves Nagashima, who is the father of the PS minus. So he's really an expert of this field. But I have to say that this is one of the things that I didn't mention because I'm not really informed on this development. Muonium is a very, I'm not sure they are going to look for the fall, the gravitational fall. I'm sure that they are going to study muonium for QED reasons. Nagashima is an expert of PS minus. His group is the first that has made PS minus. I'm sorry, this is all I know.
Okay.
Are there any further questions? Yeah, please, Alexander.
Okay, thank you very much. But probably it's a stupid question, but you know, instead of generation of positronium, probably it's possible to observe something in the universe, in astronomy, because you know there is a lot of positronium in the galactic center, but I don't know what we have to observe with positronium. But probably there are some fine structures in spectral lines or something like this. But probably you said you liked Zeldovich. Once Zeldovich said that universe is an accelerator for poor people, you know. So probably
no,
we could observe something.
I really read that book, and it also says at the beginning of that book that one day we will consider the universe as a laboratory. And that was very inspiring for me. So you of course are right. But the point is that the universe is preparing for yourself the experiment, which is fascinating, but typically high energy, and typically there's the unknown of the accelerator. It's very interesting to look for positronium, also to look for spectral lines if we find a violation in laboratory, spectral lines coming from stars. But from the universe in general, not for stars. Anti-stars are unlikely. But again, the universe is a difficult place. You need to.
Yes, but there is a lot of positronium.
I don't disagree that it's interesting. It is.
Okay, thank you.
E tu interesse, no? Da. Very interesting.
Okay. So if there are no any further urgent questions, which I don't see, thanks a lot, Marco, again. And we are moving to Alexei Petrov from Wayne State University, who will tell us about the theory developments in the charm quark. So Alexei, if you could share your slides, yes, great.
I just did. Let me see. All right, can you see my slides? Perfect. All right, so thank you very much. I'll tell you about some theoretical developments in the physics of charm quarks. For many, many years, I mean, charm quark was the first heavy quark that was discovered experimentally. For still many years, charm quark continues to churn out surprises, and many of those surprises have been discussed already in this conference. Some of them will be discussed. So, for instance, spectroscopic surprises essentially comes with charm quark attached, so to speak. So, from X3872, the first molecular or tetraquark state, to the completely charmful, so to speak, tetraquark state, to pentaquark, and to the state which is which consists of two charm quarks, not charm quark and anti-charm quark. So those spectroscopy surprises all contain charm quarks, and I'm sure Rich Levitt will be able to tell you something about that. This is a huge topic. Charm quark is physics of charm quarks is a huge topic. So I'll discuss today a couple of things that are close to my heart and essentially related to some of the new advances in physics of charm quark. So I will discuss CP violation in charm system, and what is interesting about that is that CP violation in charm makes charm quark essentially an anti-superweak system if you use Lincoln Wolfenstein's dictionary. So we first actually discovered direct CP violation in charm decays rather recently. It's the first CP violating observables in a system with up quarks, and so it is interesting to verify if there are new physics contributions to those CP violating symmetries, or it could be squarely described using standard model CKM mechanism for CP violation. Another thing which is interesting about charm system is, of course, demixing. So demixing is similar phenomena to mixing of B mesons and Cairns. However, that's the only upward systems that can oscillate, that can exhibit flavor oscillations. And there is a surprise there, right there. It turns out that completely different from what we have in a downquark system, such as a B or B system or Cairns, it appears that the lifetime difference between mass eigenstates in the DD bar system is actually larger than the mass difference, which is quite the opposite in case of the bottom quark system. So maybe we'll see that the first signs of new physics will also come from charm. So let me discuss two things. One is charming CP violation, and the second thing, mixing. So let's start with charm. So how do we see CP violation in charm system? Well, the easiest way is to compare CP conjugated decay rates in various ways, both with or without time dependence, and then looking at the observables, such as the one that is given over here, where basically a partial rate of D to the final state is compared to the opposite CP conjugated rate divided by the sum. So depending on whether you or not you're looking at the time dependence here, there are possibilities of three different types of observables. And we can see that CP violation can manifest in three different ways. So first is that we can see it in delta charm equal to 1 transitions. That's where charm quantum number or charmness of a state changes by 1 unit. So for instance, in DD case to light quark states. So in this case, this is actually called direct CP violation because the rates for CP conjugated transitions are not equal to each other. So it also can manifest itself in delta C equal to 2 transitions, which is oftentimes called indirect CP violation, which can be observed in mixing. This is when we have a phenomenon of flavor oscillations when D turns into a D bar. So in this case, we change charm quantum number by 2 units. And of course, there are observables that we can see here. Or the most famous probably observable from the B system is the observable that comes from the interference between decays and mixing. And this is what was measured long time ago as sine to beta in BDKs. So charm decays actually have their own flavors, and let me give you a couple of points of that before we start discussing it. So if you look at non-Newtonic charm decays, and those are the most ubiquitous in studies of CP violation, we could see that non-Newtonic decays can be actually classified by, in the standard model, by the Kabiba-Kobayashi-Masukawa suppression of the 3 amplitudes. So if I adopt the old formula, the old notation of Wolfenstein, and call VUS, CK matrix element, as lambda, it's about 0.2. I can classify my non-Newtonic decays in 3 different ways. So there are Kabiba favored decays. So this is when the tree-level diagram, so the Feynman diagram is given over here, is proportional to lambda to the 0th power. So essentially, there is no suppression. It originates from C to S UD bar transitions, and an example of that is essentially D naught going to K minus pi plus transitions. There are single Kabiba suppressed decays. That's when tree level is suppressed by 1 power of lambda, right? So you could see that it comes from either here or here. So it originates from transition C to Q, U, Q bar, where Q is either strange quark or a down quark. And examples actually well known nowadays. It's D decay into pi plus pi minus, or D naught decay into K plus K minus. Those are actually quite interesting, and I will tell you why. And there are also doubly Kabiba suppressed decays. So those are proportional to 2 powers of lambda squared. They are suppressed. And examples are actually quite interesting. So they also have an example is a D decay to K pi, except for the charge assignments are different. So a very naive way of searching for a CP violation by looking at the final state, CP conjugated final state, does not necessarily easily work here. You have to study time dependence to separate contributions from double Kabiba decays. So we shall here concentrate on single Kabiba suppressed, and the reason for that is basically this this funny picture over here. Besides besides tree-level decays, it also exhibits penguin contributions, and those penguin contributions are quite important. Well, the reason for that is the following. So, as I said, there is if you compare decays of D mesons to final states with their CP conjugated states, we could see that the only way to generate a direct CP violation in the standard model is by employing two different routes to reach the final state from the initial state. What I mean by that is that there should be at least two different amplitudes with different strong phases and different weak phases. And charm quarks are interesting because if you look at this diagram over here for the singly Kabibov suppressed decays, you would see that all quarks in the initial and final state belong to the first two generations. Since they belong to the first two generations, that means that the CKM mechanism is essentially reduced to a 2x2 Kabibov matrix, which is known not to have CP violating phase. So we must somehow reach out to the third generation of quarks, and this is due to penguin decays where you somehow either use non-unitarity of CKM 2x2 matrix or actually really reach out to B quarks intermediate states, which are quite suppressed. So in reality, this nice picture is actually quite complicated for theorists. So if I look at the difference, just like I advertised, if I look at the difference between D decay into the final state and anti-D decay into an anti-final state, I would find that my CP violation symmetry would contain three parts. It would have a direct CP violation from mixing, and from the interference. So this particular observable is rather rich. So if I look for a particular final state, which is a CP eigenstate, I would notice that those fellows are essentially, well, to the degree, are the same for the KK and pi final states because they're CP eigenstates. So I can form asymmetries that are actually differences between asymmetries in kns and asymmetries in pions. In this way, I can experimentally only be sensitive to direct CP violation. So in direct CP violation, I see that there are two different pathways. One is due to penguins, which is given here by P sub F. The other one is due to amplitude, which is tree-level amplitude. And as you could see, there is a direct dependence of this direct CP violation on the ratios of amplitudes, on the sign of the weak phase, and on the sign of the strong phase. So if either weak phase difference or strong phase difference is 0, there is no CP violation being generated. So the results in direct CP violating asymmetry can actually be seen as formed as a difference between this symmetry in kns and pions. And as it turns out, in the SU3 flavor symmetry limit, it actually doubles one of the single symmetries. So this comes from the fact that the CKM parameters differ by a sign in here. So this is actually interesting. If I look at the difference between different CP violating asymmetries, I not only cancel some of the asymmetries that I don't want to look at, as well as systematic uncertainties. I would also double the value of my CP violation. So of course, that's the argument, but of course, SU3 is badly broken in DD case. So we'll see what kind of consequences this would lead, this would have for our analysis. So experimental results, indeed, LHCb reported in 2015 essentially 5 sigma observation of the difference of direct CP violating asymmetries, which established CP violation in the upward system. This, however, is not so for the individual decay asymmetries. As you can see from the earlier LHCb measurement, we cannot say that those CP violating asymmetries are indeed non-zero. So in order to be sure that this happens, we actually need confirmation, I believe, from other experiments, such as Bell 2, which will eventually happen. But most importantly, since this result is here, we have to interpret what this result means. So does it mean that there is new physics, or we can actually explain it within the standard model? Of course, after the observation, there are many theory results that came up, which offered different opinions about this particular CP-violating asymmetries. It could be that there is a new physics contribution, and I'll discuss that. There are also some analysis that claim that it can be explained in the standard model. So in order to say that this is so, we actually have to perform a calculation of CP-violating asymmetries. And this is actually somewhat difficult in charm system because of the variety of reasons. So the biggest reason why this is different is actually soft QCD. Even though charm is a heavy quark, its mass is not that much larger than 1 GeV. So expansions that work well for B quarks do not necessarily work well for charm quarks. Additionally, effects of soft, charm meson lies in the region which is populated by resonances, light quark resonances, and so they might somehow affect the calculations of our symmetries or amplitudes, and essentially skew our simple picture of decays. And so pictorially, you could see that if there are tree-level amplitudes for decays and the penguin amplitudes for the decays, which could be clearly seen here as a picture of diagrams, and naively, in the picture on the left, you could see that you could easily separate trees from penguins, right? I mean, there's no way you can mix them up. Well, however, once we turn in a non-perturbative QCD, we can really not turn it off. The difference between the trees and penguins start to blur because of strong rescarings of quarks in a final state, and essential non-distinguishability between the penguin diagrams and tree-level diagrams. So one way to address that is not to calculate things, but use a certain basis of amplitudes which could be fit to experimental data. So one of those is something called topological flavor flow diagrams. So one postulates that there are several diagrams that all D amplitudes can be expressed with, and then relate the final and initial state of different amplitudes using SU3 flavor symmetry, taking into account SU3 break-in in some model-dependent fashion. So we can fit many decays modes, but assume standard model weak phase. So if you do that, you would see those expansions for many of the amplitudes. You would see expansions in terms of a tree level, exchange diagrams, different types of penguins, and so on and so forth. So the trick here is to make sure that the basis of your independent amplitudes is actually sufficient to describe all experimental data that is available. And then once this is done, you can fit for what you do, you fit for amplitude and the phase, a strong phase of each of those amplitudes. And after that, you will see, you can predict CP-violating asymmetries. So this was done in a different type of analysis. And of course, because of the particular way of handling flavor SU3 break-in, there are different solutions for the same direct CP-violating asymmetries available. But if you combine all of those two, we'll see that the asymmetry differences seem to be consistent with the LHCb observation of delta A CP. So can one claim that this is indeed new physics that is not significant in the description of those decay amplitudes? Well, so essentially, in a standard model, we need to estimate the size of a penguin versus penguin contractions versus tree amplitudes. And so there are different ways of doing that, including the one that I just described, using, for instance, the flavor flow diagrams. However, since we are using a particular fit of experimental data, it is possible that those amplitudes that we fit to contain both standard model and new physics parts. So it is rather difficult to use a fit to experimental data, which might contain, as I said, both standard model and new physics, and then claim that the result could be completely explained using a standard model only parameters. But the most difficult problem in fitting approaches, just like what I described, is many parameters. The problem is that you have to fit matrix elements to decay rates that are measured maybe to the precision of a percent. However, the CP violating asymmetries are of the order of 10 to the minus 4. So can one actually claim that you know your direct CP violating asymmetries to 10 to the minus 4 precision if the rates that you fit are only known to a percent? So in that case, you're not really sensitive to to true physics, but really sensitive to the experimental uncertainties of decay amplitude. So in principle, in order to proceed here, one needs direct calculations of the amplitudes and those CP violating asymmetries. There are several of them available, and one includes QCD sum rule calculation of delta ACP, which we did. There are other calculations that are possible. There is, of course, always progress in lattice calculations of those decays. It's very slow. This particular decay must use formalism, Lusher formalism, which is quite difficult to implement in D decays. However, the progress is still there. So there are possibilities to evaluate those CP violating asymmetries directly using, for instance, like QCD sum rules. The techniques are well known from B physics. And if we calculate those decay amplitudes, you would find that the lifetime difference would turn out calculationally to be approximately 7 times smaller than what was observed experimentally, right? So the question that one would ask here is whether this calculation is robust. There could be some duality violating corrections that could not be taken into account in LightCon QCD sum rule calculations, or there is something new at play, for instance, new physics amplitudes. And different groups took different points of view, but this is an interesting problem that needs to be addressed further. As far as mixing is concerned, the mixing calculations are also notoriously difficult because in case of chair mixing, unfortunately, the mixing amplitudes for mass and lifetime differences between the mass eigenstates and DD bar system actually could be dominated by long distance effects. So you can write the lifetime difference and the mass difference in terms of those integrals that involve time-ordered products. And there are two different approaches to calculating those. One is that one can directly calculate those in QCD using a heavy quark expansion. However, in this particular case, one has to deal with SG3 break-in as well as imperfect 1/m expansion. The other way is to populate this time-ordered product in terms of hadronic degrees of freedom and use experimental data to compute lifetime differences and mass differences. So I'm going to just give you a couple of calculations that were done at the quark level. It's interesting that so the lifetime difference calculated in this way is very sensitive to how you compute those things in QCD. So at leading order, different terms in this expression for lifetime difference, scale differently with the strange quark mass. Once you go to next leading order, you will see that the scaling changes. Moreover, at higher orders in 1 over m expansion, the dependence of the amplitudes upon the strange quark mass softens even more. So at the end of the day, you would get a gazillion of matrix elements that needs to be somehow evaluated. If you do a guesstimate, you can have a result which is about 10 to the minus 3, which is probably consistent with what we see experimentally. So a new thing that was proposed last year is that in the calculations of those mixing amplitudes, there is a interplay of different scales that enter the calculation of QCD corrections and the calculations of loop diagrams that pertain to mixing. So the question is that whether a contribution from different quark intermediate states need to be evaluated at the same scale that we have in our loop calculation. And so it turns out that if you vary those scales independently, you essentially say that the predictions are worse enough to account for the standard model I mean, the standard model predictions are bad enough to account for experimentally observed lifetime difference and mass difference. So it appears that the result at this stage is consistent with the standard model. And of course, the answer, if you take this point of view, whether we can really describe mixing, DD-bar mixing using quark language would be clarified once the next leading order calculations become available. So let me conclude by saying that there are several issues with theoretical evaluations of mixing and CP violations. In particular, exclusive approach, there are actually even a philosophical question whether the fitting to different exclusive channel to mixing would constitute a prediction of a lifetime or mass difference. The computation of charm mixing amplitudes is still a difficult task, even though there is indeed progress in QCD summary calculations as well as lattice calculations of that. And many of the calculations, in particular the quark level calculations of mass and lifetime difference, need to be revisited. My last slide essentially is the following. So if I go back to my discussion of CPU violation in charm, you see that some of the calculations are significantly smaller. Standard model calculations are produce significantly smaller predictions for CPU violating asymmetries. So there are four possible answers to the discrepancy. Of course, the theory and experiments could both be somewhat incorrect. So this is not a very interesting case. It could be that the theory is not quite correct, but the experiment is correct. In this case, standard model wins again. The same thing is true in the opposite direction. However, if the theoretical calculation is correct and experimental measurement is correct, that would actually mean that we are observing new physics in charm. So it is possible that in a current round of experiments, we could see a smoking gun of signals for new physics. Thank you very much.
Thanks a lot, Alexei, for a very interesting presentation. According to the time, I think we have a very short time for maybe one question, if there is any. So please raise your hands. If it's not the case for now, I think then the questions can be taken online in the discussion. And thanks, Alexei, again. And we move now to the talk by Richard Lebed from Arizona State University on the dynamical diquark model. Thanks, Richard.
All right.
We can see your slides. Great.
Good, good. And I assume you can hear me. So I'd like to begin by thanking the organizers for honoring me with this invitation. I'm going to be talking today specifically about all heavy tetraquarks. And yes, I'm going to be putting a little bit of focus into my own dynamical diquark model, but I want to talk about a little bit about the other approaches as well. And so even though this particular talk is about heavy tetraquarks in general, in this particular talk, we're going to be focusing on the developments that came from the observation by the LHCb collaboration of structure in the di-Jape side channel. And the reason is there's really not that much else coming out of the other sectors. There was a false alarm of a 4B state at 18.4 GeV using CMS data, but it turns out that even the CMS collaboration themselves did not put out a paper on it. It was only presented in a particular talk. And LHCb followed up on this and studied upsilon 1s, mu plus mu minus, and found no significant structures. Could you please mute the other people, please?
So everybody who is unmuted except for the speaker, could you please mute?
Okay,
I think
thank
it's
you.
actually Georgi who is unmuted, who is also recording.
No problem. Okay, so as I was saying, LHCb found no structure in the 4B sector, and it hasn't been really studied yet, but there's no structures reported yet in mixed bottom and charm sector. So specifically, we're going to be talking about what's going on in the di-Jape side channel. So even though that's the case, a lot of the lessons that we're going to be talking about today are generally applicable to all heavy tetraquarks. And so let's begin by asking, how are all heavy tetraquarks made, or at least how have they been made? At the LHCb, it appears to be mostly gluon-gluon fusion, analogous to not exactly the same as the way that the Higgs boson is made. But moreover, it turns out that if you look at non-resonant all heavy quark production, it turns out that both single, like this guy, and double parton scattering are important, although the resonant ones seem to be going mostly through single parton scattering. And it's also been pointed out that it should be possible to produce these all heavy tetraquarks in heavy ion collisions. So that's something to look forward to in the future. Now, this area of all heavy tetraquarks is one small corner of exotic hadrons, and exotic hadrons is a very active field of study. Here is where we are as of August 2021 in the neutral charmonium-like sector. Here are the conventional charmonium states in black. All of this in red are exotic candidates. As you can see, it's quite a lot. And moreover, there's plenty in the charged tetraquark sector and in the pentaquark sector, where there are no equivalent ordinary charmonium type states. So as of this moment, in August 2021, according to my count at least, we're up to 52 observed exotics, most of which are in the charmonium-like sector, including the pentaquarks. There's the famous one, decaying to di-Jape psi, which we're going to talk about in just a moment, but there are others as well. For example, ones that have a single charm quark, some in the bottomonium sector, one with two charm as opposed to a charm and an anti-charm quark. There's a lot already. Of these 52, 15 are declared to be established by the particle data group, and none of the other 37 have actually been disproved, although a few of them are on the fence. But my naive count estimates that there are still over 100 more exotic heavy states waiting to be discovered. So this is a very active field. So let's look at this LHCb paper and the plot that launched 100 theory papers. It's only a slight exaggeration, but it's getting pretty close to that number. So this is the data. And as you can see from it, there's obviously something going on here in this range of 6,000 to 7,000 MeV. Specifically, the eye immediately notices four regions. First of all, this very sharp resonance here, but also a broad bump here, a sharp dip here, and some interesting structure here at about 7,200 MeV. And we're going to be taking a look at each of those throughout the talk today. So the most apparent feature is apparently the X6900, the only really obvious peak right there. Now, notice that 6900 MeV lies about 700 MeV above the di-Jape-Psi mass threshold. So that's very interesting that it's so far away from the threshold, but it is likely not wider than the rho. So it's known to be less than about 200 MeV, and perhaps much narrower than that. If you could form a 4-charm state, a 2-charm, 2 anti-charm state as a traditional dimeson molecule, if you were going to try to do it the way that people do it for, say, a deuteron, then it would be bound through exchanging conventional charmonium. And if you say that it has the usual expected order of 10 MeV molecular binding energy, the charmonium would be very, very far off shell. And in addition to that, if you look at typical charmonium mean charge radii from potential models, especially 1s states like the Jape-Psi, you see that in order to have an exchange of Jape-Psis, you would have to have a very short-ranged interaction, which means that you don't really have the possibility of treating a 4-charm state as being bound by charmonium exchanges unless it is very compact. Okay, so then what about non-traditional dimeson molecules? Well, you could look at Pomeron exchanges or other types of multi-gluon exchanges. And of course, people do that. Or you could look at soft gluons being exchanged, but then hadronizing into light meson exchanges. And there are papers, including ones very recently, that are exploring this as a possibility. So there is the possibility that a state like this is bound by meson exchange, just not the simplest possible example that you might think of. There are also some important features that have to do with quantum numbers when you're looking at these states. If you look at JPC for a di-Jape-Psi state, both of them being 1-, they're identical bosons. Well, the first thing you notice is that, of course, the total charge conjugation is positive, but you find that the only S-wave states that are available are 0++ and 2++, and in the P-wave, there are only 3. It is a much more constrained, restrained spectroscopy than you might otherwise have if the quarks inside of these things, if the bosons that you were decaying into, the 2 Jape-Psis, were not identical. And if you look at the JPC for a system made of 2 identical charm, 2 identical anti-charm fermion pairs, that's also restricted in their S-wave. In particular, the color structure of the 2 charm quarks is either going to be color anti-triplet in a spin 1 or color sextet in a spin 0 state. So these put strong constraints on the available spectroscopy. Now, let me tell you some history of theory studies of these states. It goes back longer than you would think, but it is not as deep as you would think. So if you go all the way back to the 11th of November, 1974, what old timers in our field call the November Revolution, when the Jape-Psi was discovered essentially simultaneously by 2 groups, it did not take very long. In fact, it took less than a year until the very first di-Jape-Psi theory paper was written. But then there were only 5 more theory papers on this system written in all of the 1980s, only 1 in the 90s, 3 in the 2000s. Why? Because, to quote one of the papers, all the states are unbounded and consequently rather uninteresting. Well, taking a look at modern hadronic physics, we now reject that statement as being very short-sighted. There's a lot going on in the physics of these unbounded systems, as it was described back then. The next big step came in 2010 when first physics was taken at the LHC, and it was very soon afterwards pointed out that there would be lots of gluon-gluon fusion into di-Jape-Psi states, and that it could easily be reconstructed at LHCb. This was summarized in 2 very nice papers back in 2011 and 2012. And you would think that this would have started a cottage industry of people trying to study the system, but nothing else happened until 2016. And then there were only a dozen papers from 2016 until the middle of last year. What happened then? Well, on the 16th of June in 2020, there was a CERN seminar by a colleague of mine, Lupan An from LHCb, latest results on exotic hadrons at LHCb, where she presented that plot of structure that I showed you a few slides back. And then bam, the ambulance chasers among us theorists took over. There were 8 more theory papers just in the following 2 weeks. Why 2 weeks? Because that's how long it took for the actual LHCb preprint to appear on the archive. And since that time, there have been at least 53 theory papers posted on the archive discussing the 4-charm structure as of the last time that I took a look at it. So what are we going to be able to say in a short talk like this about 53, 75, whatever theory papers? Well, a lot has been tried, and I want to make apologies to anyone in the audience who's an author of one of these papers, because I'm not going to be able to focus on each one. Just to summarize, there have been calculations using string junction models, quark models of various types, chiral quark models, diquark models, effective theories with light meson exchanges, threshold effects, QCD sum rules, the lattice, Reggie phenomenology, holography. Here's an interesting one. There's a paper in which it's claimed that the X6900 might even be a Higgs-like boson as opposed to an ordinary tetraquark state. So a lot of different theory has been thrown at this particular set of data. So my job for you guys today is to try to give some sort of summary, some sort of idea of what are the observations of lasting impact that are coming out of this. So the first thing I want to do is I want to show you, this is a blow up of that LHCb data. I want to show you the relevant charmonium thresholds, all of the meson-meson pairs that can couple to the state. Starting with, here's a threshold, the di-Jape psi, and then not much happens until you get way up here to the very first A to C, A to C2S state, and you notice it's in this weird color. That's because A to Cs have opposite spin structure to Jape psis or chis, and so if you had a di-Jape psi state that happened to consist of an A to C2S, it would require a spin flip in order for that decay to occur. So you don't think that's going to be a very strong transition. The more important thresholds are sitting up here in red, like Jape psi 2s and chi C0, chi C0, and so forth. And you see, you get quite a forest of them up here by the time you get to the 6900. And finally, up here at around 7200, you reach the first open flavor transition to the double charm Xi baryon. So what sort of solid conclusions or consensus points can you come up with when you look through all of these papers? Well, it seems to be a consensus that X6900 from its structure appears to be a genuine resonance, even with the presence of those multiple threshold effects that we just looked at that might explain other CC bar structures. Now that is a consensus opinion, but it is not a universal opinion. There are other papers that suggest that the 6900 itself might be generated by nearby threshold like chi C0, chi C1. On the plot here, that happens to be this orange line. You see it's sitting very close to the 6900. Moreover, virtually all models to date predict ground state 1s resonances for the 4-charm system to be much lower in mass than the 6900. They typically lie in the range of 6,000 to 6,400 MeV. And this has been stated ever since that very first theory paper in 1975. So it's expected that the 1s states would be all down here. So then what is the 6900? Most obviously, it could be a 1p state, and that's been explored, or it could be a 2s state. That's been explored in a number of papers as well. Now, clearly, measuring the parity of the state is going to answer this question. Why? Because we're talking about 2 quarks and 2 antiquarks. So 1p states would be negative parity, 2s states would be positive parity. So measuring parity is an absolutely crucial observable to try to disentangle this system. Okay, so then the next structure, what about this broad structure around 6400 to 6500 MeV that we were just taking a look at right there? Well, that, as we've mentioned, is about the upper limit of where models predict the ground state, the 1s states, to occur. And again, there have been plenty of papers that have discussed this. In fact, if you look at the LHCb paper, they talk about a model 1 and a model 2 for fitting the data. And their model 1 is to say that the broad structure is a superposition of at least 2 resonances. Now, talking about 1s, you might wonder, well, we're talking about a 4-body state. What do you mean when you say a 1s state, which is something that is suggested in a 2-body description? Well, since we've been arguing that ordinary conventional molecules are problematic for the 4-charm system, and there really weren't any good thresholds in the 6400 to 6500 MeV range, then it's a very natural thing to describe states in terms of the quantum numbers of their diquarks. And specifically, you might think, okay, we're going to use the color triplet and color anti-triplet diquarks for that, and then describe 1s state as being the 1s of this particular quasi-particle and that one. Now, not everyone agrees that this is the natural 1s state. For example, this paper notes that if you talk about the attraction of 2 colored quasi-particles, the sextet, anti-sextet attraction is stronger than the anti-triplet triplet, despite the fact that if you formed a diquark that was in a color sextet, you would have rather more quark repulsion. And this paper goes on to say that the ground states actually mix these 2 configurations. However, when you go up to the more excited states, you find that the color triplet, color anti-triplet structure dominates. The third structure in the data is that sharp dip around 6750 MeV. And again, just to remind you, we're talking about this guy right here. Now that suggests a destructive interference, presumably with X6900. And in fact, I mentioned LHCb presented 2 models in their paper. Their model 2 suggested an interference between a broad 6500 MeV structure and the resonance. So what kind of interference could it be? Could it be due to chi-C0 threshold effect, as was presented by Carlin and Rosner? Well, again, here is chi-C0, and here's the dip. So that's a possibility. Also, if the 6900 turns out to be, as several more papers seem to suggest, a 2s state, a parity plus state, then it turns out that 6750 MeV is where the 1p states, the parity minus band, would be expected to lie. And so you'd say, oh, could that be an interference? The problem with that is that parity plus and parity minus configurations do not interfere with each other. And again, determining the parity of these particular events is going to be absolutely crucial to trying to disentangle what it is we're actually seeing in the data. Finally, there's this little structure that LHCb notes around 7200 MeV, this little business around here. And we've already noted that there's an interesting threshold here. Namely, it's the first time that it's the threshold for being able to make a baryon anti-baryon pair on shell that has open flavor. And so that's the first place where open flavor decays of the 4-charm state would be first allowed at 7242 MeV. Likely, there are going to be no observably narrow 4-charm structures above this point because of the possibility of having open flavor decays. In terms of the theory, using the work that I've done, that's where the color flux tube that connects the diquarks breaks. Or if you look at a holographic model, that's where new string junctions become possible. In either case, this is a point of important physical significance as far as 4-charm quark physics would be concerned. Okay, so now let's turn to the question of how many states would you actually think that you're seeing in the data? Now, if you describe the degrees of freedom in terms of dye quarks. You don't have to, even if you had a molecular model, you could still describe the degrees of freedom in terms of dye quarks. Then you'd say, well, in general, we can have color anti-triplet and color sextet dye quarks. And if you allow both of them to occur, you find a lot of states, as was pointed out by these folks. Wow, there are a lot of states. And that's even if you constrain yourself to just taking charge conjugation positive, like in the di-J-psi system, and low angular momentum, 17 of them below that open flavor threshold. So what you can do is adopt a very minimal ansatz and suppose, for example, that the only dye quarks that are going to occur are the most tightly bound ones, the color anti-triplet ones, in which case you get only about half as many states. If you then further make the constraint, as in what is called the dynamical dye quark model, that you're going to assume the only spin couplings that are significant are the ones within dye quarks, as opposed to ones that would connect the dye quark and the anti-dye quark, then you find that all S-wave multiplets of these all-heavy tetraquarks would consist of only 3 degenerate states, 2 of which you would find in di-J-psi. And in the P-wave multiplets, you would find exactly 7 states, of which 3 would have charge conjugation positive. And the neat thing about the P-wave is that there's an equal spacing mass rule if the only important mass operator is spin orbit. So they're arranged here so that you see -3, -2, -1, 0, +1, +2. You could also suppose that there's a strong tensor coupling as well that would spoil this equal spacing rule. But the important point is this, that with a simple couple of observations, that in this model, the S-wave states are degenerate, the P-wave states have an equal spacing rule, you can hope to try to find simple patterns in the data as it becomes refined. Okay, so this is my last slide. I want to give you a few parting thoughts of things to think about for the future. I think I've made the case that we desperately need spin parity information on what we're looking at, particularly parity information to disentangle the spectrum. There have been some excellent suggestions of what to do going forward. One of them is to look at the spectrum of J-psi, psi-2s. That is certainly possible at the LHCb. The problem is that you lose a lot of phase space because the 2s is a lot higher in mass than the J-psi. However, you no longer have identical particles here. Now you have access to more resonances than before. It's also true that the psi-2s production is lower than that of the J-psi, but again, LHCb is very good at characterizing its decays. Also, I want to point out that if you look at what are called the Y states, the 1-, states in the charm anti-charm light anti-light sector at best 3, they find that different ones show up more prominently in J-psi or psi-2s decays, and something similar might happen here. The next point I want to make is that we've been talking about gluon-gluon fusion for di-J-psi. That's all charge conjugation positive. It is an open question whether there is much 3-gluon, which would be charge conjugation minus production. If you could do that, you could hope to find the 1± resonance via J-psi A to C production, even though A to C is harder to reconstruct, although it does have a very nice clean decay channel into proton antiproton. Or alternately, you could look at J-psi high C decays, which would also be charge conjugation minus. But again, just like we had with the psi-2s, you have less phase space to look at. And finally, don't forget about CC bar, BB bar, and BB bar, BB bar production. In particular, the mixed charm bottom one could be detected through J-psi upsilon processes. And again, because it's no longer identical particles, you should have access to more resonances than you did with di-J-psi. And that will also provide important tests of quark flavor universality. So here we are in the opening stages of experimental information on all heavy tetraquarks, and there is a lot to be done both on the experimental side and on the theoretical side. And at that point, I want to thank you for your attention and welcome any questions you might have.
Thanks a lot, Richard. So the floor is open for questions now. I don't see any at the moment, so I take a chance to ask a question myself. So except for the spin parity information, which I think will come once also more data are coming in, because once you need much more statistics to look into the angular distributions of the decay products and so on. Is there anything else we can look at as experimentalists, like, I don't know, the hardness of the PT of the decayed products of the new particles, or something like that? Are any other observables, or the rates, or the comparison of the rates, which is probably the first thing which one could start measuring with the more statistics before one has enough data to measure the angular distributions? Are there any...
Right. So I think the things that I mentioned on this slide, looking for Jape psi 2s and Jape psi upsilon, and maybe Jape psi chi, are going to be the easiest things for the experimentalists to do next. Because I think it's just a reconstruction efficiency issue in most of these cases. Things like the hardness of the PT distribution, that's going to tell you more about the structure of the state rather than whether there is a state. And since we're at a stage right now where we say, oh, there is one definite resonance and several possible resonances, I think the most important thing is going to be to look at other decay channels like this and see if you see the same structure.
Mm-hmm. Okay, thanks a lot.
Mm-hmm.
Any other questions? If not, thanks, Richard, again. And now we move to the next presentation, which is a bit different. So Stephen Gorley from PTNZ Consulting Group will review or give us a few insights into the SNOMAS procedure, where probably many of us are involved. Stephen?
Yes, can you see the screen?
Yes, I see your video now. I can see the screen at the moment.
Oh.
Try to share.
Try again here. Okay. Can you see it now?
Not yet. Now I can see your desktop now.
Okay.
Yes, right. Okay, perfect.
All right, sorry about that.
Thanks.
All right, so I want to start by thanking you for the invitation on behalf of my co-conveners, Vladimir Shiltsev and Tor Robbenheimer. They're actually at a kickoff meeting for our organization group today after a pause for the SNOMAS process. So I'm the one elected to give the talk today. So let me start by just taking a brief look at the current US landscape of projects and programs. The more international aspect of the SNOMAS process will come out when I get into that. And then I'll go through the SNOMAS process, the organization, and all the committees, frontiers, and groups that we have, something on the timeline, and then focus more on the accelerator frontier, and then some of the topical groups and initiatives that have risen sort of to the top at this point. All right, so I made a list of some large US accelerator construction projects, and I was kind of surprised when I did this. There's quite a bit of activity going on. So we're involved in the high luminosity LHC upgrade. And of course, the big project in high energy physics in the US is a long baseline neutrino facility and a proton improvement project at Fermilab. And then in nuclear physics, the facility for rare ion beams, that project is soon to be completed. And then they've just begun the electron ion collider at Brookhaven. And then basic energy sciences, both Argonne and the Advanced Light Source at Berkeley are doing in the middle of upgrades. And LCLS2 and LCLS2 high energy project are going on. And then we have some upgrades at the SNS. All right, so one of the outcomes of the last SNOMAS and prioritization process was a subpanel that focused more on the accelerator R&D. Typically, the strategy doesn't include a lot of accelerator people. It's mostly physics driven, which is the way it should be. So there was a separate panel put together to focus on accelerator needs in the context of the priorities from the previous organization. So that what came out of that was the near-term goals. So LBNF and the Deep Underground Neutrino Experiment, the High Lumi LHC, and the ILC was factoring quite prominently in that study. And then midterm, looking at multi-megawatt proton accelerators, a very high energy proton-proton collider that comes up every time, and a TeV scale upgrade of the ILC. So looking ahead to the ILC, and then more longer term goals, a multi-TeV E+ E- collider, and a neutrino factory. And you'll note that what's missing relative to this year is any discussion of a muon collider. All right, so right now, US HEP accelerator R&D is focused on technology. We have a strong program in high field magnets and high gradient RF. We were heavily engaged in the linear collider from 1980 to 2008. And that was refocused on superconducting RF technology for cost reduction in view of the ILC. And there's been a strong advanced acceleration programs, laser plasma, beam plasma driven accelerators. At this point, there's no concept for a collider, but they're more focused on the fundamental demonstrations of what it would take to do that. And then for a while, we had the muon accelerator program from 2011 to 2015. Based on the outcome of the last strategic planning process, MAP was canceled. So let's get into what SNOMAS is. So it's basically a particle physics community study. Our job is to provide input to the Particle Physics Project Prioritization Panel, or P5, more simply. And all we're charged to do is gather information from the community. That means international community. Everybody's welcome to contribute. There are no prioritizations from SNOMAS. We just try to put everything on the table in as coherent a way as possible. And that takes a year and a half to 2 years. Now this year, we were delayed a full year. This time we were delayed a full year because of the pandemic. So we called a halt to everything more or less for a year, and we're just now starting again. The original schedule would have had us writing the report by the end of this year, but that's now been pushed to the end of next year. Then that report will go to another group, the P5, who will spend about a year going around listening to proponents for various ideas in terms of physics, accelerators, and so on. And then they will write a report that will be fed to the Department of Energy and the National Science Foundation to plan their programs appropriately in terms of funding. And then we start work in that context. And then another several years, we'll have another SNOMAS and do it all over again. So this is a current timeline. Right now, we are soliciting white paper submissions through March. And from those and letters of interest that we received, we'll have preliminary topical group reports on various topics. Those will be boiled down to frontier reports, and the frontiers will then come up with executive summaries. So you see this giant stew is getting boiled down to just the essence. And then we'll have these final reports, and then we'll come out eventually with a book that will be in archive that will then go to P5. So the main event will be this community summer study at the University of Washington in Seattle in July this year. So here's how we're organized. We have an advisory group and a steering committee made up of members of the Division of Particles and Fields, mostly from APS, Division of Physics of Beams, Cosmology, Gravitation, and so on. And then we have 10 frontier areas, which I'll get to in a second. Some liaisons, which interact between the different frontiers to try to integrate as much as possible between them, keep the communication up. And then we try to get early career people involved in something called Snowmass Young. And then we have about 80 topical groups. And driving this whole thing is a community input. This is totally a community effort, community-driven effort. So here we have the conveners and the different frontiers. We have energy frontier, neutrinos, frontiers in rare and precision processes. And here's Alexei right here. He just gave a talk today. The cosmic frontier, theory, accelerator, instrumentation, computational, and underground facilities and infrastructure. This is largely driven by the neutrino experiments, and community engagement, which is something that physicists typically don't do a very good job on, but we're trying always to do a better job. All right, so here's just a kind of a list of the frontiers and kind of the things that they're working on. So we have about 30 frontier conveners, 250 topical group conveners, more than 40 inter-frontier liaisons, and 25 early career liaisons involved in this. So you can imagine with the logistics, you know, Zoom meetings all the time, it's pretty tough to pull off, but it's been working so far. So we had a community planning meeting in October. Let's see, my window is covering up my date. Anyway, we had about 3,000 participants, about 650 outside the North American time zone. And that's kind of significant because it was very inconvenient for a lot of people because we had it sort of in prime time in the US central area. So people put down were asked for their interests. So this is a primary frontier interest. So you can see that the energy frontier and cosmic frontier dominated pretty much. The secondary frontier interests. See, a lot of people said, well, I'm only interested in that. Again, energy frontier, cosmic frontier, computational theory, about the same. And then these letters of interest reflect also community interest. So here's energy frontier, computational, and accelerator are the three largest. Now the accelerator frontier, which is our focus, includes just about everything that's relative to accelerators, high energy hadron and lepton colliders, high intensity beams for neutrinos, physics beyond colliders, accelerator technologies, RF, magnets, targets, and sources. And we submit, we solicit letters of intent and form our effort around those priorities, get them documented. We have these key questions. So what is needed to advance the physics? What is currently available? What's state of the art around the world? What new accelerator facilities could be available in the next decade or even the next decade? What R&D would enable these future opportunities? What are the time and cost scales of the R&D and associated test facilities, as well as the time and cost scale of the facilities? Now that's a tough question to answer. We're looking at a very broad spectrum of proposals. Some are very mature, like the FCCEE, like the ILC. Others are at the extreme end, are just concepts at the moment. So there's various amounts of R&D needed to realize the potential of these ideas. Now these are a breakdown of the topical groups within the accelerator frontier. So we have beam physics and accelerator education. Some of these reflect the funding categories for DOE high energy physics. So beam physics is one. Accelerator technology, they have RF, superconducting magnets and materials, and targets and sources. Now, this is a new one, actually, that came out of the last strategic planning process that was added to the list based on the process we had before. We have neutrinos, electroweak Higgs, multi-TeV colliders. There's a lot of interest in this particular area this time. Accelerators for physics beyond colliders and rare processes, advanced accelerator concepts, and again, accelerator technology R&D. Then we added another group we call the Implementation Task Force. This is to evaluate and compare various options, and this is a big job. I'll talk about that in just a minute. So we had started out with a joint workshop between the energy frontier and the accelerator frontier. The first day, we looked at the more mature proposals. So we had FCCEE, the Chinese CEPC, ILC, CLIC, Electron Ion Collider, Large Hadron Electron Collider at CERN, High Energy LHC, SPPC in China, and FCCHH. So these are relatively mature compared to some of the other ideas. And then the next day, we looked at cold normal conducting linear colliders, an ERL-based FCCEE, gamma-gamma Higgs factories, plasma laser Wakefields at 1 TeV plus, plasma beam Wakefield accelerators at 1 TeV or more, structure beam Wakefield accelerators, and then the muon colliders from a Higgs factory all the way up to 14 TeV. All right, so just to give you an idea of what's going on, here are some of the working group activities. The beam physics people have been running a series of physics of ultimate beams and examining the fundamental limits of accelerator technology. One thing we note is that theorists like to look way out, and we have to kind of reel them back in sometimes and say, hey, that's going to be very hard to do, or maybe sometimes we have to say it's impossible. We have to keep things, to get our arms around it. AF3 is looking broadly at various options for Higgs factories, E plus E minus, gamma gamma, muons. AF4, this is the multi-TeV group, considering multiple paths to high energy, including E plus E minus, gamma gamma, muons, proton proton. There's lots of enthusiasm for a muon collider, partly to fill the gap from 3 to 14 TeV. So there are two efforts going on now. One is the US Muon Collider Forum, which is not directly associated with SNOMAS, but it does gather the community and contribute in terms of white papers and so on. And they also participate with the International Muon Collider Collaboration run out of CERN. AF5, this is the rare processes. They're working on many small or moderate scale proposals. AF6, this is the advanced accelerators, trying to understand options to upgrade a more conventional linear collider, as well as look at limits of plasma acceleration, so multi-TeV. Now they're obviously going to be on a longer timeline than some of the more mature technologies, so they have to look ahead to find out what sort of R&D has to be done to demonstrate the feasibility of these technologies. Then AF7, this is the accelerator technology. The three subgroups are exploring the limits of accelerator technology to help support these other areas. And many of these efforts are supported in part by a collaboration between the US and Japan. So this implementation task force, this is quite a job. So we talked some really good people into participating in this. So the key questions are, what are the time and cost scales of the R&D and associated test facilities, as well as the time and cost scale of the facility? That was one of our initial questions for AF. There are a lot of options on the table, as you saw, and they all have to be evaluated and compared in some even-handed way, which is quite a challenge. We have large circumference electron rings, large circumference hadron rings, ERLs, muon colliders, gamma gamma, the ILC. We need to compare the expected costs, and everybody uses different accounting rules. Look at the schedule, R&D status, and so on. And we have these people here that are involved in that. Thomas Roser at Brookhaven is the chair of this. And right now we're trying to develop metrics and a process to facilitate the comparison between these projects of different maturities. So in order to keep it as doable as possible, we're focusing on HEP colliders. So the charge is develop the metrics, compare the project's cost, schedule, timeline, technical risks, operating cost, environmental impact. One of the things we're seeing is site power is a big driver in some of these. Select the accelerator projects to be evaluated. These will be provided by the topical groups in the accelerator frontier. Work with the proponents to evaluate them against the metrics. Consider the ultimate limits of various types of colliders. Consider the limits and timescales due to accelerator technology for various types of colliders. Lead the evaluation of the different HEP accelerator proposals and inform and communicate with SNOMAS, the different frontiers, energy, neutrino, and theory, and document all these metrics and processes and write a conclusion. So here is what we've received so far that we have to evaluate. We have 8 proposals or concepts for Higgs factories, CEPC, CLIC, an ERL, Collider, FCCEE, Gamma Gamma, ILC, LHEC, and a muon collider Higgs factory. And then we have 18 high energy collider concepts or proposals. A lot of these I showed you before, ranging from a normal conducting cryo-cooled copper linac to a collider in the sea, which is a large ring that's floating in the Gulf of Mexico. Now that's going to be an interesting challenge to evaluate. So we have our work cut out for us. Now the Muon Collider Forum was established to help provide input to the SNOMAS process. So this is a joint effort between the energy frontier, accelerator frontier, theory, and intensity frontier. And it's really driven by aspirations for an energy frontier facility in the US. This seems to be the only thing that's being talked about right now that would explore the energy frontier on US soil at least. So this is starting out, is based on the successful US Muon Accelerator Program MAP that ended in 2016. That was right after the last strategic planning process, which essentially killed the Muon Collider work at that point. And then CERN has led a new initiative in Europe. So they're working together very closely to come up with a concept for a Muon Collider. Now, the European planning, which always just precedes a SNOMAS process, came out with a couple of things here that I want to mention. This is their strategy for particle physics in Europe. They formed this laboratory directors group chaired by Lenny Rivkin. The immediate outcome was that to form an accelerator R&D task force reporting to this group and the CERN Council. And they listed what the most promising accelerator R&D activities for HEP would be. So here's what they've targeted: high field magnets. And we're in the process right now in the US of writing an MOU so that our magnet program can work with the European high field magnet program that's being organized. High gradient acceleration, high gradient RF structures, muon beams, energy recovery linacs. So this is what the European strategy came out with. And of course, that obviously factors into SNOMAS and the P5 process. And we do have participants that are active on all these laboratory directors group panels. So it's as integrated as we can make it. Now, they're taking pretty bold steps toward a Muon Collider in Europe. There's an international design study underway right now. and they're going to come up with a cost estimate in the not too distant future. So in addition to high field magnets, which play a large role in realizing a muon collider, it's going to be a unique opportunity to achieve a multi-TeV energy beyond the reach of E+ E- colliders. And one of the other potential advantages is it can be much more compact than for a hadron collider. So, but the biggest challenge remains that to produce an intense beam of cooled muons. But there are new ideas that are being explored for this area. So there's an ongoing effort to build a real collaboration here. Daniel Schulte is an interim project leader. Nadia Pastroni and Lenny Rivkin are co-leaders. They had a kickoff meeting in July, and they had over 250 participants, and you can find more information at this Indigo site here. Oops, frozen. Okay, there we go. All right, and this word on the physics limits of ultimate beams. They held 4 different workshops on the topic of physics limits of ultimate beams to find out, what physics limits are there on the ideas that people would have. So we're looking particularly at colliders. We like to understand the required luminosity scaling with energy. Luminosity, of course, figures prominently in all these concepts. What goes on at the interaction region that can disrupt the luminosity and so on. And the potential feasibility of advanced concepts towards ultimate physics limits, such as PeV beams with low luminosity, for instance. All right, so in summary, obviously times have been difficult. It resulted in a delay of the whole process, which sort of driven by the fact that the projects weren't moving very quickly forward either. All the meetings and workshops so far have been virtual. We're still hoping that in July next year, we'll have a face-to-face, and that's very important to us. We have still challenges to deal with the uncertainty in 2021 and 22. But in spite of all this, the community has really come together with a lot of Zoom meetings, a lot of interactions. So huge thanks to all of them. And we really appreciate the community's continued strong participation in the process. And I want to point out and emphasize that we very much welcome the international accelerator community. Please join us. Feel free to submit white papers. And you can find more information at the wiki page here, or just go to snowmass21.org and you'll see the whole thing, and you can page through all of that stuff. So with that, we very much look forward to a productive snowmass study, and thank you very much.
Thanks a lot. I think it was very helpful, in particular for the European or for non-US community, also like me, to understand really the procedure, because we participate in the initiative. So we are preparing the white papers together with our colleagues from different countries, but you never know really the whole flow. So thanks a lot for
yeah, you don't know what we're going to do with them.
Right. Are there any questions? I don't see any. Can I maybe ask one? On your slide with the list of the accelerators.
Yes.
I don't remember which number of the slide, or it was not. Yeah, exactly, the previous one. Yeah, right. May I ask if the facilities are ordered in the order of preference, or
no,
just alphabetically?
No, that would be a big mistake on our part to prioritize anything.
Okay, just to understand for me and my colleagues from Europe, do you advise DOE, or basically you can speak out the recommendation?
Okay, well, SNOMAS itself is non-advisory. We just take input from people like you and others who have ideas, and we try to document these ideas in a coherent way, and then pass that to the P5 panel. And they will do the prioritization.
I see.
So, you know, we're very agnostic when it comes to priorities. And then DOE will take that. They may have another couple of panels that focus more on, say, on the accelerator side or something else, and they will alter their program and priorities according to that.
Okay, thanks a lot. So I wish you a successful next SNOMAS procedure 21.
Thank you.
Okay, now we are moving back to kind of a daily physics. And now we have the talk by Miguel Romao on deep learning models in the searches at colliders.
Hello, thank you very much. Let me just share the screen. Wait. After all this time, it's still confusing. Okay.
No.
I will assume that everyone can see and everything and hear me correctly. Otherwise,
yes,
just
there's some
stop
black
me.
boxes, at least on my screen.
Yes, it's the Zoom.
I see. It's the Zoom Windows. Okay.
Yeah.
If you go maybe to the full screen mode.
Yeah.
Yes, right. Perfect. Thanks.
Oh, fine. Perfect. Okay. And before I start, I would like to thank the organizers for having invited me and giving me the opportunity to talk about some of the most exciting aspects of application of machine learning nowadays, and which is using deep learning to search for new physics at colliders. So one of the main goals of the LHC and basically any other collider, I think we all will agree, which is to look for new physics. So what normally you do, the current workflow is that you have a beyond the standard model signal hypothesis that you're looking for. You then study the signal and you try to anticipate what are the backgrounds that will be draining the signal, and you try to find what the best kinematic regions and the final state topologies to look for such signal. Then you collect the data at experiments, and eventually you do perform some type of statistical tests to test that hypothesis is present or not in the data. And then if you're lucky, you'll profit, you'll find something, you get a Nobel Prize, or at least wait 50 years to get the Nobel Prize. So this workflow has a lot of challenges. And nowadays it's quite different from older accelerators or experiments, because, for example, at the LHC, we have what it's called a multivariate analysis. So when you collect data, you don't have only, for example, invariant masses or simple systems. Your low level data is actually like a collection of kinematic variables like masses, transverse momenta, eta, phi, coordinates in the detector, multiplicities, B tags, scalar energies, missing transverse energies. I mean, if you put all of this together, an event will be characterized virtually by tens of variables. So it comes to the question, which is, what is the best variable to find new physics? So what is the most discriminant variable? And so this has already been mitigated by what it's called supervised machine learning. So you train what it's called a machine learning classifier, which is trying to differentiate between that signal hypothesis from the background. So this can be neural networks, it can be deep learning, but the very common used methodology is also gradient boost trees, which will turn all of these variables into a single variable, which is the output of these discriminants, which tend to be interpreted as a probability of a certain event being of the class signal as opposed to the class background. And then you can perform statistical tests on the output of this classifier itself instead of using one of the kinematic variables. And you also have the question, which is, what is the best signal region for these variables? I mean, if you start varying the physical parameters of the theory, your signal might elude your analysis, because, for example, if you take the mass of a new resonance too low, it might not be able to decay into, for example, a B quark. Your analysis was focusing on trying to isolate. So there are many challengings, and there's one that always upsets theorists, and I'm a theorist myself, so I'm very sensitive to this problem, which is, what if there is another type of new physics in the signal instead of the hypothesis that we're looking for? Or even worse, are we forgetting something? I mean, nowadays we do have extensive searches for supersymmetry, vector-like quarks, and the more common types of BSM signals. But what if we're actually forgetting something that can be in the data and is being ignored by our dedicated analysis? So this is something that I know that a lot of theorists have an issue with. And so we went on trying to understand how can you miss or catch things. So our first paper on descent was, it was very simple and conceptually. So we had some neural networks that were trained to differentiate between specific signals, and then we fed these neural networks other signals. So we had a class, we had 3 classes of signals. So we had an FCNC perturb Z coupling. So basically we use a standard model Z, but we gave it like an effective coupling that would induce an FCNC in the top quark coupling, which is very difficult to find because it is kinematically very similar to the standard model. But then we had some more exotic signals that we wanted to try out. For example, heavy vector-like quarks produced through the standard model gluon, or even through an heavy gluon. In here, heavy gluon has the interpretation of a heavy octet boson, which can be scalar, which sometimes comes from composite Higgs type of problems. And so try to answer one of the questions, which is what if other new physics is in the data, and how sensitive will be these discriminants to varying parameters of the theory? And we went out searching. So the analogous here is that you normally, when you're looking for new physics, you have a very explicit BSM candidate. So this is the hypothesis under which you're going to perform the statistical test. So in this example, you would be looking, for example, a monkey in the jungle, and the jungle would be the standard model. What if instead of the monkey, you have Pink Panther? I mean, in principle, Pink Panther is sufficiently different from trees to be found, but is this the actual case for deep learning classifiers? So each signal, we trained a supervised classifier for that signal alone, and then we just basically did all the pairwise combinations of training versus being passed another type of signal. And then in the end, we tried to understand how the sensitivity to a physics which was not the physics that you were training on can deteriorate or not. And we performed then upper limits on the cross section, what it's called the mu upper limits. So for our more or less surprise, we found out that even when you train on a signal which is very different from another, for example, the FCNC, you can still pick up, for example, signals which are kinematically very different. For example, these vector-like quarks produced through a standard model or a heavy gluon per production. But also, even the other way around is also true. So if you train it on something which is very different from the standard model, like these vector-like quark productions, you can still find BSM physics, which is quite similar to the standard model background, which would be the case of these FCNC model that we used. So this was quite positive, and then we computed during the CLS method, we computed upper limits on the signals using all these pairwise combinations of discriminants explicitly training on the signal and then testing on the signal, and we found that up to a deterioration of around an order of magnitude, you will still be able to find any of the signals that we considered, even with the discriminant, the classifier that was trained on any other signal. So we were quite surprised about this result, but this is not, you can imagine that conceptually, this is really not how you would look for a very generic type of physics, because you're still training these things on specific BSM hypotheses. So the next obvious step is, can't we just have something that learns what the jungle is, what the standard model is, and tries to identify what new physics can be? So this is what we then set out to be, and this is, in my modest opinion, what is the most interesting aspect of these newer deep learning applications, such as for new physics at colliders, but also at other experiments, which is we'll try to find new physics without committing to any hypothesis of the BSM candidate. So this has exploded for the past 2-3 years. I can't provide a complete review of everything that has been done so far, but there is a growing interest in these applications. In the machine learning community, this is called anomaly detection. So anomaly detection is you do train something on events or on points that you think they are normal, and then you would expect that this model will then output a probability or some type of number, some type of discriminant, some type of new variable that will be indicative if an event can be anomalous or not, and then you would then perform a statistical test on the output of this anomaly detection model. I highly recommend going to the live review of machine learning application in energy physics nowadays. So this is curated by CERN's Inter-Experiment Machine Learning Work Group, and they have this GitHub, and it's like an ongoing live review of everything, all machine learning applications divided by subsections of types of application, from theory to experiment to data generation to search for new physics. Is a very, very good resource to get into, to start doing, for example, to start writing the literature review of your paper. So we then went on to explore some of these models. And so I'm going to obviously focus on the work that we have done, but there are other approaches to this type of logic using machine learning and deep learning. So I'm going to focus on the ones that we did. So we use the same signals as before, so 3 classes of signals, where in the VLQ cases we vary, as before, I didn't say that, but in the VLQ case, we vary the masses of the VLQ. So that was the difference for the 6 VLQ cases, is that 3 of them were standard model produced, the other 3 were heavy blown produced, and those 3 are 3 different values for the vector-like quarks. And then we went on to explore 4 different anomaly detection algorithms. So an autoencoder, which is a deep neural network, so it is a deep SVDD. So I'm going to focus on these 2. I have backup slides for the isolation force and histogram-based anomaly detection, which are not deep learning based, and so I decided to not give so much focus on this talk. So what is an autoencoder? So in general, a deep neural network is nothing else than a function. So it's just a map that you give it an input, and then at the end of it, after push forwarding through different layers, you're just going to have an output. Each layer is just nothing else than a collection of fine transformations of the input. So basically a weight times the input plus a bias term, and then it goes through some non-linear function, for example, a hyperbolic tangent, but you can have others more complicated, and etc. In the end, a neural network is able to represent a nonlinear function, and there are universal approximation theories for neural networks. That neural networks, under certain constraints, can approximate any continuous function which is differentiable in almost every point. So an autoencoder is an architecture where you pass in the data through to the first layers, and then it tries to embed into a smaller dimensional space. So one of these layers will compress the data into a lower dimensional space, and then it will decompress again, and it will try to reconstruct. So the point is, try to compress it into this lower dimensional space, which is called the latent space, and then reconstruct it back, and we're going to train the neural networks to do this. So the idea is that the most relevant relations in the variables will have to be learned in order to encode efficiently to this low dimensional space, and then to uncompact it again. And so in principle, relations which are not as common will then provide a bigger reconstruction error. And so the idea is that you'll train a neural network on how to compress and decompress, or to reconstruct. So we use a reconstruction error as like the training objective. And so the idea is that in principle, the events which are easy to reconstruct and are most common, or at least that carry the most common relations between the variables, will be easier to reconstruct, so they'll have a lower reconstruction error. And so this reconstruction error can then be taken as a proxy for an anomaly, or on the other hand, to be our new discriminant variable to try to find new physics. Then we also developed what is called the deep SVDD. SVDD stands for support vector data discrimination. So support vector discrimination is it's a more of a classic machine learning algorithm. So this is a deep learning version of this. So it's almost the same, but you don't have the decoder. And so the idea is that here you are only trying to project the data into this lower dimensional space. But what is the criterion? So the idea is like this: before any training, and so the neural network has been initialized randomly, so the weights which have not been trained are random. So it is just a map from whatever space of the data into this lower dimensional space. You pass all your training data and you compute the mean. So this basically will give you a notion of where the mode of this distribution is. And then you will train the neural network in order to try to compress all the points towards that center of mass, towards the mode. So the training here will be to try to minimize the average distance of all the points in your training data set, into this point. What it is interesting, and it has been proven by the people that wrote the initial paper on this, is that you can then prove that the distance to the distance that the point has to the center of mass, it's actually associated to quantiles of a likelihood. So the DPSVDD actually becomes a parametric representation of the likelihood of your data. And so when you have likelihoods, you can then perform statistical tests on this variable, which would then be the distance to see, which is a proxy to the likelihood of a point. So the main point here, which is very important to point out, is that this is only trained on standard model events. So all the train is only on standard model background. So we want to call every standard model process as being normal. And so the idea is that in principle, and hopefully this is what's going to happen, any BSM process that you pass through this will then have, in principle, higher anomaly score, either a higher reconstruction error or a higher distance to that centroid C. And we want to discuss how these different algorithms compare to each other, if they are specifically more sensitive to any other, if they are correlated, and etc. And in fact, they are not all created equal. So this is one of our first most striking results, is that we find out, for example, that DPSVDD is very uncorrelated to all the other methods that we use. And so, for example, using the background data, and we defined here what we have called outliers. And outliers are basically the 5% points that have the highest anomaly score. And we'll then try to find out through all the kinematic variables where these outliers would be lying on. And you can see that, for example, DPSVDD and the autoencoder are identifying outliers in a very different way. So this is our first result, which is we have to be careful in using all of these methods, because these methods were not all created equal, and different methods will be in principle sensitive to different types of physics. And this requires a little bit more work in trying to understand when to apply which methods. However, the second part was they do find new physics, or going back to the jungle and the animal analogy, they will be able to find animals if they're only trained on trees. So you can see that, for example, here, these are the outputs of the methods. And so these, the higher the value, the more anomalous or the rarer is an event in principle. And you can see that all the BSM samples are shifted to the right. So on average, the new physics have higher anomaly scores. So the first hypothesis, which is, can these things provide a discriminant for new physics, at least by eye? You can say, yes, some better than others. So you can see, for example, that the FCNC, being very similar to the standard model, does not look like an anomaly for most of, for 3 of the anomaly detection algorithms. But for here, for example, for DPSVDD, you can see the distribution of the FCNC is indeed different, and it is shifted to the right and after the standard model, which is the gray one. So this, in principle, can work even for cases where are very, very similar to the standard model. One thing is seeing it by eye, another completely different thing is numbers. So we then again produced computed mu, so an upper bound on the expected cross section for these models, and then we compare it to a supervised method. So in principle, a supervised method is going to be better than a non-supervised method, so it's a generic method, because it will be trained on very specific, beyond the standard model cases. So in principle, we'll learn better how to differentiate that beyond the standard model physics from standard model background. So there is an obvious degradation. Here, this is 0.6, which is smaller than 1. This is within the statistical error of the CLS method. But so, for example, you can see, for example, the autoencoder does not even go below 1 order of magnitude in deterioration, and in the DPSVDD as well does very well. Oh, I cut this. So this is FCNC. The first column is FCNC, and these are the VLQ. I don't remember much, but I think that the first 3 are the VLQ produced by the standard model heavy gluon, and the last 3 are produced by the standard model gluon, and the last 3 by the BSM heavy gluon. I'm sorry, when I was screenshotting the plots into this, I completely made this boo-boo. Okay, but so you can see that you can in fact use these things to look for new physics, and you can in fact expect sensitivity through these methods, which are not that much worse than the supervised ones. And this is actually quite a very exciting aspect of these results, which is can we start moving forward to an approach to such of new physics which is actually generic and does not require explicit hypothesis for select model physics. Of course, these are only preliminary results. When I say that these things have exploded for the past 2-3 years, this is mean that for the past 2-3 years, the low-hanging fruits have been being picked up by the community at large, but there's one thing which is picking up the low-hanging fruits, another thing it is to bring these ideas into production. So we now have a concerted effort into trying to produce more mature methodologies and approaches to use these algorithms in searches for new physics. So what we are working right now, so we are trying to systematically study when we can actually maximize the sensitivity of different anomaly detection methods. So there are still some hyperparameters of these methods that haven't been completely explored, not only by us, but by other members of the community. So we're trying to understand when there can be increased maximized sensitivity, if they can be complementary, if some will work better for some topologies than others, if data representation has a big impact on the sensitivity. So there are still many operational questions on how to actually deploy these things. We're also trying to do something else, which is we have a phenomenological work on a dark matter candidate BSM model where dark matter can be produced in relation to a monotop topology. And what we're going to try to do is we're going to try to produce a sensitivity analysis for this model, which is normal. In phenomenological studies, you try to produce also sensitivity analysis for your models. But we're going to try to do two things at the same time, which is we're going to provide a supervised analysis to try to convince experimentalist friends to, okay, you can look into this, but we're also going to provide the unsupervised one using these methods. And so in my mentality, my head, as a theorist and phenomenologist, I think it would be quite interesting for phenomenologists to actually start providing sensitivity analysis based on these methods, because then we might be able to convince experimentalists to start producing unsupervised analysis to compare to at least some likelihoods in unsupervised analysis. That could be quite interesting. So there's still a lot to understand on how different anomaly detection methods work better for different PSM models and etc. So we are very much aware of this. And there is a big elephant in the room in everything that I've said so far, which is when you produce a CLS method when you use a CLS method to produce an upper bound on the cross section of signals, that is an explicit hypothesis statistical test. So we would like to develop statistical tests that would not require that explicit hypothesis for a BSM signal. There's been some work in that. So there's this LHC Olympics for anomaly detection that has joined so far, and there's been like a working group paper last year or so, which already has some ideas on how to produce significances and p-values from the outputs of anomaly detection methods, but there's still no obvious consensus on how to approach this. And so this is also something that we would like to move forward with. So conclusions, take-home message. I hope I'm not over time. So I really hope that everyone is convinced right now that deep learning and neural networks are actually a very versatile tool to search for new physics, but also to search for new physics in a generic point of view. Not only supervised neural networks can still find out about other signals that they were not trained on. Deep learning provides a versatility in the architectures and in the problem formulation that will allow us to produce unsupervised architectures that can be generic new physics detectors. And so hopefully moving forward from now on in the community, this is something that we can get traction on and put some more work into actually bringing these ideas into production. We do hope that unsupervised methods, which are getting a lot of attention, can then bring this forward, but there is also a lot of work to be done. So we want to motivate phenomenologists and theorists to also start presenting unsupervised sensitivity analysis of their models, because I think it would be interesting to start converge on a common language on how we can give experimentalists a way of testing many models at once with the same outputs or with the same discriminant variable. But there are also a lot of systematic studies that have to be done in order to be able to deploy these methods confidently into production, so at experiment. So two of my main collaborators, Wout and Nuno, are members of the Atlas, and they are working also on the monotop search for new physics, and so they are quite involved right now in trying to bring these ideas into the experimental setting. And so there is a lot of symbiosis here between phenomenology, machine learning development, and also experimentalists. And so hopefully we'll be able to converge on some analysis which also uses this in Atlas in the foreseeable future. Thank you very much for the time.
Thanks a lot, Miguel. Yeah, indeed. I mean, you know that in the analysis, kind of in the daily life of experimentalists, we are using the methods of machine learning basically in all the analysis or in most of the analysis nowadays. However, indeed, I haven't seen yet any theory predictions where you really can involve it at the same time. In particular, for the indirect searches, would be important also to find the way of the training strategies, how to consider all the correlations. Because sometimes, I mean, you had these nice examples with the monkey or with the panther, but sometimes we're not looking either for a monkey or a panther, but something like an ant, you know, this fairy thing, which is kind of a the tree-like animals. So
exactly.
That is what we are looking for in the
direct
searches. In the indirect searches,
Yes.
so that is important that we could
Yes. Well, in a certain sense, maybe I shouldn't be more explicit than what I've presented here is more in the vein of direct searches, right? So, but in principle, one could bring this to the context of indirect searches and even beyond collider searches, right? So, in this conference, we have had a lot of neutrino talks, and it's also something that could be brought. Actually, we have collaborators that are working in SNO, and they're actually quite interested in start bringing these things to neutrinos as well. So we'll see.
Are there any further questions?
Wait, not back up. Just want to exit.
I don't see the raised hands. So Miguel, thanks a lot again for your very nice presentation. And we move to the talk by Shufang Su on the minimal supersymmetric model at future Higgs factories. So Shufang, can you? Yeah, great.
Yes.
Thanks a lot.
Yeah, can you see my slides and hear me?
Yes, I can see
Okay.
you, see the slides and hear you perfectly. Thanks.
Okay, thanks. Yeah, well, thanks organizer for the invitation. Today I'm going to talk about the minimum supersymmetric standard model at future Higgs factories. And for those of you who've been in the field for a while, think, okay, that's like ancient old ages, topic like MSSM. We have been studying that long before Higgs was discovered. And, and people have been develop all those machineries for MSSM Higgs property calculations years back. And so what we can actually add new here to look at MSSM again with the future Higgs factories. So that's basically what my talk is mostly going to cover. Very brief on the Higgs precision measurement, kind of just to give you a very big brush kind of, picture of where we're sitting in terms of Higgs precision measurement for future Higgs factories. And I'll talk about the global fit framework that we're using in our analysis. And the most part of my talk will be, given those precision measurement we have in the future, what can you say about MSSM parameter space? And you might think people have explored that to death. And actually, when we will start working on this project, we find, oh, it's actually not. People did, the Higgs glu and the Higgs gamma, and that's pretty much it. And the things we have all those tools ready, then why don't we put that into use? So that's basically what we did in our project. And I will mention the complementarity of this indirect precision measurement with the direct searches, and at the end we'll conclude. So what are the status for the Higgs precision measurement? We know that LHC, they did a great job in, try to measure the Higgs coupling strength. But given the LHC hadronic environment, you can mostly, probably approach 10, 20%, and some of them are even worse. Okay, and even by the end of the LHC the period. If you have the hydromer HCs, then you're probably, so the hydromer HCs is the red one over here. You're probably looking somewhere, a few percent to 5%, depending on which channel you're looking at. And but when you're really talking about Higgs factories with millions of Higgs can be produced, then you're looking at a complete different picture, because it's a laptop machine's background is much less, and you have ZH associated productions. So you can really look at different channels with high precisions. So this table here gives a summary of what the CEPC, which is the Chinese version of the circular machines, FCCEE is a European version of it, and also the RLC. RLC is a little bit special because they can go to higher energy, so there's certain measurements they can do much better. But if you look at the CEPC and FCCEE data, they're actually very, not data, the predicted precisions, they are actually very similar. The best they can do is H goes to BB, because that's the one with the largest branching ratios. So you can reach a precision of most, sub% levels. And then for most of them, like the WW channel, TOTO channels, and the CC channel, you can, and also the GLU, you can do 1 to 2%. In particular, for the GLU, which is a loop-induced processes, if you can do at percent level, which is really good. And then there are channels which, because of the suppressed, the branching ratio to the final state, then you can only approach like 4%-ish, for example, for on-shell Z with off-shell Z, or the gamma ones. And then, for the ones, the muons, they can't really do much because of suppression by the branching ratio over here. So that's kind of the generic picture. For certain channels, they can do it really, really well. But then for the one with reduced branching ratio, because it's statistically limited, then the precision is kind of still off. And oh yes, I do. Yeah, I did mention. So the one particular good for the H goes to GLU is that the standard model contribution coming at loop level, and the new physics contribution also come at loop level, which is comparable to the standard model contributions, which make this channel particularly sensitive to indirect approach for new physics beyond the standard models. And the same apply to H goes to gamma, but you can see I don't really mention H goes to gamma because of the experimental precision is kind of worse. So even though the new physics contribution is comparable, but because experimentally we couldn't really approach that channel well, so it's kind of less useful over here. And I did mention the RLC is slightly different, because RLC, they can approach higher Zenov mass energy, which allow you to use vector boson fusion channels. So that give you a very good determination of H to the pair of gauge boson couplings, in particular to the WW. They can do it at sub% level, and it's about almost a factor of 2 better than the CEPC and FCCEE over there. And because of this particular weak boson fusion channels, even for the dominant H goes to BB, they can do slightly better than the CEPC and FCCEE. So at the end of my talk, I will give a comparison between the reach of 3 different machines over there, and you can see that RLC in certain cases did it better than the CEPC and FCCEE. So that's kind of machine comparison over there. But let's go to the main part. So a little bit on the theory side, the Higgs sector in the MSSM is the usual type 2 Higgs doublet models. You have 2 Higgs doublet model, 2 Higgs doublets, each of them gets a valve, and then the neutral part mixed together. So you end after electroweak symmetry breaking, you end up with 2 CP even ones, 1 CP other ones, and pair of charge ones. So that's the usual story, same as the usual 2 HDMs. And as far as the coupling goes, one of them couple look really standard model-like, and the other one really looks really non-standard model-like as far as CP even Higgs goes. And the usual alignment limit people are talking about is for this particular parameter, cosine beta minus alpha is equals to 0. So the heavy ones does not couple to standard model, and the light ones is 4 strands coupled to the standard model. So for the rest of my talk, I will assume this light one is 125 GeV. So far for this slides, I have not made anything MSSM specific. It's like generic type 2 Higgs doublet models. What's special about MSSM is in the generic 2 Higgs doublet models, all the quartic couplings are random. So all the mass for those Higgses they are basically random parameter, input parameter, model parameter, if you think. But in the MSSM, the quartic couplings, it's not random. They're related to the gauge coupling over there, which actually provide certain mass relations between the mass of those particles. So I gave the 2x2 mass matrix for the CP even ones over there. The one for the first part is a tree level coupling contributions, and then the one for the second part with all those deltas are the loop contributions. And in the MSSM, loop contribution is also super important comparing to the usual type 2 Higgs double models. So one thing is, for the tree level, all the masses are really controlled by two parameters. One is MA, the CPR, the Higgs mass, and the other one is our usual tangent beta. So that is very different from the usual type 2 Higgs double models, because there it's completely random. Here it's only two parameter controls everything. And the second part is, as I mentioned, loop contribution is super important, and the dominant loop contribution coming from the stop sectors, because the top Yukawa coupling is the largest. So there we introduced two new parameters. One is so-called M-SUSY, which is like soft SUSY breaking stop mass. And here I made an assumption, which is the left and right-hand ones have identical mass. And that is assumption. You can relax that, you just introduce one more parameters. But for the moment, we just want to see for the minimum set of parameters what we can do. So we just call both of them M-SUSY. XT is also super important in MSSM because that characterizes the left-right mixing in the stop sector, and that will give a large difference in the contribution to the Higgs mass, which I have it below here. So the parameters we are considering in our studies is MA, tangent beta, M-SUSY, and XT. Okay, so the first thing we need to consider is the Higgs mass is not a free parameter in the MSSM. It's being determined by those other parameters, but experimentally we know that it's 125 GeV, so you want to make sure that all the combination of the parameters does give you 125 GeV. So this is the first constraint that we need to put in. And fortunately for the Higgs mass, there are state-of-art software available which give you the complete one loop contributions, leading to loop contributions, even some of the 3 to 4 loop contributions. That's like the best we can do over here. And it's already available. So that's good. And if you look at the formalism, you can see that other than the tree levels, large loop contribution is needed, because one thing special about the MSSM, which is kind of well known, is that for the tree level, it's capped off at MZ. And we know what the MZ mass is, and it's nowhere close to 125. So you do need a large loop corrections to bump the Higgs mass up to 125 GeVs. And you can see here, the one I circled out, that's why the stop left-right mixing is so important over here, because it's basically directly proportional to this XT parameters. And the other thing we need to consider is, even though experimentally at Higgs factories, you can measure the Higgs mass super well, like, you know, tens of MeV and things like that. But for the MSSM, unfortunately, there are theoretical uncertainties in the Higgs mass prediction. The one from higher loops, the propagating error from the top quark mass and things like that. So the current uncertainty is about 3 GeV, but in the future it might improve. So I also show slides which shows the effect on the theoretical improvement on the delta MH, how that would affect the result in terms of approaching the parameter space. So Higgs mass is first thing. The second thing is the correction to the Higgs couplings, because we want to see how much contribution the MSSM sector is to the deviation of the standard model Higgs coupling to the standard model predictions over there. And we use the so-called alpha effective approach, which is basically we use a tree level formalism, but the alpha, which is the mixing angle between the CP even Higgs, we include the loop correction as well. So it's not the usual alpha. You can see it's called alpha effective, just because all the loop contributions are included, because loop contributions is important. A little bit special special is about HBB couplings. And in particular, because that's one of the best measured coupling that we have. So we need to be a little bit careful. So for the HBB couplings, other than alpha effective, we also look at the other loop corrections to the HBB couplings, which is parameterized by this so-called delta MB over here. So this is second ingredient. We will need to fit with all the standard model Higgs couplings. The third ingredient I already mentioned is this H glu-glu and H gamma-gamma. H gamma-gamma is less important in MSSM just because experimentally we cannot measure very well. But otherwise, I give some typical diagram here which contributes to the H glu-glu at SUSY. So the global fit we are doing is we do the chi-square, the usual minimum chi-square, but we have three ingredients. One is the Higgs mass and the Higgs coupling. The Higgs coupling is two-part. One is the usual Higgs coupling to all the fermions and gauge bosons, and the second set is H goes to glu in particular. So one major difference from our work with the previous work is, when the Higgs measurement result first coming out, the immediate thing that comes to mind is, of course, those loop corrections. So the earlier work is mostly focused on the SUSY contribution to the H goes to glu or H goes to gamma, and see how well we can approach that. And we actually put all of them together, not just those loop level, also the tree level, and also the Higgs mass, and they do play an important role over there. So given that, we can do a global fit with the chosen pyramid range, which I have over here. So this is a busy slide, but this is basically the meat of what our analysis is. So let me walk through them one by one. Let's first look at the top left one. So the different columns, the first column is the fitting result, just consider Higgs mass. The second column is the fitting result, just consider H glu-glu couplings, H glu-glu, H gamma-gamma. And the third column is the other tree level couplings. And the last column is everything combined together. So the last column is really a combination of first three. So let's look at the first three. For example, the top left one, that's for the large tangent beta, and the MA is about 1 TeV. And the different color, basically the darker the color, the colder the color goes, like the black or the dark blue, those are the favored regions. And the warmer, the hotter the color goes, those are the disfavored regions over there. So for example, if you look at the Higgs mass, this is actually consistent with our usual understanding when so the x-axis is the stop mass, and the y-axis is stop mixing parameters, xt. So this arrow here is zero mixing, xt goes to 0. So you can see that for the zero mixing, you prefer M-SUSY to be relatively large, because otherwise you cannot bump it above 125 GeV. And then there's also another two branches over here. You can see one is on the top triangle over there. The one is in the lower branch. And those are so-called maximum mixing cases where xt over M-SUSY is roughly about 6. And there you can accommodate a relatively small M-SUSY. So you can see the blue region kind of goes like that. It's kind of like a triangle branch over there. So those are the usual stories as far as the Higgs mass is concerned. And as far as the large tangent beta goes, if you compare the first one with the second one, with the one in the middle, the MA is 2 TeV, they are roughly about the same, okay? So as long as the large tangent beta cases, you're either in this horizontal branch or you're in this kind of diagonal triangle branches. But you can see the story almost completely changes for the small tangent beta. So the lower bottom is for tangent beta equals to 3. And you can see that the xt equals to 0 is completely gone. Okay, the reason is for tangent beta equals to 3, the tree level contribution to Higgs is small. You really need a super big loop contributions to bump everything up to 125 GeV. And that can only be achieved in the maximum mixing cases. So you only have the top and the bottom left over there. And top one is slightly preferred given the high loop contributions. So that's kind of the Higgs mass story. The one in the middle is the loop contribution to H glu and H gamma gamma. And you can see that they are not super sensitive to tangent beta or the value of MA. The three plot pretty much look the same. And other than, the XT, other than the top left blank region and the lower left blank region. So basically, small m SUSY is not favored because small m SUSY basically make the loop contribution to be too big. Then you have too much deviation, which you don't like. But otherwise, as long as m SUSY is big, you are in this big, blue-black region, which is good. And then the third column is for the tree level deviation to the tree level couplings over here. And here you can see the small MA is very different for the large MA. Small MA has a super strong constraints from the H goes to BB. And that's because when the MA is small, the loop contribution is too big. You have too big deviation, then you're not good over here. So you're only good in the single slice. But once the MA is big, the loop contribution is reduced, then you open up big regions. So that basically characterizes the main features in terms of the physics goals. And then the last one is a combination for all three of them. But you can see because of different 10 beta, different MAs, then you have very different features. For the large 10 beta, small MA, only this teeny tiny little region on the top slice is left. Large 10 beta, but large MA, you have big window open. But small 10 beta, because of the Higgs mass constraints, then you're in this top and the bottom corner over there, kind of. So that's kind of the main conclusion for our results. The rest is basically you projected that into different parameter space. But it's still kind of useful because I want to point you guys to the last kind of presented results. So this is the same as previous one. X-axis is m SUSY, y-axis is xt, and kind of do it in a different combination of the benchmarks we're doing. So this is the large 10 beta region, same as I mentioned earlier. And this is for the slightly bigger MA where the HBB constraint is not that big. You can see you can extend it to a 10 beta, about 10. And for the large MA 2 TeV, then the constraint is the most relaxed. So all I'm showing is 95% confidence level allowed region over there. So let me show you some other combination of parameter space just so that you will see how it looks like. So this is in the MA, the CPR, the Higgs mass versus the stop mass planes over there. Then I typically present things in the zero mixing and the maximum mixing cases. So you can see that zero mixing gives much stronger constraint. Basically everything above those contour lines are allowed, everything below is excluded. So for example, for this case, for the small 10 beta, then you only allowed to have really large MA, really large M SUSY, and the dominant constraint is from Higgs mass, as I mentioned. For 10 beta equals to 5, you need huge SUSY contributions, loop contribution to bump up the Higgs mass. But once you relax, make 10 beta bigger, then you have large parameter space available over here. And once we go to the maximum mixing cases where xt is equals to 2 times M SUSY, then you can see the 10 beta lines basically coming down. Even for 10 beta equals to 3, the constraints on the MA and the M SUSY is much less over there. And similarly, 10 beta gets to bigger, then you allow large regions available. But you can see an interesting behavior that the curve, for example, 10 beta equals to 50, is start to curving back, which means even large M SUSY become unavailable over there. And that's because for the maximum mixing cases, actually you are not allowed to have too large M SUSY because otherwise the correction to Higgs mass is too big. So for example, if I flash you back, that's basically corresponding to this corner over here. Okay, when M SUSY gets too big, then the Higgs mass is above 125, which is also not good. So it's like everything kind of comes together. Let me show you this one. This is often presented one in the MA 10 beta plane. That's like pretty much the most favorite parameter space people like to show for the MSSM in the Higgs sector, which is MA and the 10 beta. Okay, so the grayish region is the current LHC direct search. It's basically looking for A goes to tau and H goes to tau. So because of its tau channel, so the large 10 beta, you have enhanced reach over here, which is a gray region. So this plot nicely shows the complementarity between direct search and indirect search. So for the indirect search, basically you would exclude out the the small MA regions over here by different curves. So it will explore. So the main message I want you to take from this plot is the indirect search will explore large parameter space, which is not covered by the direct searches over here. And the plot down here, I just show, the high room LHC, what are the direct search goals. Basically, all the colored regions are the region that will be covered by the direct search. But you can see that this so-called wedge region, the white region is still open, even at high room LHC, but then those would be the region that could be covered by the precision measurement. So there's really complementarity over here. Given the time, I actually will skip those slides, but I do want to show you this one over here, as I mentioned. This one basically shows for the theoretical predictions for the Higgs mass. If I do the uncertainty as 1 GeV versus 2 GeV versus 3 GeV, how much impact it would be in terms of approaching the parameter space. So the solid one is the current one I'm using, 3 GeV, which is the current status. But say in the future, I can do it 2 GeV, which is dashed curve. So everything below the curve will be not favored. Everything above the curve are still allowed. So you can see if I just do, 1 GeV improvement over here, it will help you. It wouldn't do much for the MA, but it will really help you in approaching M-SUSY. And if you can reduce it further to 1 GeV over here, then you improve the reach in M-SUSY even better. So the theoretical, so this one here, it's really limited by the theoretical approach, theoretical calculations, because Higgs mass can be measured very, very well experimentally. So here is where the theoretical calculations need to really, catch up over here. And just with 1 GeV improvement, you can improve a lot in terms of the sensitivities. And for those of you who are interested in looking at the comparison between CEPC, FCCEE, and ILC, this is the plot. Okay, so the solid one is CEPC. The dashed one is, the dotted one is FCCEE, and then the dashed ones is RLC. So the generic feature you can find out here is, except very few places, otherwise, the FCCEE and the CEPC is mostly comparable. Their reach is very similar. The machine is very similar as well. I mean, no surprise. Their expected precisions are very close to each other. But on the other hand, RLC, because they can run at higher center of mass energies, they can do slightly better measurement for HWW and also HB, slightly better for HBB over there, given the vector boson fusion. So the dashed curve usually have better sensitivities than the other two curves, which means RLC, typically they set better limit on the MA over here. Not much on M-SUSY, but definitely on the MAs over here. And yes, given the time, let me actually conclude. So the Higgs factory would reach really, really impressive precisions, both in terms of mass and the couplings. And in terms of the reach for the MSSM, the mass for the experimental precision, they are way better than the theoretical predictions. So the theoretical predictions on the MH is actually what need to be improved over there. Okay, so for the small tangent beta, the Higgs mass play an important role in constraining the parameter space, but otherwise, for the small MA, is the Higgs tree level couplings play an important role over there. Those loop things, H group in particular, does constrain the heavy SUSY particle masses. And the MA in particular, they are mostly constrained by the Higgs couplings, while the tangent beta, M-SUSY, XT, they are more sensitive to the Higgs mass over there. And as I already mentioned, the theoretical calculation for Higgs mass is super, super important here because the experimental precision is tiny, And if I compare three machines, most of them I would say comparable. RLC can do slightly better because of the vector boson fusion processes, and the indirect, direct measurement, they are really complementary to each other. Thank you very much.
Thanks a lot, Shufang. Are there any questions? As far as people still maybe formulating the question, may I ask you one question? You said it many times that the theoretical uncertainty in the Higgs mass have to be improved.
Yes.
What is actually limiting the calculation?
So there are two things over here. One is basically the higher loop contributions, okay? Because those, for the moment, the one loop is completely done. The dominating two loop is done, but then there's also subdominating two. I think the two loop, the dominating one that's done are the one coming from the Yukawas and the QCD contributions and things like that. And then there are 3 and 4 loops, which is not complete. And those, the higher loop contributions, I mean, Sven Heinemeier is really the expert. We're using fine Higgs. Sorry, I forgot to mention that. And those, if they can, put in the higher loop contributions over there, then that will reducing that. The another one is actually relatively easy to improve is a propagating error from the measurement, for example, top quark mass, just because, the top Yukawa coupling is big over here, which you get that from top quark mass. So if the top quark mass, we measure the top quark up to, say delta MT is 1 GeV. So it's literally 1-to-1 correspondence. If top quark mass can be measured up to 1 GeV, the propagating error into the Higgs mass is 1 GeV, literally. So if that can be reduced, which hopefully will be reduced in the future, then that will reduce delta MH as well. So these are the kind of 2 dominating contribution factors.
Yes, right. In particular, I'm working on improving the top quark mass measurement.
Nice.
But
Yeah,
I don't know. I mean,
yeah.
there are many problems also of the theory nature.
Yes.
What actually we do measure as top quark mass and so on.
Right. Yeah. So
Okay.
that would be super important. Yeah.
Thanks a lot again. I don't see any raised hands from the session. So thanks a lot. And we are moving now to the final presentation of today and of the conference by Bertrand Echnard from Caltech on searches for the hidden sector particles with Barbar.
Okay,
Bertrand, can you?
You should be able to hear
Yes,
me and
I
see my
see now your
screen.
screen,
Hopefully
right?
it will start. So, okay, that should be full screen.
Thanks a
Sorry.
lot. Okay.
Okay, so yeah, thank you for the invitation. It's a pleasure to be here today to discuss searches for hidden sector or dark sectors at Barbar and more generally B factories. So if you are not very familiar with dark sectors, they are simply new particles that don't couple directly to the standard model. But we will see in a minute that there are still indirect interactions between the 2 worlds via new mediators. They can be found in several BSM scenarios, so they are fairly well motivated, and they could have a fairly rich structure. The standard model, after all, is non-trivial, so there is no reason why a dark sector would be very simple. And we realized a few years ago that a dark sector at the MeV to GeV scale would have very interesting properties. It could obviously provide a light dark matter candidate, but also explain the CP anomaly, neutrino mass. And so all that motivates a fairly generic and broad exploration of these possibilities. So as I just said, there are a few indirect interactions that are allowed between the standard model and the hidden sector, what we usually call the portals. And you see on the left a list of the lowest dimensional portals. In this talk, we'll mostly focus on the vector 1, which introduces a new gauge boson, the A prime, usually called the dark photon, that can mix with the photon or the Z via kinetic mixing, and the scalar portal that also has a new dark scalar that can mix with the Higgs. And then there are many variations of the couplings you can play with to have slightly different scenarios. It turned out that B factories are actually well suited to study hidden sectors. There is a very well-defined initially plus or minus states. The detectors are usually fairly hermetic and provide a good coverage. So you have a good efficiency for reconstructing missing energy, secondary vertices, and you can also study low multiplicity events. And so all that allows you to probe a wide variety of signatures in the GeV range, really complementing other techniques and approaches. And that's essentially what we did at Barbar over the last decade, conducting a fairly extensive dark sector search program. You see on the left measurements, a wide selection of measurements that have been performed. There are still a few that we are working on and should be published hopefully very soon. And in this talk, I will basically go over some of those results. Before doing that, let me just remind you that BABA was a detector that collected around half an inverse autobahn at the upsilon 4s and also a little bit at the 3s and the 2s in the early 2000s. And you see on the right a picture of the detector when it was still there, fairly compact by today's standards. And so it's still kind of a little bit amazing that we are still active and doing analysis more than 10 years after data taking ended. So let me start discussing a few of the older results. First, searching for a dark photon, one of the simplest cases you could do. And you could search for that in the ISR process, E plus E minus going to gamma A prime, and then this A prime could decay to a pair of leptons on the left, or decay invisibly on the right. And you see that at the time we didn't find anything and could set bounds on the kinetic mixing, already exploring a large fraction of the allowed parameter space. Well, the story doesn't stop here. There has been many more measurements since then, and you see at the bottom the current picture together with projections for future measurements. So you see there is really a worldwide program to further explore these possibilities. And new results should be coming in the near future. As I said, then you can play a little bit with the couplings to produce new scenarios by gauging accidental symmetries of the standard model or individual flavor number. And you see right what happens to those constraints when you do that for different type of models. If you couple to B minus L, if you have a leptophobic B boson, for example, or a protophobic model. And the bottom line is that the constraint can be significantly weakened depending on the model. So you really need multiple measurements in electrons and protons to cover all your bases. Moving to something slightly more exotic, muonic dark force, which is simply a new force that would only couple to the second and third generation of leptons that introduce a new gauge boson Z prime. And such a force could actually explain some anomalies in the muon sector, G-2 being the most famous, also the photon radius puzzle, and could also explain dark matter as a sterile neutrino. So you can derive some constraint on that scenario from neutrino physics, and you see on the right the red curve here as a constraint, but it's kind of only an indirect probe of the Z prime. Turns out that at BABA we could search for that. Via this Z stratum process, you first produce a pair of mu's, and then one of the mu emits a Z prime that will then decay into another pair of muons. So you have 4 mu final states. We did search for that, we didn't find any signal, and then we could set limits on the Z prime coupling for visible decays. You see slightly better than the neutrino constraint, and chipping away a little bit more of this G-2 favored region. There is still a region here that is allowed, in which the Z prime would decay invisibly, and BEL2 gave it at first stab with a small amount of data. So you see that's the preferred region, and then the limits is still very early in the game for BEL2, so hopefully they will be able to probe more parameter space with more data. Let me now turn to the dark scalar. And here, one of the first analysis we did was searching for a dark Higgs boson, which could be added to the dark sector if the dark photon mass would be generated via the Higgs mechanism. In that case, you could produce one of those dark Higgs bosons via the Higgs stratum process. You have an off-shell A prime here that will emit an Higgs boson and then become on-shell. The interesting point is that this process is not only sensitive to the kinetic mixing, but also to the dark sector structure constant here, G dark. And so that gives you a bit more information if you were to observe something. The Higgs decay topology really depends on the mass scale. If it's heavy enough, it will then decay into a pair of dark photons promptly. If it's not, it will mostly decay invisibly. And so at BABA, we did a search, BABA and Bell actually, we did searches for visible decays of that dark Higgs. So the final state would include 3 dark photons, and then those would decay into, so be reconstructed, so into a pair of leptons or pions. Chloe did a search for invisible decays at potential 2. So we didn't observe any signal, and then we could set limits on the product of alpha dark and epsilon square. Bell also did that search, and since it's essentially background free, they could obtain slightly better limits because they have slightly more luminosity. And you see you can probe values down to 10⁻⁹s or even up a few 10⁻⁻⁻. And if you assume that alpha dark is equals to alpha EM, 1/137, then the limits on the kinetic mixing are slightly better than what you would get from direct production, even though it's a bit more model independent, of course. But more generally, you could also search for a light gauge singlet that could directly mix with the Higgs boson. Turns out that a light gauge singlet is already fairly constrained from flavor changing neutral current measurements in PDKs, unless that boson would couple mainly to leptons rather than quarks, and then you could escape the constraints. And that scenario could also, that leptophilic scalar could also explain the G-2 anomaly and the recent Koto excess. So that's all interesting. And in that scenario, the mass, the coupling is obviously proportional to the mass, which implies that the scalar is preferentially produced via its coupling to the tau, and then it would decay to the most massive lepton pair that is accessible. And so the strategy to look for that new particle was basically to first produce a pair of tau, you can see here, and then one of the tau will emit that phi that would then decay into a pair of electrons or muons, depending on its mass. So that's essentially what you're looking for, a final state with 2 taus. We just look at all 1-prong decays of the tau, and then a phi that would produce a resonance in the lepton spectrum. Train a few BDT to increase the signal purity, and one of the interesting features of this analysis is that for sufficiently light phi and low values of the coupling constant, that phi could become long-lived, and so you need to take into account the fact that it could produce displaced vertices. And so that shows the final dimuon spectrum we have, and then you simply just go bump hunting for resonance of that spectrum. We didn't find a bump, so we set limits on the cross section as a function of the dark photon lifetime. For both E's and U's, you see that sharp-wise, it's simply because above the Dito threshold, the phi is going to decay mostly into taus, and so the branching fraction to mu's really drops. And then you can transform those cross sections into limits on this coupling Xi here. And you can see, well, that's the light grain exclusion region here, that we have not only significantly improved the previous bounds, but we are also excluding almost all of the G-2 favored region below the Dito threshold. There is still this little triangular region here we haven't been able to explore, so hopefully Bell 2 will be able to do that with more data in the future. Let me now discuss briefly action-like particles in BDKs. So I suspect you all know what actions are. You might not be aware of the fact that most of the searches at low energy is really focused on the photon or gluon coupling, because the coupling to the W is obviously suppressed by G Fermi square, and it's much more difficult to access. But one of the tricks here is to use flavor changing neutral currents, which are also extremely suppressed in the standard model. So they offer a very good environment to probe that W axion coupling. In our case, we exploited the B sub S transition, looking for an ALP in B to K axion decay. And then that ALP would decay into a pair of photons via this triangular diagram coupling to the W. Once again, the axion, this ALP lifetime can become important and no masses at coupling. So you have to consider both the possibility that it could decay promptly or produce a displaced vertex. So the analysis is pretty straightforward. You just combined K-on with 2 photons to form a B candidate. Then we train BDTs to separate the signal from the background. That's the final spectrum of the 2 photon mass. So you see peaks from the pi0, eta, and eta prime, and those regions will be removed from our search. And then you essentially, once again, go bump hunting in that spectrum. There is a little bit of an eta C, but that we can estimate and remove. So we haven't excluded that region from the search. As you would guess, we haven't seen any significant signal. So we set upper limit on the production cross-section, once again, from prompt and non-zero lifetime. And then we turn those limits into bounds on the coupling between this action-like particle and W. That's the dark region here. And you see an improvement up to 2 orders of magnitude over current bounds over a fairly large mass range, which dare I say is pretty impressive. Let me now give you a quick overview of the latest analysis we had, which was considering self-interacting dark matter in a minimum dark sector model. So in that scenario, you have a dark sector with a dark fermion that couples to the dark photon. And you simply crank up the fermion, dark photon coupling constant to fairly large values so that you could form dark fermion bound states that have been called darkonium. And so the 2 lowest energy bound states are usually denoted eta D, eta dark, and upsilon dark, in analogy with a standard model. And you could produce them both in those reactions, either by emitting an additional dark photon or a regular photon. But now that we could perform a search looking for this upsilon dark in E plus E minus to gamma upsilon dark. And then the upsilon dark would decay to 3 dark photons. And then we would reconstruct those dark photons either as pair of electrons, muons, or pions. Once again, the dark photon lifetime can be large for small values of the kinetic mixing and the mass. So you have to take into account these prompt and displaced vertex possibilities. The analysis here is also fairly straightforward. You're looking for 3 pairs of leptons or pions with 2 or more electrons or muons to reject a large QD background. And of course, those 3 dark photons should have similar masses. And then the mass recoiling against the upsilon dark should be compatible, with the photon hypothesis. We don't require the presence of the photon in the calorimeter, but if we do detect it, then it has to be compatible with this E plus E minus 2 gamma upsilon dark hypothesis. And then you essentially look at the bidimensional distribution of the dark photon mass versus dark epsilon mass for the final set of candidates, and you scan this plane searching for an excess. As you would guess, we didn't find one, and then we did set limits on the kinetic mixing for different values of alpha dark, epsilon mass of the epsilon dark, and mass of the dark photon. You get on the left a few examples of those type of limits. And you can see on the right that for large values of alpha dark and large values of epsilon dark masses, you can probe a fraction of the parameter space that has been unexplored so far. So this is essentially all the news I had to report on those dark sector searches. Before concluding, let me tell you that it's not the end at Bubble. We have still a few more analyses in the pipeline, searching for dark matter linked to biogenesis or searching for heavy neutral lepton. And as I said, there is always something new to search for. So if you have a good idea, let us know and we will see what we can do. I also wanted to mention that Bubble is only one of the many experiments that's involved in searching for dark sector particles. As you can see on those plots, I took them from the Physics Beyond Collider report a few years, 2 years ago now, that there is really a worldwide effort with many, many experiments searching for this type of particles. So let me conclude. I think you can read the conclusion, but let me just say that I think there are still really amazing possibilities at a GeV scale, and we now have a dedicated programs that are underway to explore them. So that's all I had to say for today, and thank you for your attention.
Thanks a lot, Bertrand. So are there any questions? Don't see any. Alexei, yes, please go ahead.
Hi, Bertrand, nice to see you.
Yeah, Alexei.
Can you go to page 22? So this diagram in the bottom is really wild. I mean, why do you need so many lepton pairs? Wouldn't it be enough to have just one for your absolute?
I think you need 3.
I mean, your V has quantum numbers of a photon, so you know, isn't that much easier just to have 1 instead of 3? So 3 is also, it works, right? I mean,
yeah, it works, yeah.
But
well,
you
so
know, one would also work.
One would also work, yeah. But I think from 1, it's basically then going back to the previous case where it's C plus E minus 2 gamma V. And then you can extract limit. Since we haven't seen anything, you can extract limit from that. Well, that one was an attempt to see if you could improve on the sensitivity by having 3 instead of 1, because then the background is much lower. Efficiency is lower, but the background is also much lower. So it's kind of a trade-off here.
But you also pay, you know, for each additional photon, right? I mean, because of the couplings. Anyways, we should talk about that at some point.
Yeah, but so you don't really pay, because the dark photon then has to decay into a pair of leptons. It cannot do anything else.
Well,
so the only pay you price is actually here when you have to turn the photon into a dark photon, but then the rest is basically free.
Right, except for, you know, if it's only one channel, the lifetime of this V can play a role. So basically, yes, it can just escape your detector.
Yes. So that what happened is that at the end of the day, our sensitivity is such that for very low masses, like below 10, 100, or 50 MeV, you start seeing a longer lifetime, but the lifetime is still small enough that it decays well inside the detector. You would really need to drill down to much lower values of epsilon to have a very long lifetime so that it would escape a detector. So we're still safe on that front.
All right, cool. Thank you.
Any further questions? Seems not to be the case. So thanks a lot, Bertrand, and I thank all the presenters in this session for fantastic talks. And I think now I give further to Alexander Studenikin to close the conference.
Okay, well, first of all, I would like to thank all the speakers of this final closing plenary session of the 20th Lomonosov conference, and also to the chairperson of this last session, Ekaterina Lipka. Indeed, the conference is arriving to its end, and we're working for 7 days, and I would like to thank all the conference participants, all the conference speakers and conveners. I would also like to thank our numerous colleagues all over the world who have provided a very important support for the event on the stage of the scientific program formation. And with a special feeling of gratitude to my young colleagues, my students and postgraduate students, for the tremendous work done since September 2020, I would like to open their faces to all of the conference participants. I am thankful to Vadim Shakhov, Maxim Velkov, Konstantin Stankevich, Fyodor Lazarev, Alexei Levchkunov, Georgy Donchenko, Artem Popov, and to my son Ivan. So, and this is the last announcement of the 20th Lomonosov conference. Well, I would like to invite all of you and all interested persons to participate in the next edition of the Lomonosov conference on the 21st Lomonosov conference on elementary particle physics that will be held here at the Moscow State University on August from 24 to 30, 2023. And I am sure that we shall meet face to face. Thank you very much for your participation, and I hope to meet everybody very, very soon at the next Lomonosov conference. Thank you very much. Ну и что? Кость, вы не включили.
Что я не включил? Все включено.
А нет, не звук не включен.
Все включено.
Ну, а вон почему там не включено. Thank you.